Chapter 9. On the imperfection of the geological record. On the absence of intermediate varieties at the present day. On the nature of extinct intermediate varieties, on their number. On the vast lapse of time, as inferred from the rate of deposition and of denudation. On the poorness of our paleontological collections. On the intermittence of geological formations. On the absence of intermediate varieties in any one formation. On the sudden appearance of groups of species. On their sudden appearance in the lowest known fossiliferous strata. In the 6th chapter 1 enumerated the chief objections which might be justly urged against the views maintained in this volume. Most of them have now been discussed. 1. Namely the distinctness of specific forms, and their not being blended together by innumerable transitional links, is a very obvious difficulty. I assigned reasons why such links do not commonly occur at the present day, under the circumstances apparently most favorable for their presence, namely on an extensive and continuous area with graduated physical conditions. I endeavored to show that the life of each species depends in a more important manner on the presence of other already defined organic forms than on climate, and, therefore, that the really governing conditions of life do not graduate away quite insensibly like heat or moisture. I endeavored, also, to show that intermediate varieties, from existing in lesser numbers than the forms which they connect, will generally be beaten out and exterminated during the course of further modification and improvement. The main cause, however, of innumerable intermediate links not now occurring everywhere throughout nature depends on the very process of natural selection, through which new varieties continually take the places of and exterminate their parent forms. But just in proportion as this process of extermination has acted on an enormous scale, so must the number of intermediate varieties, which have formerly existed on the earth, be truly enormous. Why then is not every geological formation and every stratum full of such intermediate links? Geology assuredly does not reveal any such finely graduated organic chain, and this, perhaps, is the most obvious and gravest objection which can be urged against my theory. The explanation lies, as I believe, in the extreme imperfection of the geological record. In the first place, it should always be borne in mind what sort of intermediate forms must, on my theory, have formerly existed. I have found it difficult, when looking at any two species, to avoid picturing to myself forms directly intermediate between them. But this is a wholly false view. We should always look for forms intermediate between each species and a common but unknown progenitor, and the progenitor will generally have differed in some respects from all its modified descendants. To give a simple illustration, the fantail and pouter pigeons have both descended from the rock pigeon. If we possessed all the intermediate varieties which have ever existed, we should have an extremely close series between both and the rock pigeon, but we should have no varieties directly intermediate between the fantail and pouter, none, for instance, combining a tail somewhat expanded with a crop somewhat enlarged, the characteristic features of these two breeds. These two breeds, moreover, have become so much modified, that if we had no historical or indirect evidence regarding their origin, it would not have been possible to have determined from a mere comparison of their structure with that of the rock pigeon, whether they had descended from this species or from some other allied species, such as C. enas. So with natural species, if we look to forms very distinct, for instance to the horse and tapir, we have no reason to suppose that links ever existed directly intermediate between them, but between each and an unknown common parent. The common parent will have had in its whole organization much general resemblance to the tapir and to the horse, but in some points of structure may have differed considerably from both, even perhaps more than they differ from each other. Hence in all such cases, we should be unable to recognize the parent form of any two or more species, even if we closely compared the structure of the parent with that of its modified descendants, unless at the same time we had a nearly perfect chain of the intermediate links. It is just possible by my theory, that one of two living forms might have descended from the other, for instance, a horse from a tapir, and in this case direct intermediate links will have existed between them. But such a case would imply that one form had remained for a very long period unaltered, whilst its descendants had undergone a vast amount of change, and the principle of competition between organism and organism, between child and parent, will render this a very rare event, for in all cases the new and improved forms of life will tend to supplant the old and unimproved forms. By the theory of natural selection, all living species have been connected with the parent species of each genus, by differences not greater than we see between the varieties of the same species at the present day, and these parent species, now generally extinct, have in their turn been similarly connected with more ancient species, and so on backwards, always converging to the common ancestor of each great class. So that the number of intermediate and transitional links between all living and extinct species must have been inconceivably great. But assuredly, if this theory be true, such have lived upon this earth. On the lapse of time. Independently of our not finding fossil remains of such infinitely numerous connecting links, it may be objected that time will not have sufficed for so great an amount of organic change, all changes having been effected very slowly through natural selection. It is hardly possible for me even to recall to the reader, who may not be a practical geologist, the facts leading the mind feebly to comprehend the lapse of time. He who can read Sir Charles Lyell's grand work on the principles of geology, which the future historian will recognize as having produced a revolution in natural science, yet does not admit how incomprehensibly vast have been the past periods of time, may at once close this volume. Not that it suffices to study the principles of geology, or to read special treatises by different observers on separate formations, and to mark how each author attempts to give an inadequate idea of the duration of each formation or even each stratum. A man must for years examine for himself great piles of superimposed strata, and watch the sea at work grinding down old rocks and making fresh sediment, before he can hope to comprehend anything of the lapse of time, the monuments of which we see around us. It is good to wander along lines of sea coast, when formed of moderately hard rocks, and mark the process of degradation. The tides in most cases reach the cliffs only for a short time twice a day, and the waves eat into them only when they are charged with sand or pebbles, for there is reason to believe that pure water can effect little or nothing in wearing away rock. At last the base of the cliff is undermined, huge fragments fall down, and these remaining fixed, have to be worn away, atom by atom, until reduced in size they can be rolled about by the waves, and then are more quickly ground into pebbles, sand, or mud. But how often do we see along the bases of retreating cliffs rounded boulders, all thickly clothed by marine productions, showing how little they are abraded and how seldom they are rolled about. Moreover, if we follow for a few miles any line of rocky cliff, which is undergoing degradation, we find that it is only here and there, along a short length or round a promontory, that the cliffs are at the present time suffering. The appearance of the surface and the vegetation show that elsewhere years have elapsed since the waters washed their base. He who most closely studies the action of the sea on our shores will, I believe, be most deeply impressed with the slowness with which rocky coasts are worn away. The observations on this head by Hugh Miller, and by that excellent observer Mr. Smith of Jordan Hill, are most impressive. With the mind thus impressed, let any one examine beds of conglomerate many thousand feet in thickness, which, though probably formed at a quicker rate than many other deposits, yet, from being formed of worn and rounded pebbles, each of which bears the stamp of time, are good to show how slowly the mass has been accumulated. Let him remember Lyell's profound remark, that the thickness and extent of sedimentary formations are the result and measure of the degradation which the earth's crust has elsewhere suffered. And what an amount of degradation is implied by the sedimentary deposits of many countries! Professor Ramsay has given me the maximum thickness, in most cases from actual measurement, in a few cases from estimate, of each formation in different parts of Great Britain, and this is the result. Feet. Paleozoic strata, not including igneous beds, 57,154. Secondary strata, 13,190. Tertiary strata, 2,240. Making altogether 72,584 feet, that is, very nearly 13 3/4 British miles. Some of these formations, which are represented in England by thin beds, are thousands of feet in thickness on the continent. Moreover, between each successive formation, we have, in the opinion of most geologists, enormously long blank periods. So that the lofty pile of sedimentary rocks in Britain gives but an inadequate idea of the time which has elapsed during their accumulation, yet what time this must have consumed. Good observers have estimated that sediment is deposited by the great Mississippi River at the rate of only 600 feet in 100,000 years. This estimate may be quite erroneous, yet, considering over what wide spaces very fine sediment is transported by the currents of the sea, the process of accumulation in any one area must be extremely slow. But the amount of denudation which the strata have in many places suffered, independently of the rate of accumulation of the degraded matter, probably offers the best evidence of the lapse of time. I remember having been much struck with the evidence of denudation when viewing volcanic islands, which have been worn by the waves and pared all round into perpendicular cliffs of 1,000 or 2,000 feet in height, for the gentle slope of the lava streams, due to their formerly liquid state, showed at a glance how far the hard, rocky beds had once extended into the open ocean. The same story is still more plainly told by faults, those great cracks along which the strata have been upheaved on one side, or thrown down on the other, to the height or depth of thousands of feet, for since the crust cracked, the surface of the land has been so completely planed down by the action of the sea, that no trace of these vast dislocations is externally visible. The Craven Fault, for instance, extends for upwards of 30 miles, and along this line the vertical displacement of the strata has varied from 600 to 3,000 feet. Professor Ramsay has published an account of a downthrow in Anglesey of 2,300 feet, and he informs me that he fully believes there is one in Merionethshire of 12,000 feet, yet in these cases there is nothing on the surface to show such prodigious movements, the pile of rocks on the one or other side having been smoothly swept away. The consideration of these facts impresses my mind almost in the same manner as does the vain endeavor to grapple with the idea of eternity. I am tempted to give one other case, the well-known one of the denudation of the Weald. Though it must be admitted that the denudation of the Weald has been a mere trifle, in comparison with that which has removed masses of our Paleozoic strata, in parts 10,000 feet in thickness, as shown in Professor Ramsay's masterly memoir on this subject. Yet it is an admirable lesson to stand on the North Downs and to look at the distant South Downs, for, remembering that at no great distance to the west the northern and southern escarpments meet and close, one can safely picture to oneself the great dome of rocks which must have covered up the Weald within so limited a period as since the latter part of the chalk formation. The distance from the northern to the southern downs is about 22 miles, and the thickness of the several formations is on an average about 1,100 feet, as I am informed by Professor Ramsay. But if, as some geologists suppose, a range of older rocks underlies the Weald, on the flanks of which the overlying sedimentary deposits might have accumulated in thinner masses than elsewhere, the above estimate would be erroneous, but this source of doubt probably would not greatly affect the estimate as applied to the western extremity of the district. If, then, we knew the rate at which the sea commonly wears away a line of cliff of any given height, we could measure the time requisite to have denuded the Weald. This, of course, cannot be done, but we may, in order to form some crude notion on the subject, assume that the sea would eat into cliffs 500 feet in height at the rate of 1 inch in a century. This will at first appear much too small an allowance, but it is the same as if we were to assume a cliff 1 yard in height to be eaten back along a whole line of coast at the rate of 1 yard in nearly every 22 years. I doubt whether any rock, even as soft as chalk, would yield at this rate excepting on the most exposed coasts, though no doubt the degradation of a lofty cliff would be more rapid from the breakage of the fallen fragments. On the other hand, I do not believe that any line of coast, 10 or 20 miles in length, ever suffers degradation at the same time along its whole indented length, and we must remember that almost all strata contain harder layers or nodules, which from long resisting attrition form a breakwater at the base. Hence, under ordinary circumstances, I conclude that for a cliff 500 feet in height, a denudation of 1 inch per century for the whole length would be an ample allowance. At this rate, on the above data, the denudation of the Weald must have required 306,662,400 years, or say 300 million years. The action of fresh water on the gently inclined Wealden district, when upraised, could hardly have been great, but it would somewhat reduce the above estimate. On the other hand, during oscillations of level, which we know this area has undergone, the surface may have existed for millions of years as land, and thus have escaped the action of the sea. When deeply submerged for perhaps equally long periods, it would, likewise, have escaped the action of the coast waves. So that in all probability a far longer period than 300 million years has elapsed since the latter part of the secondary period. I have made these few remarks because it is highly important for us to gain some notion, however imperfect, of the lapse of years. During each of these years, over the whole world, the land and the water has been peopled by hosts of living forms. What an infinite number of generations, which the mind cannot grasp, must have succeeded each other in the long roll of years. Now turn to our richest geological museums, and what a paltry display we behold. On the poorness of our paleontological collections. That our paleontological collections are very imperfect is admitted by every one. The remark of that admirable paleontologist, the late Edward Forbes, should not be forgotten, namely, that numbers of our fossil species are known and named from single and often broken specimens, or from a few specimens collected on some one spot. Only a small portion of the surface of the Earth has been geologically explored, and no part with sufficient care, as the important discoveries made every year in Europe prove. No organism wholly soft can be preserved. Shells and bones will decay and disappear when left on the bottom of the sea, where sediment is not accumulating. I believe we are continually taking a most erroneous view when we tacitly admit to ourselves that sediment is being deposited over nearly the whole bed of the sea, at a rate sufficiently quick to embed and preserve fossil remains. Throughout an enormously large proportion of the ocean, the bright blue tint of the water bespeaks its purity. The many cases on record of a formation conformably covered, after an enormous interval of time, by another and later formation, without the underlying bed having suffered in the interval any wear and tear, seem explicable only on the view of the bottom of the sea not rarely lying for ages in an unaltered condition. The remains which do become embedded, if in sand or gravel, will when the beds are upraised generally be dissolved by the percolation of rainwater. I suspect that but few of the very many animals which live on the beach between high and low water mark are preserved. For instance, the several species of the chameleony, a subfamily of sessile cirripedes, coat the rocks all over the world in infinite numbers. They are all strictly littoral, with the exception of a single Mediterranean species, which inhabits deep water and has been found fossil in Sicily, whereas not one other species has hitherto been found in any tertiary formation. Yet it is now known that the genus Thamylus existed during the chalk period. The molluscan genus Chiton offers a partially analogous case. With respect to the terrestrial productions which lived during the secondary and Paleozoic periods, it is superfluous to state that our evidence from fossil remains is fragmentary in an extreme degree. For instance, not a land shell is known belonging to either of these vast periods, with one exception discovered by Sir C. Lyell in the Carboniferous strata of North America. In regard to mammiferous remains, a single glance at the historical table published in the supplement to Lyell's manual will bring home the truth. How accidental and rare is their preservation, far better than pages of detail. Nor is their rarity surprising, when we remember how large a proportion of the bones of tertiary mammals have been discovered either in caves or in lacustrine deposits, and that not a cave or true lacustrine bed is known belonging to the age of our secondary or Paleozoic formations. But the imperfection in the geological record mainly results from another and more important cause than any of the foregoing, namely, from the several formations being separated from each other by wide intervals of time. When we see the formations tabulated in written works, or when we follow them in nature, it is difficult to avoid believing that they are closely consecutive. But we know, for instance, from Sir R. Murchison's great work on Russia, what wide gaps there are in that country between the superimposed formations, so it is in North America, and in many other parts of the world. The most skillful geologist, if his attention had been exclusively confined to these large territories, would never have suspected that during the periods which were blank and barren in his own country, great piles of sediment, charged with new and peculiar forms of life, had elsewhere been accumulated. And if in each separate territory, hardly any idea can be formed of the length of time which has elapsed between the consecutive formations, we may infer that this could nowhere be ascertained. The frequent and great changes in the mineralogical composition of consecutive formations, generally implying great changes in the geography of the surrounding lands, whence the sediment has been derived, accords with the belief of vast intervals of time having elapsed between each formation. But we can, I think, see why the geological formations of each region are almost invariably intermittent, that is, have not followed each other in close sequence. Scarcely any fact struck me more when examining many hundred miles of the South American coasts, which have been upraised several hundred feet within the recent period, than the absence of any recent deposit sufficiently extensive to last for even a short geological period. Along the whole west coast, which is inhabited by a peculiar marine fauna, tertiary beds are so scantily developed that no record of several successive and peculiar marine faunas will probably be preserved to a distant age. A little reflection will explain why along the rising coast of the western side of South America no extensive formations with recent or tertiary remains can anywhere be found, though the supply of sediment must for ages have been great, from the enormous degradation of the coast rocks and from muddy streams entering the sea. The explanation, no doubt, is that the littoral and sublittoral deposits are continually worn away, as soon as they are brought up by the slow and gradual rising of the land within the grinding action of the coast waves. We may, I think, safely conclude that sediment must be accumulated in extremely thick, solid, or extensive masses, in order to withstand the incessant action of the waves, when first upraised and during subsequent oscillations of level. Such thick and extensive accumulations of sediment may be formed in two ways, either in profound depths of the sea, in which case, judging from the researches of E. Forbes, we may conclude that the bottom will be inhabited by extremely few animals, and the mass when appraised will give a most imperfect record of the forms of life which then existed, or, sediment may be accumulated to any thickness and extent over a shallow bottom, if it continues slowly to subside. In this latter case, as long as the rate of subsidence and supply of sediment nearly balance each other, the sea will remain shallow and favorable for life, and thus a far saliferous formation thick enough, when upraised, to resist any amount of degradation, may be formed. I am convinced that all our ancient formations, which are rich in fossils, have thus been formed during subsidence. Since publishing my views on this subject in 1845, I have watched the progress of geology, and have been surprised to note how author after author, in treating of this or that great formation, has come to the conclusion that it was accumulated during subsidence. I may add that the only ancient tertiary formation on the west coast of South America which has been bulky enough to resist such degradation as it has as yet suffered, but which will hardly last to a distant geological age, was certainly deposited during a downward oscillation of level, and thus gained considerable thickness. All geological facts tell us plainly that each area has undergone numerous slow oscillations of level, and apparently these oscillations have affected wide spaces. Consequently, formations rich in fossils and sufficiently thick and extensive to resist subsequent degradation may have been formed over wide spaces during periods of subsidence, but only where the supply of sediment was sufficient to keep the sea shallow and to embed and preserve the remains before they had time to decay. On the other hand, as long as the bed of the sea remained stationary, thick deposits could not have been accumulated in the shallow parts, which are the most favorable to life. Still less could this have happened during the alternate periods of elevation, or, to speak more accurately, the beds which were then accumulated will have been destroyed by being upraised and brought within the limits of the coast action. Thus the geological record will almost necessarily be rendered intermittent. I feel much confidence in the truth of these views, for they are in strict accordance with the general principles inculcated by Sir C. Lyell, and E. Forbes independently arrived at a similar conclusion. One remark is here worth a passing notice. During periods of elevation the area of the land and of the adjoining shoal parts of the sea will be increased, and new stations will often be formed, all circumstances most favorable, as previously explained, for the formation of new varieties and species, but during such periods there will generally be a blank in the geological record. On the other hand, during subsidence, the inhabited area and number of inhabitants will decrease, excepting the productions on the shores of a continent when first broken up into an archipelago, and consequently during subsidence, though there will be much extinction, fewer new varieties or species will be formed, and it is during these very periods of subsidence that our great deposits rich in fossils have been accumulated. Nature may almost be said to have guarded against the frequent discovery of her transitional or linking forms. From the foregoing considerations it cannot be doubted that the geological record, viewed as a whole, is extremely imperfect, but if we confine our attention to any one formation, it becomes more difficult to understand why we do not therein find closely graduated varieties between the allied species which lived at its commencement and at its close. Some cases are on record of the same species presenting distinct varieties in the upper and lower parts of the same formation, but, as they are rare, they may be here passed over. Although each formation has indisputably required a vast number of years for its deposition, I can see several reasons why each should not include a graduated series of links between the species which then lived, but I can by no means pretend to assign due proportional weight to the following considerations. Although each formation may mark a very long lapse of years, each perhaps is short compared with the period requisite to change one species into another. I am aware that two paleontologists, whose opinions are worthy of much deference, namely Bron and Woodward, have concluded that the average duration of each formation is twice or thrice as long as the average duration of specific forms. But insuperable difficulties, as it seems to me, prevent us coming to any just conclusion on this head. When we see a species first appearing in the middle of any formation, it would be rash in the extreme to infer that it had not elsewhere previously existed. So again, when we find a species disappearing before the uppermost layers have been deposited, it would be equally rash to suppose that it then became wholly extinct. We forget how small the area of Europe is compared with the rest of the world, nor have the several stages of the same formation throughout Europe been correlated with perfect accuracy. With marine animals of all kinds, we may safely infer a large amount of migration during climatal and other changes, and when we see a species first appearing in any formation, the probability is that it only then first immigrated into that area. It is well known, for instance, that several species appeared somewhat earlier in the Paleozoic beds of North America than in those of Europe, time having apparently been required for their migration from the American to the European seas. In examining the latest deposits of various quarters of the world, it has everywhere been noted that some few still existing species are common in the deposit, but have become extinct in the immediately surrounding sea, or, conversely, that some are now abundant in the neighboring sea, but are rare or absent in this particular deposit. It is an excellent lesson to reflect on the ascertained amount of migration of the inhabitants of Europe during the glacial period, which forms only a part of one whole geological period, and likewise to reflect on the great changes of level, on the inordinately great change of climate, on the prodigious lapse of time, all included within this same glacial period. Yet it may be doubted whether in any quarter of the world, sedimentary deposits, including fossil remains, have gone on accumulating within the same area during the whole of this period. It is not, for instance, probable that sediment was deposited during the whole of the glacial period near the mouth of the Mississippi, within that limit of depth at which marine animals can flourish, for we know what vast geographical changes occurred in other parts of America during this space of time. When such beds as were deposited in shallow water near the mouth of the Mississippi during some part of the glacial period shall have been upraised, organic remains will probably first appear and disappear at different levels, owing to the migration of species and to geographical changes. And in the distant future, a geologist examining these beds might be tempted to conclude that the average duration of life of the embedded fossils had been less than that of the glacial period, instead of having been really far greater, that is extending from before the glacial epoch to the present day. In order to get a perfect gradation between two forms in the upper and lower parts of the same formation, the deposit must have gone on accumulating for a very long period, in order to have given sufficient time for the slow process of variation. Hence the deposit will generally have to be a very thick one, and the species undergoing modification will have had to live on the same area throughout this whole time. But we have seen that a thick fossiliferous formation can only be accumulated during a period of subsidence, and to keep the depth approximately the same, which is necessary in order to enable the same species to live on the same space, the supply of sediment must nearly have counterbalanced the amount of subsidence. But this same movement of subsidence will often tend to sink the area whence the sediment is derived, and thus diminish the supply whilst the downward movement continues. In fact, this nearly exact balancing between the supply of sediment and the amount of subsidence is probably a rare contingency, for it has been observed by more than one paleontologist that very thick deposits are usually barren of organic remains, except near their upper or lower limits. It would seem that each separate formation, like the whole pile of formations in any country, has generally been intermittent in its accumulation. When we see, as is so often the case, a formation composed of beds of different mineralogical composition, we may reasonably suspect that the process of deposition has been much interrupted, as a change in the currents of the sea and a supply of sediment of a different nature will generally have been due to geographical changes requiring much time. Nor will the closest inspection of a formation give any idea of the time which its deposition has consumed. Many instances could be given of beds only a few feet in thickness, representing formations, elsewhere thousands of feet in thickness, and which must have required an enormous period for their accumulation, yet no one ignorant of this fact would have suspected the vast lapse of time represented by the thinner formation. Many cases could be given of the lower beds of a formation having been upraised, denuded, submerged, and then recovered by the upper beds of the same formation, facts showing what wide, yet easily overlooked, intervals have occurred in its accumulation. In other cases we have the plainest evidence in great fossilized trees, still standing upright as they grew, of many long intervals of time and changes of level during the process of deposition, which would never even have been suspected, had not the trees chanced to have been preserved. Thus, Messrs. Lyell and Dawson found carboniferous beds 1,400 feet thick in Nova Scotia, with ancient root-bearing strata, one above the other, at no less than 68 different levels. Hence, when the same species occur at the bottom, middle, and top of a formation, the probability is that they have not lived on the same spot during the whole period of deposition, but have disappeared and reappeared, perhaps many times, during the same geological period. So that if such species were to undergo a considerable amount of modification during any one geological period, a section would not probably include all the fine intermediate gradations which must on my theory have existed between them, but abrupt, though perhaps very slight, changes of form. It is all important to remember that naturalists have no golden rule by which to distinguish species and varieties. They grant some little variability to each species, but when they meet with a somewhat greater amount of difference between any two forms, they rank both as species, unless they are enabled to connect them together by close intermediate gradations. And this from the reasons just assigned we can seldom hope to effect in any one geological section. Supposing B and C to be two species, and a third, A, to be found in an underlying bed, even if A were strictly intermediate between B and C, it would simply be ranked as a third and distinct species, unless at the same time it could be most closely connected with either one or both forms by intermediate varieties. Nor should it be forgotten, as before explained, that A might be the actual progenitor of B and C, and yet might not at all necessarily be strictly intermediate between them in all points of structure. So that we might obtain the parent species and its several modified descendants from the lower and upper beds of a formation, and unless we obtained numerous transitional gradations, we should not recognize their relationship and should consequently be compelled to rank them all as distinct species. It is notorious on what excessively slight differences many paleontologists have founded their species, and they do this the more readily if the specimens come from different substages of the same formation. Some experienced conchologists are now sinking many of the very fine species of Daurbigny and others into the rank of varieties, and on this view we do find the kind of evidence of change which on my theory we ought to find. Moreover, if we look to rather wider intervals, namely, to distinct but consecutive stages of the same great formation, we find that the embedded fossils, though almost universally ranked as specifically different, yet are far more closely allied to each other than other species found in more widely separated formations, but to this subject I shall have to return in the following chapter. One other consideration is worth notice: with animals and plants that can propagate rapidly and are not highly locomotive, there is reason to suspect, as we have formerly seen, that their varieties are generally at first local, and that such local varieties do not spread widely and supplant their parent forms until they have been modified and perfected in some considerable degree. According to this view, the chance of discovering in a formation in any one country all the early stages of transition between any two forms is small, for the successive changes are supposed to have been local or confined to some one spot. Most marine animals have a wide range, and we have seen that with plants it is those which have the widest range that oftenest present varieties, so that with shells and other marine animals, it is probably those which have had the widest range, far exceeding the limits of the known geological formations of Europe, which have oftenest given rise, first to local varieties and ultimately to new species, and this again would greatly lessen the chance of our being able to trace the stages of transition in any one geological formation. It should not be forgotten that at the present day, with perfect specimens for examination, two forms can seldom be connected by intermediate varieties and thus prove to be the same species until many specimens have been collected from many places, and in the case of fossil species this could rarely be effected by paleontologists. We shall, perhaps, best perceive the improbability of our being enabled to connect species by numerous, fine, intermediate, fossil links, by asking ourselves whether, for instance, geologists at some future period will be able to prove that our different breeds of cattle, sheep, horses, and dogs have descended from a single stock or from several aboriginal stocks, or, again, whether certain seashells inhabiting the shores of North America, which are ranked by some conchologists as distinct species from their European representatives, and by other conchologists as only varieties, are really varieties or are, as it is called, specifically distinct. This could be effected only by the future geologist discovering in a fossil state numerous intermediate gradations, and such success seems to me improbable in the highest degree. Geological research, though it has added numerous species to existing and extinct genera, and has made the intervals between some few groups less wide than they otherwise would have been, yet has done scarcely anything in breaking down the distinction between species, by connecting them together by numerous, fine, intermediate varieties, and this not having been effected, is probably the gravest and most obvious of all the many objections which may be urged against my views. Hence it will be worthwhile to sum up the foregoing remarks under an imaginary illustration. The Malay archipelago is of about the size of Europe from the North Cape to the Mediterranean, and from Britain to Russia, and therefore equals all the geological formations which have been examined with any accuracy, excepting those of the United States of America. I fully agree with Mr. Godwin Austen that the present condition of the Malay archipelago, with its numerous large islands separated by wide and shallow seas, probably represents the former state of Europe, when most of our formations were accumulating. The Malay archipelago is one of the richest regions of the whole world in organic beings, yet if all the species were to be collected which have ever lived there, how imperfectly would they represent the natural history of the world. But we have every reason to believe that the terrestrial productions of the archipelago would be preserved in an excessively imperfect manner in the formations which we suppose to be there accumulating. I suspect that not many of the strictly literal animals, or of those which lived on naked submarine rocks, would be embedded, and those embedded in gravel or sand would not endure to a distant epoch. Wherever sediment did not accumulate on the bed of the sea, or where it did not accumulate at a sufficient rate to protect organic bodies from decay, no remains could be preserved. In our archipelago, I believe that fossiliferous formations could be formed of sufficient thickness to last to an age, as distant in futurity as the secondary formations lie in the past, only during periods of subsidence. These periods of subsidence would be separated from each other by enormous intervals, during which the area would be either stationary or rising. Whilst rising, each fossiliferous formation would be destroyed, almost as soon as accumulated, by the incessant coast action, as we now see on the shores of South America. During the periods of subsidence there would probably be much extinction of life. During the periods of elevation, there would be much variation, but the geological record would then be least perfect. It may be doubted whether the duration of any one great period of subsidence over the whole or part of the archipelago, together with a contemporaneous accumulation of sediment, would exceed the average duration of the same specific forms, and these contingencies are indispensable for the preservation of all the transitional gradations between any two or more species. If such gradations were not fully preserved, transitional varieties would merely appear as so many distinct species. It is, also, probable that each great period of subsidence would be interrupted by oscillations of level, and that slight climatal changes would intervene during such lengthy periods, and in these cases the inhabitants of the archipelago would have to migrate, and no closely consecutive record of their modifications could be preserved in any one formation. Very many of the marine inhabitants of the archipelago now range thousands of miles beyond its confines. An analogy leads me to believe that it would be chiefly these far-ranging species which would oftenest produce new varieties, and the varieties would at first generally be local or confined to one place, but if possessed of any decided advantage, or when further modified and improved, they would slowly spread and supplant their parent forms. When such varieties return to their ancient homes, as they would differ from their former state, in a nearly uniform, though perhaps extremely slight degree, they would, according to the principles followed by many paleontologists, be ranked as new and distinct species. If then there be some degree of truth in these remarks, we have no right to expect to find in our geological formations an infinite number of those fine transitional forms, which on my theory assuredly have connected all the past and present species of the same group into one long and branching chain of life. We ought only to look for a few links, some more closely, some more distantly related to each other, and these links, let them be ever so close, if found in different stages of the same formation, would, by most paleontologists, be ranked as distinct species. But I do not pretend that I should ever have suspected how poor a record of the mutations of life the best preserved geological section presented, had not the difficulty of our not discovering innumerable transitional links between the species which appeared at the commencement and close of each formation, pressed so hardly on my theory. On the sudden appearance of whole groups of allied species. The abrupt manner in which whole groups of species suddenly appear in certain formations has been urged by several paleontologists, for instance, by Agassiz, Pictet, and by none more forcibly than by Professor Sedgwick, as a fatal objection to the belief in the transmutation of species. If numerous species, belonging to the same genera or families, have really started into life all at once, the fact would be fatal to the theory of descent with slow modification through natural selection. For the development of a group of forms, all of which have descended from some one progenitor, must have been an extremely slow process, and the progenitors must have lived long ages before their modified descendants. But we continually overrate the perfection of the geological record, and falsely infer, because certain genera or families have not been found beneath a certain stage, that they did not exist before that stage. We continually forget how large the world is, compared with the area over which our geological formations have been carefully examined. We forget that groups of species may elsewhere have long existed and have slowly multiplied before they invaded the ancient archipelagos of Europe and of the United States. We do not make due allowance for the enormous intervals of time, which have probably elapsed between our consecutive formations, longer perhaps in some cases than the time required for the accumulation of each formation. These intervals will have given time for the multiplication of species from some one or some few parent forms, and in the succeeding formation such species will appear as if suddenly created. I may here recall a remark formerly made, namely that it might require a long succession of ages to adapt an organism to some new and peculiar line of life, for instance to fly through the air, but that when this had been effected, and a few species had thus acquired a great advantage over other organisms, a comparatively short time would be necessary to produce many divergent forms, which would be able to spread rapidly and widely throughout the world. I will now give a few examples to illustrate these remarks, and to show how liable we are to error in supposing that whole groups of species have suddenly been produced. I may recall the well-known fact that in geological treatises, published not many years ago, the great class of mammals was always spoken of as having abruptly come in at the commencement of the Tertiary series. And now one of the richest known accumulations of fossil mammals belongs to the middle of the Secondary series, and one true mammal has been discovered in the New Red Sandstone at nearly the commencement of this great series. Cuvier used to urge that no monkey occurred in any Tertiary stratum, but now extinct species have been discovered in India, South America, and in Europe even as far back as the Eocene stage. The most striking case, however, is that of the whale family, as these animals have huge bones, are marine, and range over the world. The fact of not a single bone of a whale having been discovered in any secondary formation seemed fully to justify the belief that this great and distinct order had been suddenly produced in the interval between the latest secondary and earliest tertiary formation. But now we may read in the supplement to Lyell's A Manual, published in 1858, clear evidence of the existence of whales in the Upper Greensand, some time before the close of the secondary period. I may give another instance, which from having passed under my own eyes has much struck me. In a memoir on fossil sessile cirripedes, I have stated that, from the number of existing and extinct tertiary species, from the extraordinary abundance of the individuals of many species all over the world, from the Arctic regions to the equator, inhabiting various zones of depths from the upper tidal limits to 50 fathoms, from the perfect manner in which specimens are preserved in the oldest tertiary beds, from the ease with which even a fragment of a valve can be recognized, from all these circumstances, I inferred that had sessile cirripedes existed during the secondary periods, they would certainly have been preserved and discovered, and as not one species had been discovered in beds of this age, I concluded that this great group had been suddenly developed at the commencement of the Tertiary series. This was a sore trouble to me, adding as I thought one more instance of the abrupt appearance of a great group of species. But my work had hardly been published, when a skillful paleontologist, M. Bosquet, sent me a drawing of a perfect specimen of an unmistakable sessile cirripede, which he had himself extracted from the chalk of Belgium. And, as if to make the case as striking as possible, this sessile cirripede was a Thamylus, a very common, large, and ubiquitous genus, of which not one specimen has as yet been found even in any tertiary stratum. Hence we now positively know that sessile cirripedes existed during the secondary period, and these cirripedes might have been the progenitors of our many tertiary and existing species. The case most frequently insisted on by paleontologists of the apparently sudden appearance of a whole group of species is that of the teleostean fishes, low down in the chalk period. This group includes the large majority of existing species. Lately, Professor Pictet has carried their existence one substage further back, and some paleontologists believe that certain much older fishes, of which the affinities are as yet imperfectly known, are really teleostean. Assuming, however, that the whole of them did appear, as Agassiz believes, at the commencement of the chalk formation, the fact would certainly be highly remarkable, but I cannot see that it would be an insuperable difficulty on my theory, unless it could likewise be shown that the species of this group appeared suddenly and simultaneously throughout the world at this same period. It is almost superfluous to remark that hardly any fossil fish are known from south of the equator, and by running through Pictet's paleontology it will be seen that very few species are known from several formations in Europe. Some few families of fish now have a confined range. The teleostean fish might formerly have had a similarly confined range, and after having been largely developed in some one sea, might have spread widely. Nor have we any right to suppose that the seas of the world have always been so freely open from south to north as they are at present. Even at this day, if the Malay archipelago were converted into land, the tropical parts of the Indian Ocean would form a large and perfectly enclosed basin, in which any great group of marine animals might be multiplied, and here they would remain confined, until some of the species became adapted to a cooler climate, and were enabled to double the southern capes of Africa or Australia, and thus reach other and distant seas. From these and similar considerations, but chiefly from our ignorance of the geology of other countries beyond the confines of Europe and the United States, and from the revolution in our paleontological ideas on many points, which the discoveries of even the last dozen years have effected, it seems to me to be about as rash in us to dogmatize on the succession of organic beings throughout the world, as it would be for a naturalist to land for 5 minutes on some one barren point in Australia, and then to discuss the number and range of its productions. On the sudden appearance of groups of allied species in the lowest known fossiliferous strata. There is another and allied difficulty, which is much graver. I allude to the manner in which numbers of species of the same group suddenly appear in the lowest known fossiliferous rocks. Most of the arguments which have convinced me that all the existing species of the same group have descended from one progenitor apply with nearly equal force to the earliest known species. For instance, I cannot doubt that all the Silurian trilobites have descended from some one crustacean, which must have lived long before the Silurian age, and which probably differed greatly from any known animal. Some of the most ancient Silurian animals, as the nautilus, lingula, etc., do not differ much from living species, and it cannot on my theory be supposed that these old species were the progenitors of all the species of the orders to which they belong, for they do not present characters in any degree intermediate between them. If, moreover, they had been the progenitors of these orders, they would almost certainly have been long ago supplanted and exterminated by their numerous and improved descendants. Consequently, if my theory be true, it is indisputable that before the lowest Silurian stratum was deposited, long periods elapsed, as long as, or probably far longer than, the whole interval from the Silurian age to the present day, and that during these vast, yet quite unknown, periods of time, the world swarmed with living creatures. To the question why we do not find records of these vast primordial periods, I can give no satisfactory answer. Several of the most eminent geologists, with Sir R. Murchison at their head, are convinced that we see in the organic remains of the lowest Silurian stratum the dawn of life on this planet. Other highly competent judges, as Lyell and the late E. Forbes, dispute this conclusion. We should not forget that only a small portion of the world is known with accuracy. M. Barrand has lately added another and lower stage to the Silurian system, abounding with new and peculiar species. Traces of life have been detected in the longmine beds beneath Barrand's so-called primordial zone. The presence of phosphatic nodules and bituminous matter in some of the lowest Azoic rocks probably indicates the former existence of life at these periods. But the difficulty of understanding the absence of vast piles of fossiliferous strata, which on my theory no doubt were somewhere accumulated before the Silurian epoch, is very great. If these most ancient beds had been wholly worn away by denudation or obliterated by metamorphic action, we ought to find only small remnants of the formations next succeeding them in age, and these ought to be very generally in a metamorphosed condition. But the descriptions which we now possess of the Silurian deposits over immense territories in Russia and in North America do not support the view that the older a formation is, the more it has suffered the extremity of denudation and metamorphism. The case at present must remain inexplicable, and may be truly urged as a valid argument against the views here entertained. To show that it may hereafter receive some explanation, I will give the following hypothesis. From the nature of the organic remains, which do not appear to have inhabited profound depths in the several formations of Europe and of the United States, and from the amount of sediment, miles in thickness, of which the formations are composed, we may infer that from first to last large islands or tracts of land, whence the sediment was derived, occurred in the neighborhood of the existing continents of Europe and North America. But we do not know what was the state of things in the intervals between the successive formations, whether Europe and the United States during these intervals existed as dry land, or as a submarine surface near land, on which sediment was not deposited, or again as the bed of an open and unfathomable sea. Looking to the existing oceans, which are thrice as extensive as the land, we see them studded with many islands, but not one oceanic island is as yet known to afford even a remnant of any Paleozoic or secondary formation. Hence we may perhaps infer that during the Paleozoic and secondary periods, neither continents nor continental islands existed where our oceans now extend, for had they existed there, Paleozoic and secondary formations would in all probability have been accumulated from sediment derived from their wear and tear, and would have been at least partially upheaved by the oscillations of level, which we may fairly conclude must have intervened during these enormously long periods. If then we may infer anything from these facts, we may infer that where our oceans now extend, oceans have extended from the remotest period of which we have any record, and on the other hand, that where continents now exist, large tracts of land have existed, subjected no doubt to great oscillations of level, since the earliest Silurian period. The colored map appended to my volume on coral reefs led me to conclude that the great oceans are still mainly areas of subsidence, the great archipelagos still areas of oscillations of level, and the continents areas of elevation. But have we any right to assume that things have thus remained from eternity? Our continents seem to have been formed by a preponderance, during many oscillations of level, of the force of elevation, but may not the areas of preponderant movement have changed in the lapse of ages? At a period immeasurably antecedent to the Silurian epoch, continents may have existed where oceans are now spread out, and clear and open oceans may have existed where our continents now stand. Nor should we be justified in assuming that if, for instance, the bed of the Pacific Ocean were now converted into a continent, we should there find formations older than the Silurian strata, supposing such to have been formerly deposited, for it might well happen that strata which had subsided some miles nearer to the center of the Earth, and which had been pressed on by an enormous weight of superincumbent water, might have undergone far more metamorphic action than strata which have always remained nearer to the surface. The immense areas in some parts of the world, for instance in South America, of bare metamorphic rocks, which must have been heated under great pressure, have always seemed to me to require some special explanation, and we may perhaps believe that we see in these large areas the many formations long anterior to the Silurian epoch in a completely metamorphosed condition. The several difficulties here discussed, namely our not finding in the successive formations infinitely numerous transitional links between the many species which now exist or have existed, the sudden manner in which whole groups of species appear in our European formations, the almost entire absence, as at present known, of fossiliferous formations beneath the Silurian strata, are all undoubtedly of the gravest nature. We see this in the plainest manner by the fact that all the most eminent paleontologists, namely Cuvier, Owen, Agassiz, Barrand, Falconer, E. Forbes, etc., and all our greatest geologists, as Lyell, Murchison, Sedgwick, etc., have unanimously, often vehemently, maintained the immutability of species. But I have reason to believe that one great authority, Sir Charles Lyell, from further reflection entertains grave doubts on this subject. I feel how rash it is to differ from these great authorities, to whom, with others, we owe all our knowledge. Those who think the natural geological record in any degree perfect, and who do not attach much weight to the facts and arguments of other kinds given in this volume, will undoubtedly at once reject my theory. For my part, following out Lyell's metaphor, I look at the natural geological record as a history of the world imperfectly kept, and written in a changing dialect. Of this history we possess the last volume alone, relating only to 2 or 3 countries. Of this volume, only here and there a short chapter has been preserved, and of each page, only here and there a few lines. Each word of the slowly changing language, in which the history is supposed to be written, being more or less different in the interrupted succession of chapters, may represent the apparently abruptly changed forms of life, entombed in our consecutive, but widely separated formations. On this view, the difficulties above discussed are greatly diminished, or even disappear. Chapter 10. On the geological succession of organic beings. On the slow and successive appearance of new species. On their different rates of change. Species once lost do not reappear. Groups of species follow the same general rules in their appearance and disappearance as do single species. On extinction. On simultaneous changes in the forms of life throughout the world. On the affinities of extinct species to each other and to living species. On the state of development of ancient forms. On the succession of the same types within the same areas. Summary of preceding and present chapters. Let us now see whether the several facts and rules relating to the geological succession of organic beings better accord with the common view of the immutability of species, or with that of their slow and gradual modification through descent and natural selection. New species have appeared very slowly, one after another, both on the land and in the waters. Lyell has shown that it is hardly possible to resist the evidence on this head in the case of the several tertiary stages, and every year tends to fill up the blanks between them, and to make the percentage system of lost and new forms more gradual. In some of the most recent beds, though undoubtedly of high antiquity if measured by years, only 1 or 2 species are lost forms, and only 1 or 2 are new forms, having here appeared for the first time, either locally, or, as far as we know, on the face of the earth. If we may trust the observations of Philippi in Sicily, the successive changes in the marine inhabitants of that island have been many and most gradual. The secondary formations are more broken, but, as Bron has remarked, neither the appearance nor disappearance of their many now extinct species has been simultaneous in each separate formation. Species of different genera and classes have not changed at the same rate, or in the same degree. In the oldest tertiary beds a few living shells may still be found in the midst of a multitude of extinct forms. Falconer has given a striking instance of a similar fact in an existing crocodile associated with many strange and lost mammals and reptiles in the sub-Himalayan deposits. The Silurian lingula differs but little from the living species of this genus, whereas most of the other Silurian mollusks and all the crustaceans have changed greatly. The productions of the land seem to change at a quicker rate than those of the sea, of which a striking instance has lately been observed in Switzerland. There is some reason to believe that organisms, considered high in the scale of nature, change more quickly than those that are low, though there are exceptions to this rule. The amount of organic change, as Pictet has remarked, does not strictly correspond with the succession of our geological formations, so that between each 2 consecutive formations, the forms of life have seldom changed in exactly the same degree. Yet if we compare any but the most closely related formations, all the species will be found to have undergone some change. When a species has once disappeared from the face of the earth, we have reason to believe that the same identical form never reappears. The strongest apparent exception to this latter rule is that of the so-called colonies of M. Barrand, which intrude for a period in the midst of an older formation, and then allow the pre-existing fauna to reappear, but Lyell's explanation, namely, that it is a case of temporary migration from a distinct geographical province, seems to me satisfactory. These several facts accord well with my theory. I believe in no fixed law of development, causing all the inhabitants of a country to change abruptly, or simultaneously, or to an equal degree. The process of modification must be extremely slow. The variability of each species is quite independent of that of all others. Whether such variability be taken advantage of by natural selection, and whether the variations be accumulated to a greater or lesser amount, thus causing a greater or lesser amount of modification in the varying species, depends on many complex contingencies, on the variability being of a beneficial nature, on the power of intercrossing, on the rate of breeding, on the slowly changing physical conditions of the country, and more especially on the nature of the other inhabitants with which the varying species comes into competition. Hence it is by no means surprising that one species should retain the same identical form much longer than others, or, if changing, that it should change less. We see the same fact in geographical distribution, for instance, in the land shells and coleopterous insects of Madeira having come to differ considerably from their nearest allies on the continent of Europe, whereas the marine shells and birds have remained unaltered. We can perhaps understand the apparently quicker rate of change in terrestrial and in more highly organized productions compared with marine and lower productions, by the more complex relations of the higher beings to their organic and inorganic conditions of life, as explained in a former chapter. When many of the inhabitants of a country have become modified and improved, we can understand, on the principle of competition, and on that of the many all-important relations of organism to organism, that any form which does not become in some degree modified and improved, will be liable to be exterminated. Hence we can see why all the species in the same region do at last, if we look to wide enough intervals of time, become modified, for those which do not change will become extinct. In members of the same class the average amount of change, during long and equal periods of time, may, perhaps, be nearly the same, But as the accumulation of long-enduring fossiliferous formations depends on great masses of sediment having been deposited on areas whilst subsiding, our formations have been almost necessarily accumulated at wide and irregularly intermittent intervals. Consequently, the amount of organic change exhibited by the fossils embedded in consecutive formations is not equal. Each formation, on this view, does not mark a new and complete act of creation, but only an occasional scene, taken almost at hazard, in a slowly changing drama. We can clearly understand why a species when once lost should never reappear, even if the very same conditions of life, organic and inorganic, should recur. For though the offspring of one species might be adapted, and no doubt this has occurred in innumerable instances, to fill the exact place of another species in the economy of nature, and thus supplant it, yet the two forms, the old and the new, would not be identically the same, for both would almost certainly inherit different characters from their distinct progenitors. For instance, it is just possible, if our fantail pigeons were all destroyed, that fanciers, by striving during long ages for the same object, might make a new breed hardly distinguishable from our present fantail. But if the parent rock pigeon were also destroyed, and in nature we have every reason to believe that the parent form will generally be supplanted and exterminated by its improved offspring, it is quite incredible that a fantail, identical with the existing breed, could be raised from any other species of pigeon, or even from the other well-established races of the domestic pigeon, for the newly formed fantail would be almost sure to inherit from its new progenitor some slight characteristic differences. Groups of species, that is, genera and families, follow the same general rules in their appearance and disappearance as do single species, changing more or less quickly, and in a greater or lesser degree. A group does not reappear after it has once disappeared, or its existence, as long as it lasts, is continuous. I am aware that there are some apparent exceptions to this rule, but the exceptions are surprisingly few, so few, that E. Forbes, Pictet, and Woodward, though all strongly opposed to such views as I maintain, admit its truth, and the rule strictly accords with my theory. For as all the species of the same group have descended from some one species, it is clear that as long as any species of the group have appeared in the long succession of ages, so long must its members have continuously existed, in order to have generated either new and modified or the same old and unmodified forms. Species of the genus Lingula, for instance, must have continuously existed by an unbroken succession of generations, from the lowest Silurian stratum to the present day. We have seen in the last chapter that the species of a group sometimes falsely appear to have come in abruptly, and I have attempted to give an explanation of this fact, which if true would have been fatal to my views. But such cases are certainly exceptional, the general rule being a gradual increase in number, till the group reaches its maximum, and then, sooner or later, it gradually decreases. If the number of the species of a genus, or the number of the genera of a family, be represented by a vertical line of varying thickness, crossing the successive geological formations in which the species are found, the line will sometimes falsely appear to begin at its lower end, not in a sharp point, but abruptly. It then gradually thickens upwards, sometimes keeping for a space of equal thickness, and ultimately thins out in the upper beds, marking the decrease and final extinction of the species. This gradual increase in number of the species of a group is strictly conformable with my theory, as the species of the same genus, and the genera of the same family, can increase only slowly and progressively, for the process of modification and the production of a number of allied forms must be slow and gradual, one species giving rise first to 2 or 3 varieties, these being slowly converted into species, which in their turn produce by equally slow steps other species, and so on, like the branching of a great tree from a single stem, till the group becomes large. On extinction. We have as yet spoken only incidentally of the disappearance of species and of groups of species. On the theory of natural selection, the extinction of old forms and the production of new and improved forms are intimately connected together. The old notion of all the inhabitants of the earth having been swept away at successive periods by catastrophes is very generally given up, even by those geologists, as Elie de Beaumont, Murchison, Barrand, etc., whose general views would naturally lead them to this conclusion. On the contrary, we have every reason to believe, from the study of the tertiary formations, that species and groups of species gradually disappear, one after another, first from one spot, then from another, and finally from the world. Both single species and whole groups of species last for very unequal periods, some groups, as we have seen, having endured from the earliest known dawn of life to the present day, some having disappeared before the close of the Paleozoic period. No fixed law seems to determine the length of time during which any single species or any single genus endures. There is reason to believe that the complete extinction of the species of a group is generally a slower process than their production, if the appearance and disappearance of a group of species be represented, as before, by a vertical line of varying thickness. The line is found to taper more gradually at its upper end, which marks the progress of extermination, than at its lower end, which marks the first appearance and increase in numbers of the species. In some cases, however, the extermination of whole groups of beings, as of ammonites towards the close of the secondary period, has been wonderfully sudden. The whole subject of the extinction of species has been involved in the most gratuitous mystery. Some authors have even supposed that as the individual has a definite length of life, so have species a definite duration. No one, I think, can have marveled more at the extinction of species than I have done. When I found in La Plata the tooth of a horse embedded with the remains of Mastodon, Megatherium, Toxodon, and other extinct monsters, which all coexisted with still living shells at a very late geological period, I was filled with astonishment, foreseeing that the horse, since its introduction by the Spaniards into South America, has run wild over the whole country and has increased in numbers at an unparalleled rate. I asked myself what could so recently have exterminated the former horse, under conditions of life apparently so favorable. But how utterly groundless was my astonishment! Professor Owen soon perceived that the tooth, though so like that of the existing horse, belonged to an extinct species. Had this horse been still living, but in some degree rare, no naturalist would have felt the least surprise at its rarity, for rarity is the attribute of a vast number of species of all classes, in all countries. If we ask ourselves why this or that species is rare, we answer that something is unfavorable in its conditions of life, but what that something is, we can hardly ever tell. On the supposition of the fossil horse still existing as a rare species, we might have felt certain from the analogy of all other mammals, even of the slow-breeding elephant, and from the history of the naturalization of the domestic horse in South America, that under more favorable conditions it would in a very few years have stocked the whole continent. But we could not have told what the unfavorable conditions were which checked its increase, whether some one or several contingencies, and at what period of the horse's life, and in what degree, they severally acted. If the conditions had gone on, however slowly, becoming less and less favorable, we assuredly should not have perceived the fact, yet the fossil horse would certainly have become rarer, and finally extinct, its place being seized on by some more successful competitor. It is most difficult always to remember that the increase of every living being is constantly being checked by unperceived injurious agencies, and that these same unperceived agencies are amply sufficient to cause rarity, and finally extinction. We see in many cases in the more recent tertiary formations, that rarity precedes extinction, and we know that this has been the progress of events with those animals which have been exterminated, either locally or wholly, through man's agency. I may repeat what I published in 1845, namely, that to admit that species generally become rare before they become extinct, to feel no surprise at the rarity of a species, and yet to marvel greatly when it ceases to exist, is much the same as to admit that sickness in the individual is the forerunner of death, to feel no surprise at sickness, but when the sick man dies, to wonder and to suspect that he died by some unknown deed of violence. The theory of natural selection is grounded on the belief that each new variety, and ultimately each new species, is produced and maintained by having some advantage over those with which it comes into competition, and the consequent extinction of less favored forms almost inevitably follows. It is the same with our domestic productions. When a new and slightly improved variety has been raised, it at first supplants the less improved varieties in the same neighborhood. When much improved it is transported far and near, like our shorthorn cattle, and takes the place of other breeds in other countries. Thus the appearance of new forms and the disappearance of old forms, both natural and artificial, are bound together. In certain flourishing groups, the number of new specific forms which have been produced within a given time is probably greater than that of the old forms which have been exterminated, but we know that the number of species has not gone on indefinitely increasing, at least during the later geological periods, so that looking to later times we may believe that the production of new forms has caused the extinction of about the same number of old forms. The competition will generally be most severe, as formerly explained and illustrated by examples, between the forms which are most like each other in all respects. Hence the improved and modified descendants of a species will generally cause the extermination of the parent species, and if many new forms have been developed from any one species, the nearest allies of that species, i.e. the species of the same genus, will be the most liable to extermination. Thus, as I believe, a number of new species descended from one species, that is a new genus, comes to supplant an old genus, belonging to the same family. But it must often have happened that a new species belonging to some one group will have seized on the place occupied by a species belonging to a distinct group, and thus caused its extermination, and if many allied forms be developed from the successful intruder, many will have to yield their places, and it will generally be allied forms, which will suffer from some inherited inferiority in common. But whether it be species belonging to the same or to a distinct class, which yield their places to other species which have been modified and improved, a few of the sufferers may often long be preserved, from being fitted to some peculiar line of life, or from inhabiting some distant and isolated station, where they have escaped severe competition. For instance, a single species of Trigonia, a great genus of shells in the secondary formations, survives in the Australian seas, and a few members of the great and almost extinct group of ganorid fishes still inhabit our fresh waters. Therefore the utter extinction of a group is generally, as we have seen, a slower process than its production. With respect to the apparently sudden extermination of whole families or orders, as of trilobites at the close of the Paleozoic period and of ammonites at the close of the secondary period, we must remember what has been already said on the probable wide intervals of time between our consecutive formations, and in these intervals there may have been much slow extermination. Moreover, when by sudden immigration or by unusually rapid development, many species of a new group have taken possession of a new area, they will have exterminated in a correspondingly rapid manner many of the old inhabitants, and the forms which thus yield their places will commonly be allied, for they will partake of some inferiority in common. Thus, as it seems to me, the manner in which single species and whole groups of species become extinct accords well with the theory of natural selection. We need not marvel at extinction. If we must marvel, let it be at our presumption in imagining for a moment that we understand the many complex contingencies on which the existence of each species depends. If we forget for an instant that each species tends to increase inordinately, and that some check is always in action, yet seldom perceived by us, the whole economy of nature will be utterly obscured. Whenever we can precisely say why this species is more abundant in individuals than that, why this species and not another can be naturalized in a given country, then, and not till then, we may justly feel surprise why we cannot account for the extinction of this particular species or group of species. On the forms of life changing almost simultaneously throughout the world. Scarcely any paleontological discovery is more striking than the fact that the forms of life change almost simultaneously throughout the world. Thus our European chalk formation can be recognized in many distant parts of the world, under the most different climates, where not a fragment of the mineral chalk itself can be found, namely, in North America, in equatorial South America, in Tierra del Fuego, at the Cape of Good Hope, and in the peninsula of India. For at these distant points, the organic remains in certain beds present an unmistakable degree of resemblance to those of the chalk. It is not that the same species are met with, for in some cases not one species is identically the same, but they belong to the same families, genera, and sections of genera, and sometimes are similarly characterized in such trifling points as mere superficial sculpture. Moreover, other forms, which are not found in the chalk of Europe, but which occur in the formations either above or below, are similarly absent at these distant points of the world. In the several successive Paleozoic formations of Russia, Western Europe, and North America, a similar parallelism in the forms of life has been observed by several authors, so it is, according to Lyell, with the several European and North American tertiary deposits. Even if the few fossil species which are common to the Old and New worlds be kept wholly out of view, the general parallelism in the successive forms of life, in the stages of the widely separated Paleozoic and Tertiary periods, would still be manifest, and the several formations could be easily correlated. These observations, however, relate to the marine inhabitants of distant parts of the world. We have not sufficient data to judge whether the productions of the land and of fresh water change at distant points in the same parallel manner. We may doubt whether they have thus changed if the Megatherium, Mylodon, Macrauchenia, and Toxodon had been brought to Europe from La Plata without any information in regard to their geological position. No one would have suspected that they had coexisted with still living seashells, but as these anomalous monsters coexisted with the mastodon and horse, It might at least have been inferred that they had lived during one of the latter tertiary stages. When the marine forms of life are spoken of as having changed simultaneously throughout the world, it must not be supposed that this expression relates to the same 1000th or 100,000th year, or even that it has a very strict geological sense, for if all the marine animals which live at the present day in Europe, and all those that lived in Europe during the Pleistocene period, an enormously remote period as measured by years, including the whole glacial epoch, were to be compared with those now living in South America or in Australia, the most skillful naturalist would hardly be able to say whether the existing or the Pleistocene inhabitants of Europe resembled most closely those of the southern hemisphere. So, again, several highly competent observers believe that the existing productions of the United States are more closely related to those which lived in Europe during certain later tertiary stages than to those which now live here, and if this be so, it is evident that fossiliferous beds deposited at the present day on the shores of North America would hereafter be liable to be classed with somewhat older European beds. Nevertheless, looking to a remotely future epoch, there can, I think, be little doubt that all the more modern marine formations, namely, the Upper Pliocene, the Pleistocene and strictly modern beds of Europe, North and South America, and Australia, from containing fossil remains in some degree allied, and from not including those forms which are only found in the older underlying deposits, would be correctly ranked as simultaneous in a geological sense. The fact of the forms of life changing simultaneously, in the above large sense, at distant parts of the world, has greatly struck those admirable observers, M. de Verneuil and D. Archiac. After referring to the parallelism of the Paleozoic forms of life in various parts of Europe, they add, if struck by this strange sequence, we turn our attention to North America, and there discover a series of analogous phenomena, it will appear certain that all these modifications of species, their extinction, and the introduction of new ones, cannot be owing to mere changes in marine currents or other causes more or less local and temporary, but depend on general laws which govern the whole animal kingdom. M. Barrand has made forcible remarks to precisely the same effect. It is, indeed, quite futile to look to changes of currents, climate, or other physical conditions, as the cause of these great mutations in the forms of life throughout the world, under the most different climates. We must, as Barrand has remarked, look to some special law. We shall see this more clearly when we treat of the present distribution of organic beings, and find how slight is the relation between the physical conditions of various countries and the nature of their inhabitants. This great fact of the parallel succession of the forms of life throughout the world is explicable on the theory of natural selection. New species are formed by new varieties arising, which have some advantage over older forms, and those forms, which are already dominant, or have some advantage over the other forms in their own country, would naturally oftenest give rise to new varieties or incipient species, for these latter must be victorious in a still higher degree in order to be preserved and to survive. We have distinct evidence on this head, in the plants which are dominant, that is, which are commonest in their own homes, and are most widely diffused, having produced the greatest number of new varieties. It is also natural that the dominant, varying, and far-spreading species, which already have invaded to a certain extent the territories of other species, should be those which would have the best chance of spreading still further, and of giving rise in new countries to new varieties and species. The process of diffusion may often be very slow, being dependent on climatal and geographical changes, or on strange accidents, but in the long run the dominant forms will generally succeed in spreading. The diffusion would, it is probable, be slower with the terrestrial inhabitants of distinct continents than with the marine inhabitants of the continuous sea. We might therefore expect to find, as we apparently do find, a less strict degree of parallel succession in the productions of the land than of the sea. Dominant species spreading from any region might encounter still more dominant species, and then their triumphant course, or even their existence, would cease. We know not at all precisely what are all the conditions most favorable for the multiplication of new and dominant species, but we can, I think, clearly see that a number of individuals, from giving a better chance of the appearance of favorable variations, and that severe competition with many already existing forms, would be highly favorable, as would be the power of spreading into new territories. A certain amount of isolation, recurring at long intervals of time, would probably be also favorable, as before explained. 1/4 of the world may have been most favorable for the production of new and dominant species on the land, and another for those in the waters of the sea. If two great regions had been for a long period favorably circumstanced in an equal degree, whenever their inhabitants met, the battle would be prolonged and severe, and some from one birthplace and some from the other might be victorious. But in the course of time, the forms dominant in the highest degree, wherever produced, would tend everywhere to prevail. As they prevailed, they would cause the extinction of other and inferior forms, and as these inferior forms would be allied in groups by inheritance, whole groups would tend slowly to disappear, though here and there a single member might long be enabled to survive. Thus, as it seems to me, the parallel, and, taken in a large sense, simultaneous, succession of the same forms of life throughout the world, accords well with the principle of new species having been formed by dominant species spreading widely and varying, the new species thus produced being themselves dominant owing to inheritance, and to having already had some advantage over their parents or over other species, these again spreading, varying, and producing new species. The forms which are beaten and which yield their places to the new and victorious forms, will generally be allied in groups, from inheriting some inferiority in common, and therefore as new and improved groups spread throughout the world, old groups will disappear from the world, and the succession of forms in both ways will everywhere tend to correspond. There is one other remark connected with this subject worth making. I have given my reasons for believing that all our greater fossiliferous formations were deposited during periods of subsidence, and that blank intervals of vast duration occurred during the periods when the bed of the sea was either stationary or rising, and likewise when sediment was not thrown down quickly enough to embed and preserve organic remains. During these long and blank intervals I suppose that the inhabitants of each region underwent a considerable amount of modification and extinction, and that there was much migration from other parts of the world. As we have reason to believe that large areas are affected by the same movement, it is probable that strictly contemporaneous formations have often been accumulated over very wide spaces in the same quarter of the world, but we are far from having any right to conclude that this has invariably been the case, and that large areas have invariably been affected by the same movements. When two formations have been deposited in two regions during nearly, but not exactly the same period, we should find in both, from the causes explained in the foregoing paragraphs, the same general succession in the forms of life, but the species would not exactly correspond, for there will have been a little more time in the one region than in the other for modification, extinction, and immigration. I suspect that cases of this nature have occurred in Europe. Mr. Prestwich, in his admirable memoirs on the Eocene deposits of England and France, is able to draw a close general parallelism between the successive stages in the two countries, but when he compares certain stages in England with those in France, although he finds in both a curious accordance in the numbers of the species belonging to the same genera, yet the species themselves differ in a manner very difficult to account for, considering the proximity of the two areas, unless, indeed, it be assumed that an isthmus separated two seas inhabited by distinct, but contemporaneous, faunas. Lyell has made similar observations on some of the later tertiary formations. Barrand, also, shows that there is a striking general parallelism in the successive Silurian deposits of Bohemia and Scandinavia, nevertheless he finds a surprising amount of difference in the species. If the several formations in these regions have not been deposited during the same exact periods, a formation in one region often corresponding with a blank interval in the other, and if in both regions the species have gone on slowly changing during the accumulation of the several formations and during the long intervals of time between them, in this case, the several formations in the two regions could be arranged in the same order, in accordance with the general succession of the form of life, and the order would falsely appear to be strictly parallel. Nevertheless, the species would not all be the same in the apparently corresponding stages in the two regions. On the affinities of extinct species to each other, and to living forms. Let us now look to the mutual affinities of extinct and living species. They all fall into one grand natural system, and this fact is at once explained on the principle of descent. The more ancient any form is, the more, as a general rule, it differs from living forms. But as Backland long ago remarked, all fossils can be classed either in still existing groups, or between them. That the extinct forms of life help to fill up the wide intervals between existing genera, families, and orders, cannot be disputed. For if we confine our attention either to the living or to the extinct alone, the series is far less perfect than if we combine both into one general system. With respect to the vertebrata, whole pages could be filled with striking illustrations from our great paleontologist, Owen, showing how extinct animals fall in between existing groups. Cuvier ranked the ruminants and pachyderms as the two most distinct orders of mammals, but Owen has discovered so many fossil links that he has had to alter the whole classification of these two orders, and has placed certain pachyderms in the same suborder with ruminants. For example, he dissolves by fine gradations the apparently wide difference between the pig and the camel. In regard to the invertebrata, Barrand, and a higher authority could not be named, asserts that he is every day taught that Paleozoic animals, though belonging to the same orders, families, or genera with those living at the present day, were not at this early epoch limited in such distinct groups as they now are. Some writers have objected to any extinct species or group of species being considered as intermediate between living species or groups. If by this term it is meant that an extinct form is directly intermediate in all its characters between two living forms, the objection is probably valid. But I apprehend that in a perfectly natural classification many fossil species would have to stand between living species, and some extinct genera between living genera, even between genera belonging to distinct families. The most common case, especially with respect to very distinct groups, such as fish and reptiles, seems to be that supposing them to be distinguished at the present day from each other by a dozen characters, the ancient members of the same two groups would be distinguished by a somewhat lesser number of characters, so that the two groups, though formerly quite distinct, at that period made some small approach to each other. It is a common belief that the more ancient a form is, by so much the more it tends to connect by some of its characters groups now widely separated from each other. This remark no doubt must be restricted to those groups which have undergone much change in the course of geological ages, and it would be difficult to prove the truth of the proposition, for every now and then even a living animal, as the lepidosiren, is discovered having affinities directed towards very distinct groups. Yet if we compare the older reptiles and batrachians, the older fish, the older cephalopods, and the Eocene mammals, with the more recent members of the same classes, we must admit that there is some truth in the remark. Let us see how far these several facts and inferences accord with the theory of descent with modification. As the subject is somewhat complex, I must request the reader to turn to the diagram in the 4th chapter. We may suppose that the numbered letters represent genera, and the dotted lines diverging from them the species in each genus. The diagram is much too simple, too few genera and too few species being given, but this is unimportant for us. The horizontal lines may represent successive geological formations, and all the forms beneath the uppermost line may be considered as extinct. The three existing genera, A14, Q14, P14, will form a small family, B14 and F14 a closely allied family or subfamily, and O14, E14, M14, a third family. These three families, together with the many extinct genera on the several lines of descent diverging from the parent form A, will form an order, for all will have inherited something in common from their ancient and common progenitor. On the principle of the continued tendency to divergence of character, which was formerly illustrated by this diagram, the more recent any form is, the more it will generally differ from its ancient progenitor. Hence we can understand the rule that the most ancient fossils differ most from existing forms. We must not, however, assume that divergence of character is a necessary contingency. It depends solely on the descendants from a species being thus enabled to seize on many and different places in the economy of nature. Therefore it is quite possible, as we have seen in the case of some Silurian forms, that a species might go on being slightly modified in relation to its slightly altered conditions of life, and yet retain throughout a vast period the same general characteristics. This is represented in the diagram by the letter F14. All the many forms, extinct and recent, descended from A, make, as before remarked, one order, and this order, from the continued effects of extinction and divergence of character, has become divided into several subfamilies and families, some of which are supposed to have perished at different periods, and some to have endured to the present day. By looking at the diagram we can see that if many of the extinct forms, supposed to be embedded in the successive formations, were discovered at several points low down in the series, the three existing families on the uppermost line would be rendered less distinct from each other. If, for instance, the genera A1, A5, A10, F8, M3, M6, M9 were disinterred, these three families would be so closely linked together that they probably would have to be united into one great family, in nearly the same manner as has occurred with ruminants and pachyderms. Yet he who objected to call the extinct genera, which thus linked the living genera of three families together, intermediate in character, would be justified, as they are intermediate, not directly, but only by a long and circuitous course through many widely different forms. If many extinct forms were to be discovered above one of the middle horizontal lines or geological formations, for instance, above number 6. But none from beneath this line, then only the two families on the left hand, namely, A14, etc., and B14, etc., would have to be united into one family, and the two other families, namely, A14 to F14 now including 5 genera, and O14 to M14, would yet remain distinct. These two families, however, would be less distinct from each other than they were before the discovery of the fossils. If, for instance, we suppose the existing genera of the two families to differ from each other by a dozen characters, in this case the genera, at the early period marked 6, would differ by a lesser number of characters, for at this early stage of descent they have not diverged in character from the common progenitor of the order, nearly so much as they subsequently diverged. Thus it comes that ancient and extinct genera are often in some slight degree intermediate in character between their modified descendants, or between their collateral relations. In nature the case will be far more complicated than is represented in the diagram, for the groups will have been more numerous, they will have endured for extremely unequal lengths of time, and will have been modified in various degrees. As we possess only the last volume of the geological record, and that in a very broken condition, we have no right to expect, except in very rare cases, to fill up wide intervals in the natural system, and thus unite distinct families or orders. All that we have a right to expect is that those groups, which have within known geological periods undergone much modification, should in the older formations make some slight approach to each other, so that the older members should differ less from each other in some of their characters than do the existing members of the same groups, and this by the concurrent evidence of our best paleontologists seems frequently to be the case. Thus, on the theory of descent with modification, the main facts with respect to the mutual affinities of the extinct forms of life to each other and to living forms, seem to me explained in a satisfactory manner. And they are wholly inexplicable on any other view. On this same theory, it is evident that the fauna of any great period in the Earth's history will be intermediate in general character between that which preceded and that which succeeded it. Thus, the species which lived at the 6th great stage of descent in the diagram are the modified offspring of those which lived at the 5th stage, and are the parents of those which became still more modified at the 7th stage, hence they could hardly fail to be nearly intermediate in character between the forms of life above and below. We must, however, allow for the entire extinction of some preceding forms, and for the coming in of quite new forms by immigration, and for a large amount of modification, during the long and blank intervals between the successive formations. Subject to these allowances, the fauna of each geological period undoubtedly is intermediate in character between the preceding and succeeding faunas. I need give only one instance, namely, the manner in which the fossils of the Devonian system, when this system was first discovered, were at once recognized by paleontologists as intermediate in character between those of the overlying Carboniferous and underlying Silurian system. But each fauna is not necessarily exactly intermediate, as unequal intervals of time have elapsed between consecutive formations. It is no real objection to the truth of the statement that the fauna of each period as a whole is nearly intermediate in character between the preceding and succeeding faunas, that certain genera offer exceptions to the rule. For instance, mastodons and elephants, when arranged by Dr. Falconer in 2 series, first according to their mutual affinities and then according to their periods of existence, do not accord in arrangement. The species extreme in character are not the oldest, or the most recent, nor are those which are intermediate in character, intermediate in age. But supposing for an instant, in this and other such cases, that the record of the first appearance and disappearance of the species was perfect, we have no reason to believe that forms successively produced necessarily endure for corresponding lengths of time. A very ancient form might occasionally last much longer than a form elsewhere subsequently produced, especially in the case of terrestrial productions inhabiting separated districts. To compare small things with great, if the principal living and extinct races of the domestic pigeon were arranged as well as they could be in serial affinity, this arrangement would not closely accord with the order in time of their production, and still less with the order of their disappearance, for the parent rock pigeon now lives, and many varieties between the rock pigeon and the carrier have become extinct, and carriers which are extreme in the important character of length of beak. originated earlier than short-beak tumblers, which are at the opposite end of the series in this same respect. Closely connected with the statement that the organic remains from an intermediate formation are in some degree intermediate in character is the fact, insisted on by all paleontologists, that fossils from two consecutive formations are far more closely related to each other than are the fossils from two remote formations. Pictet gives as a well-known instance the general resemblance of the organic remains from the several stages of the chalk formation, though the species are distinct in each stage. This fact alone, from its generality, seems to have shaken Professor Pictet in his firm belief in the immutability of species. He who is acquainted with the distribution of existing species over the globe will not attempt to account for the close resemblance of the distinct species in closely consecutive formations by the physical conditions of the ancient areas having remained nearly the same. Let it be remembered that the forms of life, at least those inhabiting the sea, have changed almost simultaneously throughout the world, and therefore under the most different climates and conditions. Consider the prodigious vicissitudes of climate during the Pleistocene period, which includes the whole glacial period, and note how little the specific forms of the inhabitants of the sea have been affected. On the theory of descent, the full meaning of the fact of fossil remains from closely consecutive formations, though ranked as distinct species, being closely related, is obvious. As the accumulation of each formation has often been interrupted, and as long blank intervals have intervened between successive formations, we ought not to expect to find, as I attempted to show in the last chapter, in any one or two formations all the intermediate varieties between the species which appeared at the commencement and close of these periods, but we ought to find after intervals, very long as measured by years, but only moderately long as measured geologically, closely allied forms, or, as they have been called by some authors, representative species, and these we assuredly do find. We find, in short, such evidence of the slow and scarcely sensible mutation of specific forms as we have a just right to expect to find. On the state of development of ancient forms. There has been much discussion whether recent forms are more highly developed than ancient. I will not here enter on this subject, for naturalists have not as yet defined to each other's satisfaction what is meant by high and low forms. But in one particular sense the more recent forms must, on my theory, be higher than the more ancient, for each new species is formed by having had some advantage in the struggle for life over other and preceding forms. If under a nearly similar climate, the Eocene inhabitants of one quarter of the world were put into competition with the existing inhabitants of the same or some other quarter, the Eocene fauna or flora would certainly be beaten and exterminated, as would a secondary fauna by an Eocene, and a Paleozoic fauna by a secondary fauna. I do not doubt that this process of improvement has affected in a marked and sensible manner the organization of the more recent and victorious forms of life, in comparison with the ancient and beaten forms, but I can see no way of testing this sort of progress. Crustaceans, for instance, not the highest in their own class, may have beaten the highest mollusks. From the extraordinary manner in which European productions have recently spread over New Zealand, and have seized on places which must have been previously occupied, we may believe, if all the animals and plants of Great Britain were set free in New Zealand, that in the course of time a multitude of British forms would become thoroughly naturalized there, and would exterminate many of the natives. On the other hand, from what we see now occurring in New Zealand, and from hardly a single inhabitant of the southern hemisphere having become wild in any part of Europe, we may doubt, if all the productions of New Zealand were set free in Great Britain, whether any considerable number would be enabled to seize on places now occupied by our native plants and animals. Under this point of view, the productions of Great Britain may be said to be higher than those of New Zealand. Yet the most skillful naturalist from an examination of the species of the two countries could not have foreseen this result. Agassiz insists that ancient animals resemble to a certain extent the embryos of recent animals of the same classes, or that the geological succession of extinct forms is in some degree parallel to the embryological development of recent forms. I must follow Pictet and Huxley in thinking that the truth of this doctrine is very far from proved. Yet I fully expect to see it hereafter confirmed, at least in regard to subordinate groups, which have branched off from each other within comparatively recent times. For this doctrine of Agassiz accords well with the theory of natural selection. In a future chapter one shall attempt to show that the adult differs from its embryo, owing to variation supervening at a not early age, and being inherited at a corresponding age. This process, whilst it leaves the embryo almost unaltered, continually adds, in the course of successive generations, more and more difference to the adult. Thus the embryo comes to be left as a sort of picture, preserved by nature, of the ancient and less modified condition of each animal. This view may be true, and yet it may never be capable of full proof. Seeing, for instance, that the oldest known mammals, reptiles, and fish strictly belong to their own proper classes, though some of these old forms are in a slight degree less distinct from each other than other typical members of the same groups at the present day, it would be vain to look for animals having the common embryological character of the vertebrata, until beds far beneath the lowest Silurian strata are discovered, a discovery of which the chance is very small. On the succession of the same types within the same areas, during the later tertiary periods. Mr. Clift many years ago showed that the fossil mammals from the Australian caves were closely allied to the living marsupials of that continent. In South America, a similar relationship is manifest, even to an uneducated eye, in the gigantic pieces of armor like those of the armadillo, found in several parts of La Plata, and Professor Owen has shown in the most striking manner that most of the fossil mammals, buried there in such numbers, are related to South American types. This relationship is even more clearly seen in the wonderful collection of fossil bones made by M. Lund Clausen in the caves of Brazil. I was so much impressed with these facts that I strongly insisted, in 1839 and 1845, on this law of the succession of types, on this wonderful relationship in the same continent between the dead and the living. Professor Owen has subsequently extended the same generalization to the mammals of the Old World. We see the same law in this author's restorations of the extinct and gigantic birds of New Zealand. We see it also in the birds of the caves of Brazil. Mr. Woodward has shown that the same law holds good with seashells, but from the wide distribution of most genera of mollusks, it is not well displayed by them. Other cases could be added, as the relation between the extinct and living land shells of Madeira, and between the extinct and living brackish water shells of the Aralo-Caspian Sea. Now what does this remarkable law of the succession of the same types within the same areas mean? He would be a bold man, who after comparing the present climate of Australia and of parts of South America under the same latitude, would attempt to account, on the one hand, by dissimilar physical conditions for the dissimilarity of the inhabitants of these two continents, and, on the other hand, by similarity of conditions, for the uniformity of the same types in each during the later tertiary periods. Nor can it be pretended that it is an immutable law that marsupials should have been chiefly or solely produced in Australia, or that Edentata and other American types should have been solely produced in South America. For we know that Europe in ancient times was peopled by numerous marsupials, and I have shown in the publications above alluded to, that in America the law of distribution of terrestrial mammals was formerly different from what it now is. North America formerly partook strongly of the present character of the southern half of the continent, and the southern half was formerly more closely allied, than it is at present, to the northern half. In a similar manner we know from Falconer and Courtly's discoveries, that northern India was formerly more closely related in its mammals to Africa than it is at the present time. Analogous facts could be given in relation to the distribution of marine animals. On the theory of descent with modification, the great law of the long-enduring, but not immutable, succession of the same types within the same areas, is at once explained, for the inhabitants of each quarter of the world will obviously tend to leave in that quarter, during the next succeeding period of time, closely allied though in some degree modified descendants. If the inhabitants of one continent formerly differed greatly from those of another continent, so will their modified descendants still differ in nearly the same manner and degree. But after very long intervals of time and after great geographical changes, permitting much intermigration, the feebler will yield to the more dominant forms, and there will be nothing immutable in the laws of past and present distribution. It may be asked in ridicule, whether I suppose that the Megatherium and other allied huge monsters have left behind them in South America the sloth, armadillo, and anteater, as their degenerate descendants. This cannot for an instant be admitted. These huge animals have become wholly extinct, and have left no progeny. But in the caves of Brazil, there are many extinct species which are closely allied in size and in other characters to the species still living in South America, and some of these fossils may be the actual progenitors of living species. It must not be forgotten that, on my theory, all the species of the same genus have descended from some one species, so that if 6 genera, each having 8 species, be found in one geological formation, and in the next succeeding formation there be 6 other allied or representative genera with the same number of species, then we may conclude that only one species of each of the 6 older genera has left modified descendants, constituting the 6 new genera. The other 7 species of the old genera have all died out and have left no progeny. Or, which would probably be a far commoner case, 2 or 3 species of 2 or 3 alone of the 6 older genera will have been the parents of the 6 new genera, the other old species and the other whole genera having become utterly extinct. In failing orders, with the genera and species decreasing in numbers, as apparently is the case of the Edentator of South America, still fewer genera and species will have left modified blood descendants. Summary of the preceding and present chapters. I have attempted to show that the geological record is extremely imperfect, that only a small portion of the globe has been geologically explored with care, that only certain classes of organic beings have been largely preserved in a fossil state, that the number both of specimens and of species, preserved in our museums, is absolutely as nothing compared with the incalculable number of generations which must have passed away even during a single formation, that, owing to subsidence being necessary for the accumulation of fossiliferous deposits thick enough to resist future degradation, enormous intervals of time have elapsed between the successive formations, that there has probably been more extinction during the periods of subsidence, and more variation during the periods of elevation, and during the latter the record will have been least perfectly kept, that each single formation has not been continuously deposited, that the duration of each formation is, perhaps, short compared with the average duration of specific forms, that migration has played an important part in the first appearance of new forms in any one area and formation, that widely ranging species are those which have varied most, and have oftenest given rise to new species, and that varieties have at first often been local. All these causes taken conjointly must have tended to make the geological record extremely imperfect, and will to a large extent explain why we do not find interminable varieties, connecting together all the extinct and existing forms of life by the finest graduated steps. He who rejects these views on the nature of the geological record will rightly reject my whole theory. For he may ask in vain where are the numberless transitional links which must formerly have connected the closely allied or representative species, found in the several stages of the same great formation. He may disbelieve in the enormous intervals of time which have elapsed between our consecutive formations, he may overlook how important a part migration must have played, when the formations of any one great region alone, as that of Europe, are considered, he may urge the apparent, but often falsely apparent, sudden coming in of whole groups of species. He may ask where are the remains of those infinitely numerous organisms which must have existed long before the first bed of the Silurian system was deposited. I can answer this latter question only hypothetically, by saying that as far as we can see, where our oceans now extend they have for an enormous period extended, and where our oscillating continents now stand they have stood ever since the Silurian epoch, but that long before that period, the world may have presented a wholly different aspect, and that the older continents, formed of formations older than any known to us, may now all be in a metamorphosed condition, or may lie buried under the ocean. Passing from these difficulties, all the other great leading facts in paleontology seem to me simply to follow on the theory of descent with modification through natural selection. We can thus understand how it is that new species come in slowly and successively, how species of different classes do not necessarily change together, or at the same rate, or in the same degree, yet in the long run that all undergo modification to some extent. The extinction of old forms is the almost inevitable consequence of the production of new forms. We can understand why when a species has once disappeared it never reappears. Groups of species increase in numbers slowly, and endure for unequal periods of time, for the process of modification is necessarily slow, and depends on many complex contingencies. The dominant species of the larger dominant groups tend to leave many modified descendants, and thus new subgroups and groups are formed. As these are formed, the species of the less vigorous groups, from their inferiority inherited from a common progenitor, tend to become extinct together, and to leave no modified offspring on the face of the earth. But the utter extinction of a whole group of species may often be a very slow process, from the survival of a few descendants, lingering in protected and isolated situations. When a group has once wholly disappeared, it does not reappear, for the link of generation has been broken. We can understand how the spreading of the dominant forms of life, which are those that oftenest vary, will in the long run tend to people the world with allied, but modified, descendants, and these will generally succeed in taking the places of those groups of species which are their inferiors in the struggle for existence. Hence, after long intervals of time, the productions of the world will appear to have changed simultaneously. We can understand how it is that all the forms of life, ancient and recent, make together one grand system, for all are connected by generation. We can understand, from the continued tendency to divergence of character, why the more ancient a form is, the more it generally differs from those now living. Why ancient and extinct forms often tend to fill up gaps between existing forms, sometimes blending two groups previously classed as distinct into one, but more commonly only bringing them a little closer together. The more ancient a form is, the more often, apparently, it displays characters in some degree intermediate between groups now distinct, for the more ancient a form is, the more nearly it will be related to, and consequently resemble, the common progenitor of groups, since become widely divergent. Extinct forms are seldom directly intermediate between existing forms, but are intermediate only by a long and circuitous course through many extinct and very different forms. We can clearly see why the organic remains of closely consecutive formations are more closely allied to each other than are those of remote formations, for the forms are more closely linked together by generation. We can clearly see why the remains of an intermediate formation are intermediate in character. The inhabitants of each successive period in the world's history have beaten their predecessors in the race for life, and are, in so far, higher in the scale of nature, and this may account for that vague yet ill-defined sentiment, felt by many paleontologists, that organization on the whole has progressed. If it should hereafter be proved that ancient animals resemble to a certain extent the embryos of more recent animals of the same class, the fact will be intelligible. The succession of the same types of structure within the same areas during the later geological period ceases to be mysterious, and is simply explained by inheritance. If then the geological record be as imperfect as I believe it to be, and it may at least be asserted that the record cannot be proved to be much more perfect, the main objections to the theory of natural selection are greatly diminished or disappear. On the other hand, all the chief laws of paleontology plainly proclaim, as it seems to me, that species have been produced by ordinary generation, old forms having been supplanted by new and improved forms of life, produced by the laws of variation still acting round us, and preserved by natural selection. Chapter 11. Geographical distribution. Present distribution cannot be accounted for by differences in physical conditions. Importance of barriers. Affinity of the productions of the same continent. Centers of creation. Means of dispersal, by changes of climate and of the level of the land, and by occasional means. Dispersal during the glacial period coextensive with the world. In considering the distribution of organic beings over the face of the globe, the first great fact which strikes us is, that neither the similarity nor the dissimilarity of the inhabitants of various regions can be accounted for by their climatal and other physical conditions. Of late, almost every author who has studied the subject has come to this conclusion. The case of America alone would almost suffice to prove its truth, for if we exclude the northern parts where the circumpolar land is almost continuous, all authors agree that one of the most fundamental divisions in geographical distribution is that between the New and Old Worlds. Yet if we travel over the vast American continent, from the central parts of the United States to its extreme southern point, we meet with the most diversified conditions, the most humid districts, arid deserts, lofty mountains, grassy plains, forests, marshes, lakes, and great rivers, under almost every temperature. There is hardly a climate or condition in the Old World which cannot be paralleled in the New, at least as closely as the same species generally require, for it is a most rare case to find a group of organisms confined to any small spot, having conditions peculiar in only a slight degree. For instance, small areas in the Old World could be pointed out hotter than any in the New World. Yet these are not inhabited by a peculiar fauna or flora. Notwithstanding this parallelism in the conditions of the Old and New Worlds, how widely different are their living productions? In the Southern Hemisphere, if we compare large tracts of land in Australia, South Africa, and Western South America, between latitudes 25 degrees and 35 degrees, we shall find parts extremely similar in all their conditions, yet it would not be possible to point out three faunas and floras more utterly dissimilar. Or again we may compare the productions of South America south of lat. 35 degrees with those north of 25 degrees, which consequently inhabit a considerably different climate, and they will be found incomparably more closely related to each other than they are to the productions of Australia or Africa under nearly the same climate. Analogous facts could be given with respect to the inhabitants of the sea. A second great fact which strikes us in our general review is that barriers of any kind, or obstacles to free migration, are related in a close and important manner to the differences between the productions of various regions. We see this in the great difference of nearly all the terrestrial productions of the New and Old Worlds, excepting in the northern parts, where the land almost joins, and where, under a slightly different climate, there might have been free migration for the northern temperate forms, as there now is for the strictly Arctic productions. We see the same fact in the great difference between the inhabitants of Australia, Africa, and South America under the same latitude, for these countries are almost as much isolated from each other as is possible. On each continent, also, we see the same fact, for on the opposite sides of lofty and continuous mountain ranges, and of great deserts, and sometimes even of large rivers, we find different productions, though as mountain chains, deserts, etc., are not as impassable, or likely to have endured so long as the oceans separating continents, the differences are very inferior in degree to those characteristic of distinct continents. Turning to the sea, we find the same law. No two marine faunas are more distinct, with hardly a fish, shell, or crab in common, than those of the eastern and western shores of South and Central America, yet these great faunas are separated only by the narrow, but impassable, Isthmus of Panama. Westward of the shores of America, a wide space of open ocean extends, with not an island as a halting place for emigrants. Here we have a barrier of another kind, and as soon as this is passed we meet in the eastern islands of the Pacific, with another and totally distinct fauna. So that here three marine faunas range far northward and southward, in parallel lines not far from each other, under corresponding climates, but from being separated from each other by impassable barriers, either of land or open sea, they are wholly distinct. On the other hand, proceeding still further westward from the eastern islands of the tropical parts of the Pacific, we encounter no impassable barriers, and we have innumerable islands as halting places, until after traveling over a hemisphere we come to the shores of Africa, and over this vast space we meet with no well-defined and distinct marine faunas. Although hardly one shell, crab, or fish is common to the above-named three approximate faunas of Eastern and Western America and the Eastern Pacific Islands, yet many fish range from the Pacific into the Indian Ocean, and many shells are common to the eastern islands of the Pacific and the eastern shores of Africa, on almost exactly opposite meridians of longitude. A third great fact, partly included in the foregoing statements, is the affinity of the productions of the same continent or sea, though the species themselves are distinct at different points and stations. It is a law of the widest generality, and every continent offers innumerable instances. Nevertheless, the naturalist in traveling, for instance, from north to south never fails to be struck by the manner in which successive groups of beings, specifically distinct, yet clearly related, replace each other. He hears from closely allied, yet distinct kinds of birds, notes nearly similar, and sees their nests similarly constructed, but not quite alike, with eggs colored in nearly the same manner. The plains near the Straits of Magellan are inhabited by one species of rhea, American ostrich, and northward the plains of La Plata by another species of the same genus, and not by a true ostrich or emu, like those found in Africa and Australia under the same latitude. On these same plains of La Plata we see the agouti and bizcacha, animals having nearly the same habits as our hares and rabbits and belonging to the same order of rodents, but they plainly display an American type of structure. We ascend the lofty peaks of the Cordillera and we find an alpine species of bizcacha. We look to the waters, and we do not find the beaver or muskrat, but the coypu and capybara, rodents of the American type. Innumerable other instances could be given. If we look to the islands off the American shore, however much they may differ in geological structure, the inhabitants, though they may be all peculiar species, are essentially American. We may look back to past ages, as shown in the last chapter, and we find American types then prevalent on the American continent and in the American seas. We see in these facts some deep organic bond, prevailing throughout space and time, over the same areas of land and water, and independent of their physical conditions. The naturalist must feel little curiosity, who is not led to inquire what this bond is. This bond, on my theory, is simply inheritance, that cause which alone, as far as we positively know, produces organisms quite like, or, as we see in the case of varieties nearly like each other. The dissimilarity of the inhabitants of different regions may be attributed to modification through natural selection, and in a quite subordinate degree to the direct influence of different physical conditions. the degree of dissimilarity will depend on the migration of the more dominant forms of life from one region into another, having been effected with more or less ease, at periods more or less remote, on the nature and number of the former immigrants, and on their action and reaction, in their mutual struggles for life, the relation of organism to organism being, as I have already often remarked, the most important of all relations. Thus the high importance of barriers comes into play by checking migration, as does time for the slow process of modification through natural selection. Widely ranging species, abounding in individuals, which have already triumphed over many competitors in their own widely extended homes, will have the best chance of seizing on new places when they spread into new countries. In their new homes they will be exposed to new conditions, and will frequently undergo further modification and improvement, and thus they will become still further victorious, and will produce groups of modified descendants. On this principle of inheritance with modification, we can understand how it is that sections of genera, whole genera, and even families are confined to the same areas, as is so commonly and notoriously the case. I believe, as was remarked in the last chapter, in no law of necessary development. As the variability of each species is an independent property, and will be taken advantage of by natural selection only so far as it profits the individual in its complex struggle for life, so the degree of modification in different species will be no uniform quantity. If, for instance, a number of species, which stand in direct competition with each other, migrate in a body into a new and afterwards isolated country, they will be little liable to modification, for neither migration nor isolation in themselves can do anything. These principles come into play only by bringing organisms into new relations with each other, and in a lesser degree with the surrounding physical conditions. As we have seen in the last chapter that some forms have retained nearly the same character from an enormously remote geological period, so certain species have migrated over vast spaces and have not become greatly modified. On these views, it is obvious that the several species of the same genus, though inhabiting the most distant quarters of the world, must originally have proceeded from the same source, as they have descended from the same progenitor. In the case of those species, which have undergone during whole geological periods but little modification, there is not much difficulty in believing that they may have migrated from the same region, for during the vast geographical and climatal changes which will have supervened since ancient times, almost any amount of migration is possible. But in many other cases, in which we have reason to believe that the species of a genus have been produced within comparatively recent times, there is great difficulty on this head. It is also obvious that the individuals of the same species, though now inhabiting distant and isolated regions, must have proceeded from one spot, where their parents were first produced, for, as explained in the last chapter, it is incredible that individuals identically the same should ever have been produced through natural selection from parents specifically distinct. We are thus brought to the question which has been largely discussed by naturalists, namely, whether species have been created at one or more points of the Earth's surface. Undoubtedly there are very many cases of extreme difficulty in understanding how the same species could possibly have migrated from some one point to the several distant and isolated points where now found. Nevertheless, the simplicity of the view that each species was first produced within a single region captivates the mind. He who rejects it rejects the vera causa of ordinary generation with subsequent migration, and calls in the agency of a miracle. It is universally admitted that in most cases the area inhabited by a species is continuous, and when a plant or animal inhabits 2 points so distant from each other, or with an interval of such a nature that the space could not be easily passed over by migration, the fact is given as something remarkable and exceptional. The capacity of migrating across the sea is more distinctly limited in terrestrial mammals than perhaps in any other organic beings, and, accordingly, we find no inexplicable cases of the same mammal inhabiting distant points of the world. No geologist will feel any difficulty in such cases as Great Britain having been formerly united to Europe, and consequently possessing the same quadrupeds. But if the same species can be produced at 2 separate points, why do we not find a single mammal common to Europe and Australia or South America? The conditions of life are nearly the same, so that a multitude of European animals and plants have become naturalized in America and Australia, and some of the aboriginal plants are identically the same at these distant points of the northern and southern hemispheres? The answer, as I believe, is that mammals have not been able to migrate, whereas some plants, from their varied means of dispersal, have migrated across the vast and broken interspace. the great and striking influence which barriers of every kind have had on distribution, is intelligible only on the view that the great majority of species have been produced on one side alone, and have not been able to migrate to the other side. Some few families, many subfamilies, very many genera, and a still greater number of sections of genera are confined to a single region, and it has been observed by several naturalists that the most natural genera, or those genera in which the species are most closely related to each other, are generally local, or confined to one area. What a strange anomaly it would be, if, when coming one step lower in the series, to the individuals of the same species, a directly opposite rule prevailed, and species were not local, but had been produced in two or more distinct areas. Hence it seems to me, as it has to many other naturalists, that the view of each species having been produced in one area alone, and having subsequently migrated from that area as far as its powers of migration and subsistence under past and present conditions permitted, is the most probable. Undoubtedly many cases occur, in which we cannot explain how the same species could have passed from one point to the other. But the geographical and climatal changes, which have certainly occurred within recent geological times, must have interrupted or rendered discontinuous the formerly continuous range of many species. So that we are reduced to consider whether the exceptions to continuity of range are so numerous and of so grave a nature, that we ought to give up the belief, rendered probable by general considerations, that each species has been produced within one area, and has migrated thence as far as it could. It would be hopelessly tedious to discuss all the exceptional cases of the same species, now living at distant and separated points, nor do I for a moment pretend that any explanation could be offered of many such cases. But after some preliminary remarks, I will discuss a few of the most striking classes of facts, namely, the existence of the same species on the summits of distant mountain ranges, and at distant points in the Arctic and Antarctic regions, and secondly, in the following chapter, the wide distribution of freshwater productions, and thirdly, the occurrence of the same terrestrial species on islands and on the mainland, though separated by hundreds of miles of open sea. If the existence of the same species at distant and isolated points of the Earth's surface can in many instances be explained on the view of each species having migrated from a single birthplace, then, considering our ignorance with respect to former climatal and geographical changes and various occasional means of transport, the belief that this has been the universal law seems to me incomparably the safest. In discussing this subject, we shall be enabled at the same time to consider a point equally important for us, namely, whether the several distinct species of a genus, which on my theory have all descended from a common progenitor, can have migrated, undergoing modification during some part of their migration, from the area inhabited by their progenitor. If it can be shown to be almost invariably the case, that a region, of which most of its inhabitants are closely related to, or belong to the same genera with the species of a second region, has probably received at some former period immigrants from this other region, my theory will be strengthened, for we can clearly understand, on the principle of modification, why the inhabitants of a region should be related to those of another region, whence it has been stocked. A volcanic island, for instance, upheaved and formed at the distance of a few hundreds of miles from a continent, would probably receive from it in the course of time a few colonists, and their descendants, though modified, would still be plainly related by inheritance to the inhabitants of the continent. Cases of this nature are common, and are, as we shall hereafter more fully see, inexplicable on the theory of independent creation. This view of the relation of species in one region to those in another does not differ much, by substituting the word variety for species, from that lately advanced in an ingenious paper by Mr. Wallace, in which he concludes that every species has come into existence coincident both in space and time with a pre-existing closely allied species. And I now know from correspondence that this coincidence he attributes to generation with modification. The previous remarks on single and multiple centers of creation do not directly bear on another allied question, namely whether all the individuals of the same species have descended from a single pair, or single hermaphrodite, or whether, as some authors suppose, from many individuals simultaneously created. With those organic beings which never intercross, if such exist, the species, on my theory, must have descended from a succession of improved varieties, which will never have blended with other individuals or varieties, but will have supplanted each other, so that, at each successive stage of modification and improvement, all the individuals of each variety will have descended from a single parent. But in the majority of cases, namely, with all organisms which habitually unite for each birth, or which often intercross, I believe that during the slow process of modification the individuals of the species will have been kept nearly uniform by intercrossing, so that many individuals will have gone on simultaneously changing, and the whole amount of modification will not have been due, at each stage, to descent from a single parent. To illustrate what I mean, our English race horses differ slightly from the horses of every other breed, but they do not owe their difference and superiority to descent from any single pair, but to continued care in selecting and training many individuals during many generations. Before discussing the three classes of facts, which I have selected as presenting the greatest amount of difficulty on the theory of a single centers of creation, I must say a few words on the means of dispersal. Means of dispersal. Sir C. Ed Lyle and other authors have ably treated this subject. I can give here only the briefest abstract of the more important facts. Change of climate must have had a powerful influence on migration. A region when its climate was different may have been a high road for migration, but now be impassable. I shall, however, presently have to discuss this branch of the subject in some detail. Changes of level in the land must also have been highly influential. A narrow isthmus now separates two marine faunas. Submerge it, or let it formerly have been submerged, and the two faunas will now blend or may formerly have blended. Where the sea now extends, land may at a former period have connected islands or possibly even continents together, and thus have allowed terrestrial productions to pass from one to the other. No geologist will dispute that great mutations of level have occurred within the period of existing organisms. Edward Forbes insisted that all the islands in the Atlantic must recently have been connected with Europe or Africa, and Europe likewise with America. Other authors have thus hypothetically bridged over every ocean, and have united almost every island to some mainland. If indeed the arguments used by Forbes are to be trusted, it must be admitted that scarcely a single island exists which has not recently been united to some continent. This view cuts the Gordian knot of the dispersal of the same species to the most distant points, and removes many a difficulty, but to the best of my judgment we are not authorized in admitting such enormous geographical changes within the period of existing species. It seems to me that we have abundant evidence of great oscillations of level in our continents, but not of such vast changes in their position and extension, as to have united them within the recent period to each other and to the several intervening oceanic islands. I freely admit the former existence of many islands, now buried beneath the sea, which may have served as halting places for plants and for many animals during their migration. In the coral-producing ocean such sunken islands are now marked, as I believe, by rings of coral or atolls standing over them. Whenever it is fully admitted, as I believe it will some day be, that each species has proceeded from a single birthplace, and when in the course of time we know something definite about the means of distribution, we shall be enabled to speculate with security on the former extension of the land. But I do not believe that it will ever be proved that within the recent period continents which are now quite separate, have been continuously, or almost continuously, united with each other, and with the many existing oceanic islands. Several facts in distribution, such as the great difference in the marine faunas on the opposite sides of almost every continent, the close relation of the tertiary inhabitants of several lands and even seas to their present inhabitants, a certain degree of relation, as we shall hereafter see, between the distribution of mammals and the depth of the sea. These and other such facts seem to me opposed to the admission of such prodigious geographical revolutions within the recent period, as are necessitated on the view advanced by Forbes and admitted by his many followers. The nature and relative proportions of the inhabitants of oceanic islands likewise seem to me opposed to the belief of their former continuity with continents. Nor does their almost universally volcanic composition favor the admission that they are the wrecks of sunken continents. If they had originally existed as mountain ranges on the land, some at least of the islands would have been formed, like other mountain summits, of granite, metamorphic schists, old fossiliferous or other such rocks, instead of consisting of mere piles of volcanic matter. I must now say a few words on what are called accidental means, but which more properly might be called occasional means of distribution. I shall here confine myself to plants. In botanical works, this or that plant is stated to be ill-adapted for wide dissemination, but for transport across the sea, the greater or less facilities may be said to be almost wholly unknown. Until I tried, with Mr. Berkeley's aid, a few experiments, it was not even known how far seeds could resist the injurious action of seawater. To my surprise I found that out of 87 kinds, 64 germinated after an immersion of 28 days, and a few survived an immersion of 137 days. For convenience sake I chiefly tried small seeds, without the capsule or fruit, and as all of these sank in a few days, they could not be floated across wide spaces of the sea, whether or not they were injured by the salt water. Afterwards I tried some larger fruits, capsules, etc., and some of these floated for a long time. It is well known what a difference there is in the buoyancy of green and seasoned timber, and it occurred to me that floods might wash down plants or branches, and that these might be dried on the banks, and then by a fresh rise in the stream be washed into the sea. Hence I was led to dry stems and branches of 94 plants with ripe fruit, and to place them on sea water. The majority sank quickly, but some which whilst green floated for a very short time, when dried floated much longer. For instance, ripe hazelnuts sank immediately, but when dried, they floated for 90 days, and afterwards when planted they germinated. An asparagus plant with ripe berries floated for 23 days, when dried it floated for 85 days, and the seeds afterwards germinated. The ripe seeds of Helocyaedium sank in 2 days. When dried they floated for above 90 days, and afterwards germinated. Altogether out of the 94 dried plants, 18 floated for above 28 days, and some of the 18 floated for a very much longer period. So that as 60 for 87th seeds germinated after an immersion of 28 days, and as 18 94th plants with ripe fruit, but not all the same species as in the foregoing experiment, floated, after being dried, for above 28 days. As far as we may infer anything from these scanty facts, we may conclude that the seeds of 100 plants of any country might be floated by sea currents during 28 days, and would retain their power of germination. In Johnston's Physical Atlas, the average rate of the several Atlantic currents is 33 miles per diem, some currents running at the rate of 60 miles per diem. On this average, the seeds of 100 plants belonging to one country might be floated across 924 miles of sea to another country, and when stranded, if blown to a favorable spot by an inland gale, they would germinate. Subsequently to my experiments, M. Martins tried similar ones, but in a much better manner, for he placed the seeds in a box in the actual sea, so that they were alternately wet and exposed to the air like really floating plants. He tried 98 seeds, mostly different from mine, but he chose many large fruits and likewise seeds from plants which live near the sea, and this would have favored the average length of their flotation and of their resistance to the injurious action of the salt water. On the other hand, he did not previously dry the plants or branches with the fruit, and this, as we have seen, would have caused some of them to have floated much longer. The result was that 18/98 of his seeds floated for 42 days, and were then capable of germination. But I do not doubt that plants exposed to the waves would float for a less time than those protected from violent movement as in our experiments. Therefore it would perhaps be safer to assume that the seeds of about 10 to 100 plants of a flora, after having been dried, could be floated across a space of sea 900 miles in width, and would then germinate. The fact of the larger fruits often floating longer than the small is interesting, as plants with large seeds or fruit could hardly be transported by any other means, and Alf. De Candolle has shown that such plants generally have restricted ranges. But seeds may be occasionally transported in another manner. Drift timber is thrown up on most islands, even on those in the midst of the widest oceans, and the natives of the coral islands in the Pacific procure stones for their tools, solely from the roots of drifted trees, these stones being a valuable royal tax. I find on examination that when irregularly shaped stones are embedded in the roots of trees, small parcels of earth are very frequently enclosed in their interstices and behind them, so perfectly that not a particle could be washed away in the longest transport. Out of one small portion of earth thus completely enclosed by wood in an oak about 50 years old, 3 dicotyledonous plants germinated. I am certain of the accuracy of this observation. Again, I can show that the carcasses of birds, when floating on the sea, sometimes escape being immediately devoured, and seeds of many kinds in the crops of floating birds long retain their vitality. Peas and vetches, for instance, are killed by even a few days' immersion in seawater, but some taken out of the crop of a pigeon, which had floated on artificial salt water for 30 days, to my surprise nearly all germinated. Living birds can hardly fail to be highly effective agents in the transportation of seeds. I could give many facts showing how frequently birds of many kinds are blown by gales to vast distances across the ocean. We may, I think, safely assume that under such circumstances their rate of flight would often be 35 miles an hour, and some authors have given a far higher estimate. I have never seen an instance of nutritious seeds passing through the intestines of a bird, but hard seeds of fruit will pass uninjured through even the digestive organs of a turkey. In the course of 2 months, I picked up in my garden 12 kinds of seeds, out of the excrement of small birds, and these seemed perfect, and some of them, which I tried, germinated. But the following fact is more important: the crops of birds do not secrete gastric juice, and do not in the least injure, as I know by trial, the germination of seeds. Now, after a bird has found and devoured a large supply of food, it is positively asserted that all the grains do not pass into the gizzard for 12 or even 18 hours. A bird in this interval might easily be blown to the distance of 500 miles, and hawks are known to look out for tired birds, and the contents of their torn crops might thus readily get scattered. Mr. Brent informs me that a friend of his had to give up flying carrier pigeons from France to England, as the hawks on the English coast destroyed so many on their arrival. Some hawks and owls bolt their prey whole, and after an interval of from 12 to 20 hours, disgorge pellets, which, as I know from experiments made in the zoological gardens, include seeds capable of germination. Some seeds of the oat, wheat, millet, canary, hemp, clover, and beet germinated after having been from 12 to 21 hours in the stomachs of different birds of prey, and 2 seeds of beet grew after having been thus retained for 2 days and 14 hours. Freshwater fish, I find, eat seeds of many land and water plants. Fish are frequently devoured by birds, and thus the seeds might be transported from place to place. I forced many kinds of seeds into the stomachs of dead fish, and then gave their bodies to fishing eagles, storks, and pelicans. These birds, after an interval of many hours, either rejected the seeds in pellets or passed them in their excrement, and several of these seeds retained their power of germination. Certain seeds, however, were always killed by this process. Although the beaks and feet of birds are generally quite clean, I can show that earth sometimes adheres to them. In one instance I removed 22 grains of dry argillaceous earth from 1 foot of a partridge, and in this earth there was a pebble quite as large as the seed of a vetch. Thus seeds might occasionally be transported to great distances, for many facts could be given showing that soil almost everywhere is charged with seeds. Reflect for a moment on the millions of quails which annually cross the Mediterranean, and can we doubt that the earth adhering to their feet would sometimes include a few minute seeds? But I shall presently have to recur to this subject. As icebergs are known to be sometimes loaded with earth and stones, and have even carried brushwood, bones, and the nest of a land bird, I can hardly doubt that they must occasionally have transported seeds from one part to another of the Arctic and Antarctic regions, as suggested by Lyell, and during the glacial period from one part of the now temperate regions to another. In the Azores, from the large number of the species of plants common to Europe, in comparison with the plants of other oceanic islands nearer to the mainland, and, as remarked by Mr. H. C. Watson, from the somewhat northern character of the flora in comparison with the latitude, I suspected that these islands had been partly stocked by ice-borne seeds, during the glacial epoch. At my request Sir C. Lyell wrote to M. Hartung to inquire whether he had observed erratic boulders on these islands, and he answered that he had found large fragments of granite and other rocks, which do not occur in the archipelago. Hence we may safely infer that icebergs formerly landed their rocky burthens on the shores of these mid-ocean islands, and it is at least possible that they may have brought thither the seeds of northern plants. Considering that the several above means of transport, and that several other means, which without doubt remain to be discovered, have been in action year after year, for centuries and tens of thousands of years, it would I think be a marvelous fact if many plants had not thus become widely transported. These means of transport are sometimes called accidental, but this is not strictly correct. The currents of the sea are not accidental, nor is the direction of prevalent gales of wind. It should be observed that scarcely any means of transport would carry seeds for very great distances, for seeds do not retain their vitality when exposed for a great length of time to the action of seawater, nor could they be long carried in the crops or intestines of birds. These means, however, would suffice for occasional transport across tracts of sea some 100 miles in breadth, or from island to island, or from a continent to a neighboring island, but not from one distant continent to another. The floras of distant continents would not by such means become mingled in any great degree, but would remain as distinct as we now see them to be. The currents, from their course, would never bring seeds from North America to Britain, though they might and do bring seeds from the West Indies to our western shores, where, if not killed by so long an immersion in salt water, they could not endure our climate. Almost every year, 1 or 2 land birds are blown across the whole Atlantic Ocean, from North America to the western shores of Ireland and England, but seeds could be transported by these wanderers only by one means, namely, in dirt sticking to their feet, which is in itself a rare accident. Even in this case, how small would the chance be of a seed falling on favorable soil, and coming to maturity? But it would be a great error to argue that because a well-stocked island, like Great Britain, has not, as far as is known, and it would be very difficult to prove this, received within the last few centuries, through occasional means of transport, immigrants from Europe or any other continent, that a poorly stocked island, though standing more remote from the mainland, would not receive colonists by similar means. I do not doubt that out of 20 seeds or animals transported to an island, even if far less well-stocked than Britain, scarcely more than one would be so well fitted to its new home, as to become naturalized. But this, as it seems to me, is no valid argument against what would be effected by occasional means of transport, during the long lapse of geological time, whilst an island was being upheaved and formed, and before it had become fully stocked with inhabitants. On almost bare land, with few or no destructive insects or birds living there, nearly every seed, which chanced to arrive, would be sure to germinate and survive. Dispersal during the glacial period. The identity of many plants and animals, on mountain summits, separated from each other by hundreds of miles of lowlands, where the alpine species could not possibly exist, is one of the most striking cases known of the same species living at distant points, without the apparent possibility of their having migrated from one to the other. It is indeed a remarkable fact to see so many of the same plants living on the snowy regions of the Alps or Pyrenees, and in the extreme northern parts of Europe, but it is far more remarkable that the plants on the White Mountains, in the United States of America, are all the same with those of Labrador, and nearly all the same, as we hear from Asa Gray, with those on the loftiest mountains of Europe. Even as long ago as 1747, such facts led Gmelin to conclude that the same species must have been independently created at several distinct points, and we might have remained in this same belief, had not Agassiz and others called vivid attention to the glacial period, which, as we shall immediately see, affords a simple explanation of these facts. We have evidence of almost every conceivable kind, organic and inorganic, that within a very recent geological period, Central Europe and North America suffered under an Arctic climate. The ruins of a house burned by fire do not tell their tale more plainly than do the mountains of Scotland and Wales, with their scored flanks, polished surfaces, and perched boulders, of the icy streams with which their valleys were lately filled. So greatly has the climate of Europe changed, that in northern Italy, gigantic moraines, left by old glacier, are now clothed by the vine and maize. Throughout a large part of the United States, erratic boulders, and rocks scored by drifted icebergs and coast ice, plainly reveal a former cold period. The former influence of the glacial climate on the distribution of the inhabitants of Europe, as explained with remarkable clearness by Edward Forbes, is substantially as follows. But we shall follow the changes more readily, by supposing a new glacial period to come slowly on, and then pass away, as formerly occurred. As the cold came on, and as each more southern zone became fitted for Arctic beings and ill-fitted for their former more temperate inhabitants, the latter would be supplanted and Arctic productions would take their places. The inhabitants of the more temperate regions would at the same time travel southward, unless they were stopped by barriers, in which case they would perish. The mountains would become covered with snow and ice, and their former alpine inhabitants would descend to the plains. By the time that the cold had reached its maximum, we should have a uniform Arctic fauna and flora, covering the central parts of Europe, as far south as the Alps and Pyrenees, and even stretching into Spain. The now temperate regions of the United States would likewise be covered by Arctic plants and animals, and these would be nearly the same with those of Europe, for the present circumpolar inhabitants, which we suppose to have everywhere traveled southward, are remarkably uniform round the world. We may suppose that the glacial period came on a little earlier or later in North America than in Europe, so will the southern migration there have been a little earlier or later, but this will make no difference in the final result. As the warmth returned, the Arctic forms would retreat northward, closely followed up in their retreat by the productions of the more temperate regions. And as the snow melted from the bases of the mountains, the Arctic forms would seize on the cleared and thawed ground, always ascending higher and higher, as the warmth increased, whilst their brethren were pursuing their northern journey. Hence, when the warmth had fully returned, the same Arctic species, which had lately lived in a body together on the lowlands of the Old and New Worlds, would be left isolated on distant mountain summits, having been exterminated on all lesser heights and in the Arctic regions of both hemispheres. Thus we can understand the identity of many plants at points so immensely remote as on the mountains of the United States and of Europe. We can thus also understand the fact that the alpine plants of each mountain range are more especially related to the Arctic forms living due north or nearly due north of them, for the migration as the cold came on, and the remigration on the returning warmth, will generally have been due south and north. The alpine plants, for example, of Scotland, as remarked by Mr. H. Seath Watson, and those of the Pyrenees, as remarked by Raymond, are more especially allied to the plants of northern Scandinavia, those of the United States to Labrador, those of the mountains of Siberia to the Arctic regions of that country. These views, grounded as they are on the perfectly well ascertained occurrence of a former glacial period, seem to me to explain in so satisfactory a manner the present distribution of the alpine and Arctic productions of Europe and America, that when in other regions we find the same species on distant mountain summits, we may almost conclude without other evidence that a colder climate permitted their former migration across the low intervening tracts, since become too warm for their existence. If the climate, since the glacial period, has ever been in any degree warmer than at present, as some geologists in the United States believe to have been the case, chiefly from the distribution of the fossil Nathodon, then the Arctic and temperate productions will at a very late period have marched a little further north, and subsequently have retreated to their present homes. But I have met with no satisfactory evidence with respect to this intercalated slightly warmer period, since the glacial period. The Arctic forms, during their long southern migration and remigration northward, will have been exposed to nearly the same climate and, as is especially to be noticed, they will have kept in a body together, consequently their mutual relations will not have been much disturbed, and, in accordance with the principles inculcated in this volume, they will not have been liable to much modification. But with our alpine productions, left isolated from the moment of the returning warmth, first at the bases and ultimately on the summits of the mountains, the case will have been somewhat different, for it is not likely that all the same Arctic species will have been left on mountain ranges distant from each other, and have survived there ever since. They will, also, in all probability have become mingled with ancient alpine species, which must have existed on the mountains before the commencement of the glacial epoch, and which during its coldest period will have been temporarily driven down to the plains. They will, also, have been exposed to somewhat different climatal influences. Their mutual relations will thus have been in some degree disturbed, consequently they will have been liable to modification, and this we find has been the case, for if we compare the present alpine plants and animals of the several great European mountain ranges, though very many of the species are identically the same, some present varieties, some are ranked as doubtful forms, and some few are distinct yet closely allied or representative species. In illustrating what, as I believe, actually took place during the glacial period, I assumed that at its commencement the Arctic productions were as uniform round the polar regions as they are at the present day. But the foregoing remarks on distribution apply not only to strictly Arctic forms, but also to many subarctic and to some few northern temperate forms, for some of these are the same on the lower mountains and on the plains of North America and Europe, and it may be reasonably asked how I account for the necessary degree of uniformity of the subarctic and northern temperate forms round the world, at the commencement of the glacial period. At the present day, the subarctic and northern temperate productions of the Old and New Worlds are separated from each other by the Atlantic Ocean and by the extreme northern part of the Pacific. During the glacial period, when the inhabitants of the Old and New Worlds lived further southwards than at present, they must have been still more completely separated by wider spaces of ocean. I believe the above difficulty may be surmounted by looking to still earlier changes of climate of an opposite nature. We have good reason to believe that during the Newer Pliocene period, before the glacial epoch, and whilst the majority of the inhabitants of the world were specifically the same as now, the climate was warmer than at the present day. Hence we may suppose that the organisms now living under the climate of latitude 60 degrees, during the Pliocene period lived further north under the polar circle, in latitude 66 degrees 67 degree, and that the strictly Arctic productions then lived on the broken land still nearer to the pole. Now if we look at a globe, we shall see that under the polar circle there is almost continuous land from Western Europe, through Siberia, to Eastern America. And to this continuity of the circumpolar land, and to the consequent freedom for intermigration under a more favorable climate, I attribute the necessary amount of uniformity in the subarctic and northern temperate productions of the Old and New Worlds at a period anterior to the glacial epoch. Believing, from reasons before alluded to, that our continents have long remained in nearly the same relative position, though subjected to large, but partial oscillations of level, I am strongly inclined to extend the above view, and to infer that during some earlier and still warmer period, such as the older Pliocene period, a large number of the same plants and animals inhabited the almost continuous circumpolar land, and that these plants and animals, both in the Old and New Worlds, began slowly to migrate southwards as the climate became less warm, long before the commencement of the glacial period. We now see, as I believe, their descendants, mostly in a modified condition, in the central parts of Europe and the United States. On this view we can understand the relationship, with very little identity, between the productions of North America and Europe, a relationship which is most remarkable, considering the distance of the two areas, and their separation by the Atlantic Ocean. We can further understand the singular fact remarked on by several observers, that the productions of Europe and America during the later tertiary stages were more closely related to each other than they are at the present time, for during these warmer periods the northern parts of the Old and New Worlds will have been almost continuously united by land, serving as a bridge, since rendered impassable by cold, for the intermigration of their inhabitants. During the slowly decreasing warmth of the Pliocene period, as soon as the species in common, which inhabited the New and Old Worlds, migrated south of the polar circle, they must have been completely cut off from each other. This separation, as far as the more temperate productions are concerned, took place long ages ago. And as the plants and animals migrated southward, they will have become mingled in the one great region with the Native American productions, and have had to compete with them, and in the other great region, with those of the Old World. Consequently we have here everything favorable for much modification, for far more modification than with the alpine productions, left isolated, within a much more recent period, on the several mountain ranges and on the Arctic lands of the two worlds. Hence it has come, that when we compare the now living productions of the temperate regions of the New and Old Worlds, we find very few identical species, though Asa Gray has lately shown that more plants are identical than was formerly supposed, but we find in every great class many forms, which some naturalists rank as geographical races, and others as distinct species, and a host of closely allied or representative forms which are ranked by all naturalists as specifically distinct. As on the land, so in the waters of the sea, a slow southern migration of a marine fauna, which during the Pliocene or even a somewhat earlier period, was nearly uniform along the continuous shores of the polar circle, will account, on the theory of modification, for many closely allied forms now living in areas completely sundered. Thus, I think, we can understand the presence of many existing and tertiary representative forms on the eastern and western shores of temperate North America, and the still more striking case of many closely allied crustaceans, as described in Dana's admirable work, of some fish and other marine animals, in the Mediterranean and in the seas of Japan, areas now separated by a continent and by nearly a hemisphere of equatorial ocean. These cases of relationship, without identity, of the inhabitants of seas now disjoined, and likewise of the past and present inhabitants of the temperate lands of North America and Europe, are inexplicable on the theory of creation. We cannot say that they have been created alike, in correspondence with the nearly similar physical conditions of the areas, for if we compare, for instance, certain parts of South America with the southern continents of the Old World, we see countries closely corresponding in all their physical conditions, but with their inhabitants utterly dissimilar. But we must return to our more immediate subject, the glacial period. I am convinced that Forbes's view may be largely extended. In Europe we have the plainest evidence of the cold period, from the western shores of Britain to the Ural Range, and southward to the Pyrenees. We may infer, from the frozen mammals and nature of the mountain vegetation, that Siberia was similarly affected. Along the Himalaya, at points 900 miles apart, glacier have left the marks of their former low descent, and in Sikkim, Dr. Hooker saw maize growing on gigantic ancient moraines. South of the equator, we have some direct evidence of former glacial action in New Zealand, and the same plants, found on widely separated mountains in this island, tell the same story. If one account which has been published can be trusted, we have direct evidence of glacial action in the southeastern corner of Australia. Looking to America, in the northern half, ice-borne fragments of rock have been observed on the eastern side as far south as lat. 36 to 37 degrees, and on the shores of the Pacific, where the climate is now so different, as far south as lat. 46 degrees, erratic boulders have, also, been noticed on the Rocky Mountains. In the Cordillera of equatorial South America, glacier once extended far below their present level. In central Chile I was astonished at the structure of a vast mound of detritus, about 800 feet in height, crossing a valley of the Andes, and this I now feel convinced was a gigantic moraine, left far below any existing glacier. Further south on both sides of the continent, from lat. 41 degrees to the southernmost extremity, we have the clearest evidence of former glacial action, in huge boulders transported far from their parent source. We do not know that the glacial epoch was strictly simultaneous at these several far distant points on opposite sides of the world. But we have good evidence in almost every case that the epoch was included within the latest geological period. We have, also, excellent evidence that it endured for an enormous time, as measured by years, at each point. The cold may have come on, or have ceased, earlier at one point of the globe than at another, but seeing that it endured for long at each, and that it was contemporaneous in a geological sense, it seems to me probable that it was, during a part at least of the period, actually simultaneous throughout the world. Without some distinct evidence to the contrary, we may at least admit as probable that the glacial action was simultaneous on the eastern and western sides of North America, in the Cordillera under the equator and under the warmer temperate zones, and on both sides of the southern extremity of the continent. If this be admitted, it is difficult to avoid believing that the temperature of the whole world was at this period simultaneously cooler. But it would suffice for my purpose if the temperature was at the same time lower along certain broad belts of longitude. On this view of the whole world, or at least of broad longitudinal belts, having been simultaneously colder from pole to pole, much light can be thrown on the present distribution of identical and allied species. In America, Dr. Hooker has shown that between 40 and 50 of the flowering plants of Tierra del Fuego, forming no inconsiderable part of its scanty flora, are common to Europe, enormously remote as these 2 points are, and there are many closely allied species. On the lofty mountains of equatorial America a host of peculiar species belonging to European genera occur. On the highest mountains of Brazil, some few European genera were found by Gardner, which do not exist in the wide intervening hot countries. So on the Silla of Caracas the illustrious Humboldt long ago found species belonging to genera characteristic of the Cordillera. On the mountains of Abyssinia, several European forms and some few representatives of the peculiar flora of the Cape of Good Hope occur. At the Cape of Good Hope are very few European species, believed not to have been introduced by man, and on the mountains, some few representative European forms are found, which have not been discovered in the intertropical parts of Africa. On the Himalaya, and on the isolated mountain ranges of the peninsula of India, on the heights of Ceylon, and on the volcanic cones of Java, many plants occur, either identically the same or representing each other, and at the same time representing plants of Europe, not found in the intervening hot lowlands. A list of the genera collected on the loftier peaks of Java raises a picture of a collection made on a hill in Europe. Still more striking is the fact that southern Australian forms are clearly represented by plants growing on the summits of the mountains of Borneo. Some of these Australian forms, as I hear from Dr. Hooker, extend along the heights of the peninsula of Malacca, and are thinly scattered, on the one hand over India and on the other as far north as Japan. On the southern mountains of Australia, Dr. F. O. Muller has discovered several European species. Other species, not introduced by man, occur on the lowlands, and a long list can be given, as I am informed by Dr. Hooker, of European genera, found in Australia, but not in the intermediate torrid regions. In the admirable introduction to the flora of New Zealand, by Dr. Hooker, analogous and striking facts are given in regard to the plants of that large island. Hence we see that throughout the world, the plants growing on the more lofty mountains, and on the temperate lowlands of the northern and southern hemispheres, are sometimes identically the same, but they are much oftener specifically distinct, though related to each other in a most remarkable manner. This brief abstract applies to plants alone. Some strictly analogous facts could be given on the distribution of terrestrial animals. In marine productions, similar cases occur. As an example, I may quote a remark by the highest authority, Professor Dana, that it is certainly a wonderful fact that New Zealand should have a closer resemblance in its crustacea to Great Britain, its antipode, than to any other part of the world. Sir J. Richardson also speaks of the reappearance on the shores of New Zealand, Tasmania, etc., of northern forms of fish. Dr. Hooker informs me that 25 species of algae are common to New Zealand and to Europe, but have not been found in the intermediate tropical seas. It should be observed that the northern species and forms found in the southern parts of the southern hemisphere, and on the mountain ranges of the intertropical regions, are not Arctic, but belong to the northern temperate zones. As Mr. H.C. Watson has recently remarked, in receding from polar towards equatorial latitudes, the alpine or mountain floras really become less and less Arctic. Many of the forms living on the mountains of the warmer regions of the Earth and in the southern hemisphere are of doubtful value, being ranked by some naturalists as specifically distinct, by others as varieties, but some are certainly identical, and many, though closely related to northern forms, must be ranked as distinct species. Now let us see what light can be thrown on the foregoing facts, on the belief, supported as it is by a large body of geological evidence, that the whole world, or a large part of it, was during the glacial period simultaneously much colder than at present. The glacial period, as measured by years, must have been very long, and when we remember over what vast spaces some naturalized plants and animals have spread within a few centuries, this period will have been ample for any amount of migration. As the cold came slowly on, all the tropical plants and other productions will have retreated from both sides towards the equator, followed in the rear by the temperate productions, and these by the Arctic, but with the latter we are not now concerned. The tropical plants probably suffered much extinction, how much no one can say. Perhaps formerly the tropics supported as many species as we see at the present day crowded together at the Cape of Good Hope, and in parts of temperate Australia. As we know that many tropical plants and animals can withstand a considerable amount of cold, many might have escaped extermination during a moderate fall of temperature, more especially by escaping into the warmest spots. But the great fact to bear in mind is that all tropical productions will have suffered to a certain extent. On the other hand, the temperate productions, after migrating nearer to the equator, though they will have been placed under somewhat new conditions, will have suffered less. And it is certain that many temperate plants, if protected from the inroads of competitors, can withstand a much warmer climate than their own. Hence, it seems to me possible, bearing in mind that the tropical productions were in a suffering state and could not have presented a firm front against intruders, that a certain number of the more vigorous and dominant temperate forms might have penetrated the native ranks and have reached or even crossed the equator. The invasion would, of course, have been greatly favored by high land, and perhaps by a dry climate, for Dr. Falconer informs me that it is the damp with the heat of the tropics which is so destructive to perennial plants from a temperate climate. On the other hand, the most humid and hottest districts will have afforded an asylum to the tropical natives. The mountain ranges northwest of the Himalaya, and the long line of the Cordillera, seem to have afforded two great lines of invasion, and it is a striking fact, lately communicated to me by Dr. Hooker, that all the flowering plants, about 46 in number, common to Tierra del Fuego and to Europe still exist in North America, which must have lain on the line of march. But I do not doubt that some temperate productions entered and crossed even the lowlands of the tropics at the period when the cold was most intense, when Arctic forms had migrated some 25 degrees of latitude from their native country and covered the land at the foot of the Pyrenees. At this period of extreme cold, I believe that the climate under the equator at the level of the sea was about the same with that now felt there at the height of 6,000 or 7,000 feet. During this the coldest period, I suppose that large spaces of the tropical lowlands were clothed with a mingled tropical and temperate vegetation, like that now growing with strange luxuriance at the base of the Himalaya, as graphically described by Hooker. Thus, as I believe, a considerable number of plants, a few terrestrial animals, and some marine productions, migrated during the glacial period from the northern and southern temperate zones into the intertropical regions, and some even crossed the equator. As the warmth returned, these temperate forms would naturally ascend the higher mountains, being exterminated on the lowlands. Those which had not reached the equator would remigrate northward or southward towards their former homes, but the forms, chiefly northern, which had crossed the equator, would travel still further from their homes into the more temperate latitudes of the opposite hemisphere. Although we have reason to believe from geological evidence that the whole body of Arctic shells underwent scarcely any modification during their long southern migration and remigration northward, the case may have been wholly different with those intruding forms which settled themselves on the intertropical mountains and in the southern hemisphere. These being surrounded by strangers will have had to compete with many new forms of life, and it is probable that selected modifications in their structure, habits, and constitutions will have profited them. Thus many of these wanderers, though still plainly related by inheritance to their brethren of the northern or southern hemispheres, now exist in their new homes as well-marked varieties or as distinct species. It is a remarkable fact, strongly insisted on by Hooker in regard to America, and by Alf. de Candolle in regard to Australia, that many more identical plants and allied forms have apparently migrated from the north to the south, than in a reverse direction. We see, however, a few southern vegetable forms on the mountains of Borneo and Abyssinia. I suspect that this preponderant migration from north to south is due to the greater extent of land in the north, and to the northern forms having existed in their own homes in greater numbers, and having consequently been advanced through natural selection and competition to a higher stage of perfection or dominating power, than the southern forms. And thus, when they became commingled during the glacial period, the northern forms were enabled to beat the less powerful southern forms. Just in the same manner as we see at the present day, that very many European productions cover the ground in La Plata, and in a lesser degree in Australia, and have to a certain extent beaten the natives, whereas extremely few southern forms have become naturalized in any part of Europe, though hides, wool, and other objects likely to carry seeds have been largely imported into Europe during the last 2 or 3 centuries from La Plata, and during the last 30 or 40 years from Australia. Something of the same kind must have occurred on the intertropical mountains. No doubt before the glacial period they were stocked with endemic alpine forms, but these have almost everywhere largely yielded to the more dominant forms, generated in the larger areas and more efficient workshops of the north. In many islands the native productions are nearly equaled or even outnumbered by the naturalized, and if the natives have not been actually exterminated, their numbers have been greatly reduced, and this is the first stage towards extinction. A mountain is an island on the land, and the intertropical mountains before the glacial period must have been completely isolated, and I believe that the productions of these islands on the land yielded to those produced within the larger areas of the north, just in the same way as the productions of real islands have everywhere lately yielded to continental forms, naturalized by man's agency. I am far from supposing that all difficulties are removed on the view here given in regard to the range and affinities of the allied species which live in the northern and southern temperate zones and on the mountains of the intertropical regions. Very many difficulties remain to be solved. I do not pretend to indicate the exact lines and means of migration, or the reason why certain species and not others have migrated, why certain species have been modified and have given rise to new groups of forms, and others have remained unaltered. We cannot hope to explain such facts until we can say why one species and not another becomes naturalized by man's agency in a foreign land, why one ranges twice or thrice as far, and is twice or thrice as common, as another species within their own homes. I have said that many difficulties remain to be solved. Some of the most remarkable are stated with admirable clearness by Dr. Hooker in his botanical works on the Antarctic regions. These cannot be here discussed. I will only say that as far as regards the occurrence of identical species at points so enormously remote as Kerguelen Land, New Zealand, and Fuegia, I believe that towards the close of the glacial period, icebergs, as suggested by Lyell, have been largely concerned in their dispersal. But the existence of several quite distinct species, belonging to genera exclusively confined to the south, at these and other distant points of the southern hemisphere, is, on my theory of descent with modification, a far more remarkable case of difficulty. For some of these species are so distinct, that we cannot suppose that there has been time since the commencement of the glacial period for their migration, and for their subsequent modification to the necessary degree. The facts seem to me to indicate that peculiar and very distinct species have migrated in radiating lines from some common center, and I am inclined to look in the southern, as in the northern hemisphere, to a former and warmer period, before the commencement of the glacial period, when the Antarctic lands, now covered with ice, supported a highly peculiar and isolated flora. I suspect that before this flora was exterminated by the glacial epoch, a few forms were widely dispersed to various points of the southern hemisphere by occasional means of transport, and by the aid, as halting places, of existing and now sunken islands, and perhaps at the commencement of the glacial period, by icebergs. By these means, as I believe, the southern shores of America, Australia, New Zealand have become slightly tinted by the same peculiar forms of vegetable life. Sir C. Lyle in a striking passage has speculated, in language almost identical with mine, on the effects of great alternations of climate on geographical distribution. I believe that the world has recently felt one of his great cycles of change, and that on this view, combined with modification through natural selection, a multitude of facts in the present distribution both of the same and of allied forms of life can be explained. The living waters may be said to have flowed during one short period from the north and from the south, and to have crossed at the equator, but to have flowed with greater force from the north so as to have freely inundated the south. As the tide leaves its drift in horizontal lines, though rising higher on the shores where the tide rises highest, so have the living waters left their living drift on our mountain summits, in a line gently rising from the Arctic lowlands to a great height under the equator. The various beings thus left stranded may be compared with savage races of man, driven up and surviving in the mountain fastnesses of almost every land, which serve as a record, full of interest to us, of the former inhabitants of the surrounding lowlands. Chapter 12. Geographical distribution, continued. Distribution of freshwater productions. On the inhabitants of oceanic islands. Absence of batrachians and of terrestrial mammals. On the relation of the inhabitants of islands to those of the nearest mainland. On colonization from the nearest source with subsequent modification. Summary of the last and present chapters. As lakes and river systems are separated from each other by barriers of land, it might have been thought that freshwater productions would not have ranged widely within the same country, and as the sea is apparently a still more impassable barrier, that they never would have extended to distant countries. But the case is exactly the reverse. Not only have many freshwater species, belonging to quite different classes, an enormous range, but allied species prevail in a remarkable manner throughout the world. I well remember, when first collecting in the fresh waters of Brazil, feeling much surprise at the similarity of the freshwater insects, shells, etc., and at the dissimilarity of the surrounding terrestrial beings, compared with those of Britain. But this power in freshwater productions of ranging widely, though so unexpected, can, I think, in most cases be explained by their having become fitted, in a manner highly useful to them, for short and frequent migrations from pond to pond, or from stream to stream, and liability to wide dispersal would follow from this capacity as an almost necessary consequence. We can here consider only a few cases. In regard to fish, I believe that the same species never occur in the fresh waters of distant continents. But on the same continent the species often range widely and almost capriciously, for two river systems will have some fish in common and some different. A few facts seem to favor the possibility of their occasional transport by accidental means, like that of the live fish not rarely dropped by whirlwinds in India, and the vitality of their ova when removed from the water. But I am inclined to attribute the dispersal of freshwater fish mainly to slight changes within the recent period in the level of the land, having caused rivers to flow into each other. Instances, also, could be given of this having occurred during floods, without any change of level. We have evidence in the Lurs of the Rhine of considerable changes of level in the land within a very recent geological period, and when the surface was peopled by existing land and freshwater shells. The wide difference of the fish on opposite sides of continuous mountain ranges, which from an early period must have parted river systems and completely prevented their inosculation, seems to lead to this same conclusion. With respect to allied freshwater fish occurring at very distant points of the world, no doubt there are many cases which cannot at present be explained, but some freshwater fish belong to very ancient forms, and in such cases there will have been ample time for great geographical changes, and consequently time and means for much migration. In the second place, saltwater fish can with care be slowly accustomed to live in fresh water, and, according to Valencians, there is hardly a single group of fishes confined exclusively to fresh water, so that we may imagine that a marine member of a freshwater group might travel far along the shores of the sea, and subsequently become modified and adapted to the fresh waters of a distant land. Some species of freshwater shells have a very wide range, and allied species, which, on my theory, are descended from a common parent and must have proceeded from a single source, prevail throughout the world. Their distribution at first perplexed me much, as their ova are not likely to be transported by birds, and they are immediately killed by sea water, as are the adults. I could not even understand how some naturalized species have rapidly spread throughout the same country. But two facts, which I have observed, and no doubt many others remain to be observed, throw some light on this subject. When a duck suddenly emerges from a pond covered with duckweed, I have twice seen these little plants adhering to its back, and it has happened to me, in removing a little duckweed from one aquarium to another, that I have quite unintentionally stocked the one with freshwater shells from the other. But another agency is perhaps more effectual. I suspended a duck's feet, which might represent those of a bird sleeping in a natural pond, in an aquarium, where many ova of freshwater shells were hatching, and I found that numbers of the extremely minute and just hatched shells crawled on the feet, and clung to them so firmly that when taken out of the water they could not be jarred off, though at a somewhat more advanced age they would voluntarily drop off. These just hatched mollusks, though aquatic in their nature, survived on the duck's feet, in damp air, from 12 to 20 hours, and in this length of time a duck or heron might fly at least 600 or 700 miles, and would be sure to alight on a pool or rivulet, if blown across sea to an oceanic island or to any other distant point. Sir Charles Lyell also informs me that a Ditticus has been caught with an ancellus, a freshwater shell like a limpet, firmly adhering to it, and a water beetle of the same family, a carlimbetes, once flew on board the Beagle, when 45 miles distant from the nearest land. How much farther it might have flown with a favouring gale no one can tell. With respect to plants, it has long been known what enormous ranges many freshwater and even marsh species have, both over continents and to the most remote oceanic islands. This is strikingly shown, as remarked by Alf. De Candolle, in large groups of terrestrial plants, which have only a very few aquatic members, for these latter seem immediately to acquire, as if in consequence, a very wide range. I think favourable means of dispersal explain this fact. I have before mentioned that earth occasionally, though rarely, adheres in some quantity to the feet and beaks of birds. Wading birds, which frequent the muddy edges of ponds, if suddenly flushed, would be the most likely to have muddy feet. Birds of this order I can show are the greatest wanderers, and are occasionally found on the most remote and barren islands in the open ocean. They would not be likely to alight on the surface of the sea, so that the dirt would not be washed off their feet. When making land, they would be sure to fly to their natural freshwater haunts. I do not believe that botanists are aware how charged the mud of ponds is with seeds. I have tried several little experiments, but will here give only the most striking case. I took in February 3 tablespoonfuls of mud from 3 different points, beneath water, on the edge of a little pond. This mud when dry weighed only 6 3/4 ounces. I kept it covered up in my study for 6 months, pulling up and counting each plant as it grew. The plants were of many kinds, and were altogether 537 in number, and yet the viscid mud was all contained in a breakfast cup. Considering these facts, I think it would be an inexplicable circumstance if waterbirds did not transport the seeds of freshwater plants to vast distances, and if consequently the range of these plants was not very great. The same agency may have come into play with the eggs of some of the smaller freshwater animals. Other and unknown agencies probably have also played a part. I have stated that freshwater fish eat some kinds of seeds, though they reject many other kinds after having swallowed them. Even small fish swallow seeds of moderate size, as of the yellow water lily and potamogeton. Herons and other birds, century after century, have gone on daily devouring fish. They then take flight and go to other waters, or are blown across the sea, and we have seen that seeds retain their power of germination, when rejected in pellets or in excrement, many hours afterwards. When I saw the great size of the seeds of that fine water lily, the nelumbium, and remembered Alf. De Candolle's remarks on this plant, I thought that its distribution must remain quite inexplicable, but Audubon states that he found the seeds of the great southern water lily, probably, according to Dr. Hooker, the nelumbium luteum, in a heron's stomach. Although I do not know the fact, yet analogy makes me believe that a heron flying to another pond and getting a hearty meal of fish would probably reject from its stomach a pellet containing the seeds of the nelumbium undigested, or the seeds might be dropped by the bird whilst feeding its young, in the same way as fish are known sometimes to be dropped. In considering these several means of distribution, it should be remembered that when a pond or stream is first formed, for instance, on a rising islet, it will be unoccupied, and a single seed or egg will have a good chance of succeeding. Although there will always be a struggle for life between the individuals of the species, however few, already occupying any pond, yet as the number of kinds is small, compared with those on the land, the competition will probably be less severe between aquatic than between terrestrial species. Consequently, an intruder from the waters of a foreign country would have a better chance of seizing on a place than in the case of terrestrial colonists. We should, also, remember that some, perhaps many, freshwater productions are low in the scale of nature, and that we have reason to believe that such low beings change or become modified less quickly than the high, and this will give longer time than the average for the migration of the same aquatic species. We should not forget the probability of many species having formerly ranged as continuously as freshwater productions ever can range, over immense areas, and having subsequently become extinct in intermediate regions. But the wide distribution of freshwater plants and of the lower animals, whether retaining the same identical form or in some degree modified, I believe mainly depends on the wide dispersal of their seeds and eggs by animals, more especially by freshwater birds, which have large powers of flight, and naturally travel from one to another and often distant piece of water. Nature, like a careful gardener, thus takes her seeds from a bed of a particular nature, and drops them in another equally well fitted for them. On the inhabitants of oceanic islands. We now come to the last of the three classes of facts, which I have selected as presenting the greatest amount of difficulty, on the view that all the individuals both of the same and of allied species have descended from a single parent, and therefore have all proceeded from a common birthplace, notwithstanding that in the course of time they have come to inhabit distant points of the globe. I have already stated that I cannot honestly admit Forbes's view on continental extensions, which, if legitimately followed out, would lead to the belief that within the recent period all existing islands have been nearly or quite joined to some continent. This view would remove many difficulties, but it would not, I think, explain all the facts in regard to insular productions. In the following remarks I shall not confine myself to the mere question of dispersal, but shall consider some other facts, which bear on the truth of the two theories of independent creation and of descent with modification. The species of all kinds which inhabit oceanic islands are few in number compared with those on equal continental areas. Alf. De Candolle admits this for plants, and Wollaston for insects. If we look to the large size and varied stations of New Zealand, extending over 780 miles of latitude, and compare its flowering plants, only 750 in number, with those on an equal area at the Cape of Good Hope or in Australia, we must, I think, admit that something quite independently of any difference in physical conditions has caused so great a difference in number. Even the uniform county of Cambridge has 847 plants, and the little island of Anglesey 764, but a few ferns and a few introduced plants are included in these numbers, and the comparison in some other respects is not quite fair. We have evidence that the barren island of Ascension aboriginally possessed under half a dozen flowering plants, yet many have become naturalized on it, as they have on New Zealand and on every other oceanic island which can be named. In St. Helena there is reason to believe that the naturalized plants and animals have nearly or quite exterminated many native productions. He who admits the doctrine of the creation of each separate species will have to admit that a sufficient number of the best adapted plants and animals have not been created on oceanic islands, for man has unintentionally stocked them from various sources far more fully and perfectly than has nature. Although in oceanic islands the number of kinds of inhabitants is scanty, the proportion of endemic species, i.e. those found nowhere else in the world, is often extremely large. If we compare, for instance, the number of the endemic land shells in Madeira, or of the endemic birds in the Galapagos archipelago, with the number found on any continent, and then compare the area of the islands with that of the continent, we shall see that this is true. This fact might have been expected on my theory, for, as already explained, species occasionally arriving after long intervals in a new and isolated district, and having to compete with new associates, will be eminently liable to modification, and will often produce groups of modified descendants. But it by no means follows that, because in an island nearly all the species of one class are peculiar, those of another class, or of another section of the same class, are peculiar, and this difference seems to depend on the species which do not become modified having immigrated with facility and in a body, so that their mutual relations have not been much disturbed. Thus in the Galapagos Islands nearly every land bird, but only 2 out of the 11 marine birds, are peculiar, and it is obvious that marine birds could arrive at these islands more easily than land birds. Bermuda, on the other hand, which lies at about the same distance from North America as the Galapagos Islands do from South America, and which has a very peculiar soil, does not possess one endemic land bird, and we know from Mr. J.O.M. Jones's admirable account of Bermuda that very many North American birds, during their great annual migrations, visit either periodically or occasionally this island. Madeira does not possess one peculiar bird, and many European and African birds are almost every year blown there, as I am informed by Mr. E. V. Harcourt. So that these two islands of Bermuda and Madeira have been stocked by birds, which for long ages have struggled together in their former homes, and have become mutually adapted to each other, and when settled in their new homes, each kind will have been kept by the others to their proper places and habits, and will consequently have been little liable to modification. Madeira, again, is inhabited by a wonderful number of peculiar land shells, whereas not one species of seashell is confined to its shores. Now, though we do not know how seashells are dispersed, yet we can see that their eggs or larvae, perhaps attached to seaweed or floating timber, or to the feet of wading birds, might be transported far more easily than land shells, across 300 or 400 miles of open sea. The different orders of insects in Madeira apparently present analogous facts. Oceanic islands are sometimes deficient in certain classes, and their places are apparently occupied by the other inhabitants. In the Galapagos Islands, reptiles, and in New Zealand gigantic wingless birds, take the place of mammals. In the plants of the Galapagos Islands, Dr. Hooker has shown that the proportional numbers of the different orders are very different from what they are elsewhere. Such cases are generally accounted for by the physical conditions of the islands, but this explanation seems to me not a little doubtful. Facility of immigration, I believe, has been at least as important as the nature of the conditions. Many remarkable little facts could be given with respect to the inhabitants of remote islands. For instance, in certain islands not tenanted by mammals, some of the endemic plants have beautifully hooked seeds, yet few relations are more striking than the adaptation of hooked seeds for transportal by the wool and fur of quadrupeds. This case presents no difficulty on my view, for a hooked seed might be transported to an island by some other means, and the plant then becoming slightly modified, but still retaining its hooked seeds, would form an endemic species, having as useless an appendage as any rudimentary organ, for instance, as the shriveled wings under the sodded elytra of many insular beetles. Again, islands often possess trees or bushes belonging to orders which elsewhere include only herbaceous species, now trees, as Alf. De Candolle has shown, generally have, whatever the cause may be, confined ranges. Hence trees would be little likely to reach distant oceanic islands, and an herbaceous plant, though it would have no chance of successfully competing in stature with a fully developed tree, when established on an island and having to compete with herbaceous plants alone, might readily gain an advantage by growing taller and overtopping the other plants. If so, natural selection would often tend to add to the stature of herbaceous plants when growing on an island, to whatever order they belonged, and thus convert them first into bushes and ultimately into trees. With respect to the absence of whole orders on oceanic islands, Bory St. Vincent long ago remarked that batrachians, frogs, toads, newts, have never been found on any of the many islands with which the great oceans are studied. I have taken pains to verify this assertion, and I have found it strictly true. I have, however, been assured that a frog exists on the mountains of the great island of New Zealand, but I suspect that this exception, if the information be correct, may be explained through glacial agency. This general absence of frogs, toads, and newts on so many oceanic islands cannot be accounted for by their physical conditions. Indeed, it seems that islands are peculiarly well fitted for these animals, for frogs have been introduced into Madeira, the Azores, and Mauritius, and have multiplied so as to become a nuisance. But as these animals and their spawn are known to be immediately killed by seawater, on my view we can see that there would be great difficulty in their transportal across the sea, and therefore why they do not exist on any oceanic island. But why, on the theory of creation, they should not have been created there, it would be very difficult to explain. Mammals offer another and similar case. I have carefully searched the oldest voyages, but have not finished my search. As yet I have not found a single instance, free from doubt, of a terrestrial mammal, excluding domesticated animals kept by the natives, inhabiting an island situated above 300 miles from a continent or great continental island, and many islands situated at a much less distance are equally barren. The Falkland Islands, which are inhabited by a wolf-like fox, come nearest to an exception, but this group cannot be considered as oceanic, as it lies on a bank connected with the mainland. Moreover, icebergs formerly brought boulders to its western shores, and they may have formerly transported foxes, as so frequently now happens in the Arctic regions. Yet it cannot be said that small islands will not support small mammals, for they occur in many parts of the world on very small islands. if close to a continent, and hardly an island can be named on which our smaller quadrupeds have not become naturalized and greatly multiplied. It cannot be said, on the ordinary view of creation, that there has not been time for the creation of mammals. Many volcanic islands are sufficiently ancient, as shown by the stupendous degradation which they have suffered and by their tertiary strata. There has also been time for the production of endemic species belonging to other classes, and on continents it is thought that mammals appear and disappear at a quicker rate than other and lower animals. Though terrestrial mammals do not occur on oceanic islands, aerial mammals do occur on almost every island. New Zealand possesses 2 bats found nowhere else in the world: Norfolk Island, the VT Archipelago, the Bonin Islands, the Caroline and Marianne Archipelagos, and Mauritius, all possess their peculiar bats. Why, it may be asked, has the supposed creative force produced bats and no other mammals on remote islands? On my view, this question can easily be answered, for no terrestrial mammal can be transported across a wide space of sea, but bats can fly across. Bats have been seen wandering by day far over the Atlantic Ocean, and 2 North American species either regularly or occasionally visit Bermuda, at the distance of 600 miles from the mainland. I hear from Mr. Tomes, who has specially studied this family, that many of the same species have enormous ranges, and are found on continents and on far distant islands. Hence we have only to suppose that such wandering species have been modified through natural selection in their new homes in relation to their new position, and we can understand the presence of endemic bats on islands, with the absence of all terrestrial mammals. Besides the absence of terrestrial mammals in relation to the remoteness of islands from continents, there is also a relation, to a certain extent independent of distance, between the depth of the sea separating an island from the neighboring mainland, and the presence in both of the same mammiferous species or of allied species in a more or less modified condition. Mr. Windsor Earle has made some striking observations on this head in regard to the Great Malay Archipelago, which is traversed near Celebes by a space of deep ocean, and this space separates 2 widely distinct mammalian faunas. On either side the islands are situated on moderately deep submarine banks, and they are inhabited by closely allied or identical quadrupeds. No doubt some few anomalies occur in this great archipelago, and there is much difficulty in forming a judgment in some cases owing to the probable naturalization of certain mammals through man's agency, but we shall soon have much light thrown on the natural history of this archipelago by the admirable zeal and researches of Mr. Wallace. I have not as yet had time to follow up this subject in all other quarters of the world, but as far as I have gone, the relation generally holds good. We see Britain separated by a shallow channel from Europe, and the mammals are the same on both sides. We meet with analogous facts on many islands separated by similar channels from Australia. The West Indian Islands stand on a deeply submerged bank, nearly 1,000 fathoms in depth, and here we find American forms, but the species and even the genera are distinct. As the amount of modification in all cases depends to a certain degree on the lapse of time, and as during changes of level it is obvious that islands separated by shallow channels are more likely to have been continuously united within a recent period to the mainland than islands separated by deeper channels, we can understand the frequent relation between the depth of the sea and the degree of affinity of the mammalian inhabitants of islands with those of a neighboring continent, an inexplicable relation on the view of independent acts of creation. All the foregoing remarks on the inhabitants of oceanic islands, namely, the scarcity of kinds, the richness in endemic forms in particular classes or sections of classes, the absence of whole groups, as of batrachians, and of terrestrial mammals notwithstanding the presence of aerial bats, the singular proportions of certain orders of plants, herbaceous forms having been developed into trees, etc., seem to me to accord better with the view of occasional means of transport having been largely efficient in the long course of time, than with the view of all our oceanic islands having been formerly connected by continuous land with the nearest continent, for on this latter view the migration would probably have been more complete, and if modification be admitted, all the forms of life would have been more equally modified, in accordance with the paramount importance of the relation of organism to organism. I do not deny that there are many and grave difficulties in understanding how several of the inhabitants of the more remote islands, whether still retaining the same specific form or modified since their arrival, could have reached their present homes. But the probability of many islands having existed as halting places, of which not a wreck now remains, must not be overlooked. I will here give a single instance of one of the cases of difficulty. Almost all oceanic islands, even the most isolated and smallest, are inhabited by land shells, generally by endemic species, but sometimes by species found elsewhere. Dr. August A. Gould has given several interesting cases in regard to the land shells of the islands of the Pacific. Now it is notorious that land shells are very easily killed by salt. Their eggs, at least such as I have tried, sink in seawater and are killed by it. Yet there must be, on my view, some unknown, but highly efficient means for their transportal. Would the just hatched young occasionally crawl on and adhere to the feet of birds roosting on the ground, and thus get transported? It occurred to me that land shells, when hibernating and having a membranous diaphragm over the mouth of the shell, might be floated in chinks of drifted timber across moderately wide arms of the sea. And I found that several species did in this state withstand uninjured an immersion in seawater during 7 days. One of these shells was the Helix pomatia, and after it had again hibernated I put it in seawater for 20 days, and it perfectly recovered. As this species has a thick calcareous operculum, I removed it, and when it had formed a new membranous one, I immersed it for 14 days in seawater, and it recovered and crawled away, but more experiments are wanted on this head. The most striking and important fact for us in regard to the inhabitants of islands is their affinity to those of the nearest mainland, without being actually the same species. Numerous instances could be given of this fact. I will give only one, that of the Galapagos archipelago, situated under the equator, between 500 and 600 miles from the shores of South America. Here almost every product of the land and water bears the unmistakable stamp of the American continent. There are 26 land birds, and 25 of these are ranked by Mr. Gould as distinct species, supposed to have been created here, yet the close affinity of most of these birds to American species in every character, in their habits, gestures, and tones of voice, was manifest. So it is with the other animals, and with nearly all the plants, as shown by Dr. Hooker in his admirable memoir on the flora of this archipelago. The naturalist, looking at the inhabitants of these volcanic islands in the Pacific, distant several hundred miles from the continent, yet feels that he is standing on American land. Why should this be so? Why should the species which are supposed to have been created in the Galapagos archipelago, and nowhere else, bear so plain a stamp of affinity to those created in America? There is nothing in the conditions of life, in the geological nature of the islands, in their height or climate, or in the proportions in which the several classes are associated together, which resembles closely the conditions of the South American coast. In fact, there is a considerable dissimilarity in all these respects. On the other hand, there is a considerable degree of resemblance in the volcanic nature of the soil, in climate, height, and size of the islands, between the Galapagos and Cape de Verde archipelagos, but what an entire and absolute difference in their inhabitants. The inhabitants of the Cape de Verde Islands are related to those of Africa, like those of the Galapagos to America. I believe this grand fact can receive no sort of explanation on the ordinary view of independent creation, whereas on the view here maintained, it is obvious that the Galapagos Islands would be likely to receive colonists, whether by occasional means of transport or by formerly continuous land, from America, and the Cape de Verde Islands from Africa, and that such colonists would be liable to modification, the principle of inheritance still betraying their original birthplace. Many analogous facts could be given. Indeed, it is an almost universal rule that the endemic productions of islands are related to those of the nearest continent, or of other near islands. The exceptions are few, and most of them can be explained. Thus the plants of Kerguelen Land, though standing nearer to Africa than to America, are related, and that very closely, as we know from Dr. Hooker's account, to those of America, but on the view that this island has been mainly stocked by seeds brought with earth and stones on icebergs, drifted by the prevailing currents, this anomaly disappears. New Zealand in its endemic plants is much more closely related to Australia, the nearest mainland, than to any other region, and this is what might have been expected, but it is also plainly related to South America, which, although the next nearest continent, is so enormously remote, that the fact becomes an anomaly. But this difficulty almost disappears on the view that both New Zealand, South America, and other southern lands were long ago partially stocked from a nearly intermediate though distant point, namely from the Antarctic islands, when they were clothed with vegetation, before the commencement of the glacial period. The affinity, which, though feeble, I am assured by Dr. Hooker is real, between the flora of the southwestern corner of Australia and of the Cape of Good Hope, is a far more remarkable case, and is at present inexplicable. But this affinity is confined to the plants, and will, I do not doubt, be someday explained. The law which causes the inhabitants of an archipelago, though specifically distinct, to be closely allied to those of the nearest continent, we sometimes see displayed on a small scale, yet in a most interesting manner, within the limits of the same archipelago. Thus the several islands of the Galapagos archipelago are tenanted, as I have elsewhere shown, in a quite marvelous manner, by very closely related species, so that the inhabitants of each separate island, though mostly distinct, are related in an incomparably closer degree to each other than to the inhabitants of any other part of the world. And this is just what might have been expected on my view, for the islands are situated so near each other that they would almost certainly receive immigrants from the same original source, or from each other. But this dissimilarity between the endemic inhabitants of the islands may be used as an argument against my views, for it may be asked, how has it happened in the several islands situated within sight of each other, having the same geological nature, the same height, climate, etc., that many of the immigrants should have been differently modified, though only in a small degree? This long appeared to me a great difficulty, but it arises in chief part from the deeply seated error of considering the physical conditions of a country as the most important for its inhabitants, whereas it cannot, I think, be disputed that the nature of the other inhabitants, with which each has to compete, is at least as important, and generally a far more important element of success. Now if we look to those inhabitants of the Galapagos archipelago which are found in other parts of the world, laying on one side for the moment the endemic species, which cannot be here fairly included, as we are considering how they have come to be modified since their arrival, we find a considerable amount of difference in the several islands. This difference might indeed have been expected on the view of the islands having been stocked by occasional means of transport, a seed, for instance, of one plant having been brought to one island, and that of another plant to another island. Hence when in former times an immigrant settled on any one or more of the islands, or when it subsequently spread from one island to another, it would undoubtedly be exposed to different conditions of life in the different islands, for it would have to compete with different sets of organisms. A plant, for instance, would find the best fitted ground more perfectly occupied by distinct plants in one island than in another, and it would be exposed to the attacks of somewhat different enemies. If then it varied, natural selection would probably favor different varieties in the different islands. Some species, however, might spread and yet retain the same character throughout the group, just as we see on continents some species spreading widely and remaining the same. The really surprising fact in this case of the Galapagos archipelago, and in a lesser degree in some analogous instances, is that the new species formed in the separate islands have not quickly spread to the other islands. But the islands, though in sight of each other, are separated by deep arms of the sea, in most cases wider than the British Channel, and there is no reason to suppose that they have at any former period been continuously united. The currents of the sea are rapid and sweep across the archipelago, and gales of wind are extraordinarily rare, so that the islands are far more effectually separated from each other than they appear to be on a map. Nevertheless, a good many species, both those found in other parts of the world and those confined to the archipelago, are common to the several islands, and we may infer from certain facts that these have probably spread from some one island to the others. But we often take, I think, an erroneous view of the probability of closely allied species invading each other's territory when put into free intercommunication. Undoubtedly, if one species has any advantage whatever over another, it will in a very brief time wholly or in part supplant it, but if both are equally well fitted for their own places in nature, both probably will hold their own places and keep separate for almost any length of time. Being familiar with the fact that many species, naturalized through man's agency, have spread with astonishing rapidity over new countries, we are apt to infer that most species would thus spread, but we should remember that the forms which become naturalized in new countries are not generally closely allied to the aboriginal inhabitants, but are very distinct species, belonging in a large proportion of cases, as shown by Alf. de Candolle, to distinct genera. In the Galapagos archipelago, many even of the birds, though so well adapted for flying from island to island, are distinct on each. Thus there are 3 closely allied species of mocking thrush, each confined to its own island. Now let us suppose the mocking thrush of Chatham Island to be blown to Charles Island, which has its own mocking thrush. Why should it succeed in establishing itself there? We may safely infer that Charles Island is well stocked with its own species, for annually more eggs are laid there than can possibly be reared, and we may infer that the mocking thrush peculiar to Charles Island is at least as well fitted for its home as is the species peculiar to Chatham Island. Sir C. Lyle and Mr. Wollaston have communicated to me a remarkable fact bearing on this subject, namely, that Madeira and the adjoining islet of Porto Santo possess many distinct but representative land shells, some of which live in crevices of stone, and although large quantities of stone are annually transported from Porto Santo to Madeira, yet this latter island has not become colonized by the Porto Santo species. Nevertheless, both islands have been colonized by some European land shells, which no doubt had some advantage over the indigenous species. From these considerations, I think we need not greatly marvel at the endemic and representative species, which inhabit the several islands of the Galapagos archipelago, not having universally spread from island to island. In many other instances, as in the several districts of the same continent, preoccupation has probably played an important part in checking the commingling of species under the same conditions of life. Thus, the southeast and southwest corners of Australia have nearly the same physical conditions, and are united by continuous land, yet they are inhabited by a vast number of distinct mammals, birds, and plants. The principle which determines the general character of the fauna and flora of oceanic islands, namely, that the inhabitants, when not identically the same, yet are plainly related to the inhabitants of that region whence colonists could most readily have been derived, the colonists having been subsequently modified and better fitted to their new homes, is of the widest application throughout nature. We see this on every mountain, in every lake and marsh. For alpine species, excepting in so far as the same forms, chiefly of plants, have spread widely throughout the world during the recent glacial epoch, are related to those of the surrounding lowlands. Thus we have in South America, alpine hummingbirds, alpine rodents, alpine plants, etc., all of strictly American forms, and it is obvious that a mountain, as it became slowly upheaved, would naturally be colonized from the surrounding lowlands. So it is with the inhabitants of lakes and marshes, excepting in so far as great facility of transport has given the same general forms to the whole world. We see this same principle in the blind animals inhabiting the caves of America and of Europe. Other analogous facts could be given. And it will, I believe, be universally found to be true, that wherever in two regions, let them be ever so distant, many closely allied or representative species occur, there will likewise be found some identical species, showing, in accordance with the foregoing view, that at some former period there has been intercommunication or migration between the two regions. And wherever many closely allied species occur, there will be found many forms which some naturalists rank as distinct species, and some as varieties, these doubtful forms showing us the steps in the process of modification. This relation between the power and extent of migration of a species, either at the present time or at some former period under different physical conditions, and the existence at remote points of the world of other species allied to it, is shown in another and more general way. Mr. Gould remarked to me long ago, that in those genera of birds which range over the world, many of the species have very wide ranges. I can hardly doubt that this rule is generally true, though it would be difficult to prove it. Amongst mammals, we see it strikingly displayed in bats, and in a lesser degree in the Felidae and Canidae. We see it, if we compare the distribution of butterflies and beetles. So it is with most freshwater productions, in which so many genera range over the world, and many individual species have enormous ranges. It is not meant that in world-ranging genera all the species have a wide range, or even that they have on an average a wide range, but only that some of the species range very widely, for the facility with which widely ranging species vary and give rise to new forms will largely determine their average range. For instance, two varieties of the same species inhabit America and Europe, and the species thus has an immense range, but if the variation had been a little greater, the two varieties would have been ranked as distinct species, and the common range would have been greatly reduced. Still less is it meant that a species which apparently has the capacity of crossing barriers and ranging widely, as in the case of certain powerfully winged birds, will necessarily range widely, for we should never forget that to range widely implies not only the power of crossing barriers, but the more important power of being victorious in distant lands in the struggle for life with foreign associates. But on the view of all the species of a genus having descended from a single parent, though now distributed to the most remote points of the world, we ought to find, and I believe as a general rule we do find, that some at least of the species range very widely, for it is necessary that the unmodified parent should range widely, undergoing modification during its diffusion, and should place itself under diverse conditions favorable for the conversion of its offspring, firstly into new varieties, and ultimately into new species. In considering the wide distribution of certain genera, we should bear in mind that some are extremely ancient, and must have branched off from a common parent at a remote epoch, so that in such cases there will have been ample time for great climatal and geographical changes and for accidents of transport, and consequently for the migration of some of the species into all quarters of the world, where they may have become slightly modified in relation to their new conditions. There is, also, some reason to believe from geological evidence that organisms low in the scale within each great class generally change at a slower rate than the higher forms, and consequently the lower forms will have had a better chance of ranging widely and of still retaining the same specific character. This fact, together with the seeds and eggs of many low forms being very minute and better fitted for distant transportation, probably accounts for a law which has long been observed, and which has lately been admirably discussed by Alf. De Candolle in regard to plants, namely, that the lower any group of organisms is, the more widely it is apt to range. The relations just discussed, namely, low and slowly changing organisms ranging more widely than the high, some of the species of widely ranging genera themselves ranging widely, such facts as alpine, lacustrine, and marsh productions being related, with the exceptions before specified, to those on the surrounding lowlands and dry lands, though these stations are so different. The very close relation of the distinct species which inhabit the islets of the same archipelago, and especially the striking relation of the inhabitants of each whole archipelago or island to those of the nearest mainland, are, I think, utterly inexplicable on the ordinary view of the independent creation of each species, but are explicable on the view of colonization from the nearest and readiest source, together with the subsequent modification and better adaptation of the colonists to their new homes. Summary of last and present chapters. In these chapters 1 have endeavored to show that if we make due allowance for our ignorance of the full effects of all the changes of climate and of the level of the land, which have certainly occurred within the recent period, and of other similar changes which may have occurred within the same period, if we remember how profoundly ignorant we are with respect to the many and curious means of occasional transport, a subject which has hardly ever been properly experimentized on, if we bear in mind how often a species may have ranged continuously over a wide area, and then have become extinct in the intermediate tracts, I think the difficulties in believing that all the individuals of the same species, wherever located, have descended from the same parents, are not insuperable. And we are led to this conclusion, which has been arrived at by many naturalists under the designation of single centers of creation, by some general considerations, more especially from the importance of barriers and from the analogical distribution of subgenera, genera, and families. With respect to the distinct species of the same genus, which on my theory must have spread from one parent source, if we make the same allowances as before for our ignorance, and remember that some forms of life change most slowly, enormous periods of time being thus granted for their migration, I do not think that the difficulties are insuperable, though they often are in this case, and in that of the individuals of the same species, extremely grave. As exemplifying the effects of climatal changes on distribution, I have attempted to show how important has been the influence of the modern glacial period, which I am fully convinced simultaneously affected the whole world, or at least great meridional belts. As showing how diversified are the means of occasional transport, I have discussed at some little length the means of dispersal of freshwater productions. If the difficulties be not insuperable in admitting that in the long course of time the individuals of the same species, and likewise of allied species, have proceeded from some one source, then I think all the grand leading facts of geographical distribution are explicable on the theory of migration, generally of the more dominant forms of life, together with subsequent modification and the multiplication of new forms. We can thus understand the high importance of barriers, whether of land or water, which separate our several zoological and botanical provinces. We can thus understand the localization of subgenera, genera, and families, and how it is that under different latitudes, for instance in South America, the inhabitants of the plains and mountains, of the forests, marshes, and deserts, are in so mysterious a manner linked together by affinity, and are likewise linked to the extinct beings which formerly inhabited the same continent. Bearing in mind that the mutual relations of organism to organism are of the highest importance, we can see why two areas having nearly the same physical condition should often be inhabited by very different forms of life, for according to the length of time which has elapsed since new inhabitants entered one region, according to the nature of the communication which allowed certain forms and not others to enter, either in greater or lesser numbers, according or not, as those which entered happen to come in more or less direct competition with each other and with the Aborigines, and according as the immigrants were capable of varying more or less rapidly, there would ensue in different regions, independently of their physical conditions, infinitely diversified conditions of life. There would be an almost endless amount of organic action and reaction, and we should find, as we do find, some groups of beings greatly, and some only slightly modified, some developed in great force, some existing in scanty numbers, in the different great geographical provinces of the world. On these same principles, we can understand, as I have endeavored to show, why oceanic islands should have few inhabitants, but of these a great number should be endemic or peculiar, and why, in relation to the means of migration, one group of beings, even within the same class, should have all its species endemic, and another group should have all its species common to other quarters of the world. We can see why whole groups of organisms, as batrachians and terrestrial mammals, should be absent from oceanic islands, whilst the most isolated islands possess their own peculiar species of aerial mammals or bats. We can see why there should be some relation between the presence of mammals, in a more or less modified condition, and the depth of the sea between an island and the mainland. We can clearly see why all the inhabitants of an archipelago, though specifically distinct on the several islets, should be closely related to each other, and likewise be related, but less closely, to those of the nearest continent or other source whence immigrants were probably derived. We can see why in two areas, however distant from each other, there should be a correlation, in the presence of identical species, of varieties, of doubtful species, and of distinct but representative species. As the late Edward Forbes often insisted, there is a striking parallelism in the laws of life throughout time and space, the laws governing the succession of forms in past times being nearly the same with those governing at the present time the differences in different areas. We see this in many facts. The endurance of each species and group of species is continuous in time, for the exceptions to the rule are so few, that they may fairly be attributed to our not having as yet discovered in an intermediate deposit the forms which are therein absent, but which occur above and below. So in space, it certainly is the general rule that the area inhabited by a single species, or by a group of species, is continuous, and the exceptions, which are not rare, may, as I have attempted to show, be accounted for by migration at some former period under different conditions or by occasional means of transport, and by the species having become extinct in the intermediate tracts. Both in time and space, species and groups of species have their points of maximum development. Groups of species, belonging either to a certain period of time, or to a certain area, are often characterized by trifling characters in common, as of sculpture or color. In looking to the long succession of ages, as in now looking to distant provinces throughout the world, we find that some organisms differ little, whilst others belonging to a different class, or to a different order, or even only to a different family of the same order, differ greatly. In both time and space the lower members of each class generally change less than the higher, but there are in both cases marked exceptions to the rule. On my theory these several relations throughout time and space are intelligible, for whether we look to the forms of life which have changed during successive ages within the same quarter of the world, or to those which have changed after having migrated into distant quarters, in both cases the forms within each class have been connected by the same bond of ordinary generation, and the more nearly any two forms are related in blood, the nearer they will generally stand to each other in time and space. In both cases the laws of variation have been the same, and modifications have been accumulated by the same power of natural selection. Chapter 13. Mutual affinities of organic beings, morphology, embryology, rudimentary organs. Classification, group subordinate to groups. Natural system. Rules and difficulties in classification, explained on the theory of descent with modification. Classification of varieties. Descent always used in classification. Analogical or adaptive characters. Affinities, general, complex and radiating. Extinction separates and defines groups. Morphology, between members of the same class, between parts of the same individual. Embryology, laws of, explained by variations not supervening at an early age, and being inherited at a corresponding age. Rudimentary organs, their origin explained. Summary. From the first dawn of life, all organic beings are found to resemble each other in descending degrees, so that they can be classed in groups under groups. This classification is evidently not arbitrary like the grouping of the stars in constellations. The existence of groups would have been of simple signification if one group had been exclusively fitted to inhabit the land, and another the water, one to feed on flesh, another on vegetable matter, and so on, but the case is widely different in nature, for it is notorious how commonly members of even the same subgroup have different habits. In our second and fourth chapters, on variation and on natural selection, I have attempted to show that it is the widely ranging, the much diffused and common, that is the dominant species belonging to the larger genera, which vary most. The varieties, or incipient species, thus produced ultimately become converted, as I believe, into new and distinct species, and these, on the principle of inheritance, tend to produce other new and dominant species. Consequently, the groups which are now large, and which generally include many dominant species, tend to go on increasing indefinitely in size. I further attempted to show that from the varying descendants of each species trying to occupy as many and as different places as possible in the economy of nature, there is a constant tendency in their characters to diverge. This conclusion was supported by looking at the great diversity of the forms of life which, in any small area, come into the closest competition, and by looking to certain facts in naturalization. I attempted also to show that there is a constant tendency in the forms which are increasing in number and diverging in character, to supplant and exterminate the less divergent, the less improved, and preceding forms. I request the reader to turn to the diagram illustrating the action, as formerly explained, of these several principles, and he will see that the inevitable result is that the modified descendants proceeding from one progenitor become broken up into groups subordinate to groups. In the diagram, each letter on the uppermost line may represent a genus including several species, and all the genera on this line form together one class, for all have descended from one ancient but unseen parent, and, consequently, have inherited something in common. But the three genera on the left hand have, on this same principle, much in common, and form a subfamily, distinct from that including the next two genera on the right hand, which diverged from a common parent at the fifth stage of descent. These five genera have also much, though less, in common, and they form a family distinct from that including the three genera still further to the right hand, which diverged at a still earlier period. And all these genera, descended from A, form an order distinct from the genera descended from I. So that we here have many species descended from a single progenitor grouped into genera, and the genera are included in, or subordinate to, subfamilies, families, and orders, all united into one class. Thus, the grand fact in natural history of the subordination of group under group, which, from its familiarity, does not always sufficiently strike us, is in my judgment fully explained. Naturalists try to arrange the species, genera, and families in each class, on what is called the natural system. But what is meant by this system? Some authors look at it merely as a scheme for arranging together those living objects which are most alike, and for separating those which are most unlike, or as an artificial means for enunciating, as briefly as possible, general propositions, that is, by one sentence to give the characters common, for instance, to all mammals, by another those common to all carnivora, by another those common to the dog genus, and then by adding a single sentence, a full description is given of each kind of dog. The ingenuity and utility of this system are indisputable. But many naturalists think that something more is meant by the natural system. They believe that it reveals the plan of the Creator, but unless it be specified whether order in time or space, or what else is meant by the plan of the Creator, it seems to me that nothing is thus added to our knowledge. Such expressions as that famous one of Linnaeus, and which we often meet with in a more or less concealed form, that the characters do not make the genus, but that the genus gives the characters, seem to imply that something more is included in our classification than mere resemblance. I believe that something more is included, and that propinquity of descent, the only known cause of the similarity of organic beings, is the bond, hidden as it is by various degrees of modification, which is partially revealed to us by our classifications. Let us now consider the rules followed in classification, and the difficulties which are encountered on the view that classification either gives some unknown plan of creation, or is simply a scheme for enunciating general propositions and of placing together the forms most like each other. It might have been thought, and was in ancient times thought, that those parts of the structure which determined the habits of life, and the general place of each being in the economy of nature, would be of very high importance in classification. Nothing can be more false. No one regards the external similarity of a mouse to a shrew, of a dugong to a whale, of a whale to a fish, as of any importance. These resemblances, though so intimately connected with the whole life of the being, are ranked as merely adaptive or analogical characters, but to the consideration of these resemblances we shall have to recur. It may even be given as a general rule that the less any part of the organization is concerned with special habits, the more important it becomes for classification. As an instance, Owen, in speaking of the dugong, says, the generative organs being those which are most remotely related to the habits and food of an animal, I have always regarded as affording very clear indications of its true affinities. We are least likely in the modifications of these organs to mistake a merely adaptive for an essential character. So with plants, how remarkable it is that the organs of vegetation, on which their whole life depends, are of little signification, excepting in the first main divisions, whereas the organs of reproduction, with their product the seed, are of paramount importance. We must not, therefore, in classifying, trust to resemblances in parts of the organization, however important they may be for the welfare of the being in relation to the outer world. Perhaps from this cause it has partly arisen that almost all naturalists lay the greatest stress on resemblances in organs of high vital or physiological importance. No doubt this view of the classificatory importance of organs which are important is generally, but by no means always, true. But their importance for classification, I believe, depends on their greater constancy throughout large groups of species, and this constancy depends on such organs having generally been subjected to less change in the adaptation of the species to their conditions of life. That the mere physiological importance of an organ does not determine its classificatory value is almost shown by the one fact that in allied groups, in which the same organ, as we have every reason to suppose, has nearly the same physiological value, its classificatory value is widely different. No naturalist can have worked at any group without being struck with this fact, and it has been most fully acknowledged in the writings of almost every author. It will suffice to quote the highest authority, Robert Brown, who in speaking of certain organs in the Proteaceae, says their generic importance, like that of all their parts, not only in this but, as I apprehend, in every natural family, is very unequal, and in some cases seems to be entirely lost. Again in another work he says, the genera of the Carnaracea differ in having one or more ovaria, in the existence or absence of albumin, in the imbricate or valvular estivation. Any one of these characters singly is frequently of more than generic importance, though here even when all taken together they appear insufficient to separate Nestis from Carnarus. To give an example amongst insects, in one great division of the Hymenoptera, the antennae, as Westwood has remarked, are most constant in structure, in another division they differ much, and the differences are of quite subordinate value in classification, yet no one probably will say that the antennae in these two divisions of the same order are of unequal physiological importance. Any number of instances could be given of the varying importance for classification of the same important organ within the same group of beings. Again, no one will say that rudimentary or atrophied organs are of high physiological or vital importance, yet, undoubtedly, organs in this condition are often of high value in classification. No one will dispute that the rudimentary teeth in the upper jaws of young ruminants and certain rudimentary bones of the leg are highly serviceable in exhibiting the close affinity between ruminants and pachyderms. Robert Brown has strongly insisted on the fact that the rudimentary florets are of the highest importance in the classification of the grasses. Numerous instances could be given of characters derived from parts which must be considered of very trifling physiological importance, but which are universally admitted as highly serviceable in the definition of whole groups. For instance, whether or not there is an open passage from the nostrils to the mouth, the only character, according to Owen, which absolutely distinguishes fishes and reptiles, the inflection of the angle of the jaws in marsupials, the manner in which the wings of insects are folded, mere color in certain algae, mere pubescence on parts of the flower in grasses, the nature of the dermal covering, as hair or feathers, in the vertebrata. If the Ornithorhynchus had been covered with feathers instead of hair, this external and trifling character would, I think, have been considered by naturalists as important an aid in determining the degree of affinity of this strange creature to birds and reptiles, as an approach in structure in any one internal and important organ. The importance, for classification, of trifling characters mainly depends on their being correlated with several other characters of more or less importance. The value indeed of an aggregate of characters is very evident in natural history. Hence, as has often been remarked, a species may depart from its allies in several characters, both of high physiological importance and of almost universal prevalence, and yet leave us in no doubt where it should be ranked. Hence, also, it has been found that a classification founded on any single character, however important that may be, has always failed, for no part of the organization is universally constant. The importance of an aggregate of characters, even when none are important, alone explains, I think, that saying of Linnaeus, that the characters do not give the genus, but the genus gives the characters, for this saying seems founded on an appreciation of many trifling points of resemblance, too slight to be defined. Certain plants, belonging to the Malpighiaceae, bear perfect and degraded flowers. In the latter, as A. de Jussieu has remarked, the greater number of the characters proper to the species, to the genus, to the family, to the class, disappear, and thus laugh at our classification. But when Aspicarpa produced in France, during several years, only degraded flowers, departing so wonderfully in a number of the most important points of structure from the proper type of the order, yet M. Richard sagaciously saw, as Jussieu observes, that this genus should still be retained amongst the Malpighiaceae. This case seems to me well to illustrate the spirit with which our classifications are sometimes necessarily founded. Practically, when naturalists are at work, they do not trouble themselves about the physiological value of the characters which they use in defining a group, or in allocating any particular species. If they find a character nearly uniform, and common to a great number of forms, and not common to others, they use it as one of high value. If common to some lesser number, they use it as of subordinate value. This principle has been broadly confessed by some naturalists to be the true one, and by none more clearly than by that excellent botanist, Auguste Saint Hilaire. If certain characters are always found correlated with others, though no apparent bond of connection can be discovered between them, especial value is set on them. As in most groups of animals, important organs, such as those for propelling the blood, or for aerating it, or those for propagating the race, are found nearly uniform, they are considered as highly serviceable in classification, but in some groups of animals all these, the most important vital organs, are found to offer characters of quite subordinate value. We can see why characters derived from the embryo should be of equal importance with those derived from the adult, for our classifications of course include all ages of each species. But it is by no means obvious, on the ordinary view, why the structure of the embryo should be more important for this purpose than that of the adult, which alone plays its full part in the economy of nature. Yet it has been strongly urged by those great naturalists, Milne Edwards and Agassiz, that embryonic characters are the most important of any in the classification of animals, and this doctrine has very generally been admitted as true. The same fact holds good with flowering plants, of which the two main divisions have been founded on characters derived from the embryo, on the number and position of the embryonic leaves or cotyledons, and on the mode of development of the plumule and radicle. In our discussion on embryology, we shall see why such characters are so valuable, on the view of classification tacitly including the idea of descent. Our classifications are often plainly influenced by chains of affinities. Nothing can be easier than to define a number of characters common to all birds, but in the case of crustaceans, such definition has hitherto been found impossible. There are crustaceans at the opposite ends of the series, which have hardly a character in common, yet the species at both ends, from being plainly allied to others, and these to others, and so onwards, can be recognized as unequivocally belonging to this, and to no other class of the articulator. Geographical distribution has often been used, though perhaps not quite logically, in classification, more especially in very large groups of closely allied forms. Temminck insists on the utility or even necessity of this practice in certain groups of birds, and it has been followed by several entomologists and botanists. Finally, with respect to the comparative value of the various groups of species, such as orders, suborders, families, subfamilies, and genera, they seem to be, at least at present, almost arbitrary. Several of the best botanists, such as Mr. Bentham and others, have strongly insisted on their arbitrary value. Instances could be given amongst plants and insects, of a group of forms, first ranked by practiced naturalists as only a genus, and then raised to the rank of a subfamily or family, and this has been done, not because further research has detected important structural differences, at first overlooked, but because numerous allied species, with slightly different grades of difference, have been subsequently discovered. All the foregoing rules and aids and difficulties in classification are explained, if I do not greatly deceive myself, on the view that the natural system is founded on descent with modification, that the characters which naturalists consider as showing true affinity between any two or more species are those which have been inherited from a common parent, and, in so far, all true classification is genealogical. That community of descent is the hidden bond which naturalists have been unconsciously seeking, and not some unknown plan of creation, or the enunciation of general propositions, and the mere putting together and separating objects more or less alike. But I must explain my meaning more fully. I believe that the arrangement of the groups within each class, in due subordination and relation to the other groups, must be strictly genealogical in order to be natural, but that the amount of difference in the several branches or groups, though allied in the same degree in blood to their common progenitor, may differ greatly, being due to the different degrees of modification which they have undergone, and this is expressed by the forms being ranked under different genera, families, sections, or orders. The reader will best understand what is meant if he will take the trouble of referring to the diagram in the 4th chapter. We will suppose the letters A to L to represent allied genera, which lived during the Silurian epoch, and these have descended from a species which existed at an unknown anterior period. Species of 3 of these genera, A, F, and I, have transmitted modified descendants to the present day, represented by the 15 genera, A14 to Z14, on the uppermost horizontal line. Now all these modified descendants from a single species are represented as related in blood or descent to the same degree. They may metaphorically be called cousins to the same millionth degree, yet they differ widely and in different degrees from each other. The forms descended from A, now broken up into 2 or 3 families, constitute a distinct order from those descended from I, also broken up into 2 families. Nor can the existing species, descended from A, be ranked in the same genus with the parent A, or those from I, with the parent I. But the existing genus F14 may be supposed to have been but slightly modified, and it will then rank with the parent genus F, just as some few still living organic beings belong to Silurian genera. So that the amount or value of the differences between organic beings all related to each other in the same degree in blood has come to be widely different. Nevertheless, their genealogical arrangement remains strictly true, not only at the present time, but at each successive period of descent. All the modified descendants from A will have inherited something in common from their common parent, as will all the descendants from I, so will it be with each subordinate branch of descendants, at each successive period. If, however, we choose to suppose that any of the descendants of A or of I have been so much modified as to have more or less completely lost traces of their parentage, in this case, their places in a natural classification will have been more or less completely lost, as sometimes seems to have occurred with existing organisms. All the descendants of the genus F, along its whole line of descent, are supposed to have been but little modified, and they yet form a single genus. But this genus, though much isolated, will still occupy its proper intermediate position, for F originally was intermediate in character between A and I, and the several genera descended from these 2 genera will have inherited to a certain extent their characters. This natural arrangement is shown, as far as is possible on paper, in the diagram, but in much too simple a manner. If a branching diagram had not been used, and only the names of the groups had been written in a linear series, it would have been still less possible to have given a natural arrangement, and it is notoriously not possible to represent in a series, on a flat surface, the affinities which we discover in nature amongst the beings of the same group. Thus, on the view which I hold, the natural system is genealogical in its arrangement, like a pedigree, but the degrees of modification which the different groups have undergone have to be expressed by ranking them under different so-called genera, subfamilies, families, sections, orders, and classes. It may be worthwhile to illustrate this view of classification by taking the case of languages. If we possessed a perfect pedigree of mankind, a genealogical arrangement of the races of man would afford the best classification of the various languages now spoken throughout the world, and if all extinct languages, and all intermediate and slowly changing dialects, had to be included, such an arrangement would, I think, be the only possible one. Yet it might be that some very ancient language had altered little, and had given rise to few new languages, whilst others, owing to the spreading and subsequent isolation and states of civilization of the several races, descended from a common race, had altered much, and had given rise to many new languages and dialects. The various degrees of difference in the languages from the same stock would have to be expressed by groups subordinate to groups, but the proper or even only possible arrangement would still be genealogical, and this would be strictly natural, as it would connect together all languages, extinct and modern, by the closest affinities, and would give the filiation and origin of each tongue. In confirmation of this view, let us glance at the classification of varieties, which are believed or known to have descended from one species. These are grouped under species, with subvarieties under varieties, and with our domestic productions, several other grades of difference are requisite, as we have seen with pigeons. The origin of the existence of groups subordinate to groups is the same with varieties as with species, namely, closeness of descent with various degrees of modification. Nearly the same rules are followed in classifying varieties, as with species. Authors have insisted on the necessity of classing varieties on a natural instead of an artificial system. We are cautioned, for instance, not to class two varieties of the pineapple together, merely because their fruit, though the most important part, happens to be nearly identical. No one puts the Swedish and common turnips together, though the esculent and thickened stems are so similar. Whatever part is found to be most constant is used in classing varieties. Thus the great agriculturist Marshall says the horns are very useful for this purpose with cattle, because they are less variable than the shape or color of the body, etc., whereas with sheep the horns are much less serviceable, because less constant. In classing varieties, I apprehend if we had a real pedigree, a genealogical classification would be universally preferred, and it has been attempted by some authors. For we might feel sure whether there had been more or less modification, the principle of inheritance would keep the forms together which were allied in the greatest number of points. In tumbler pigeons, though some subvarieties differ from the others in the important character of having a longer beak, yet all are kept together from having the common habit of tumbling, but the short-faced breed has nearly or quite lost this habit. Nevertheless, without any reasoning or thinking on the subject, these tumblers are kept in the same group, because allied in blood and alike in some other respects. If it could be proved that the Hottentot had descended from the Negro, I think he would be classed under the Negro group, however much he might differ in color and other important characters from Negroes. With species in a state of nature, every naturalist has in fact brought descent into his classification, for he includes in his lowest grade, or that of a species, the two sexes, and how enormously these sometimes differ in the most important characters, is known to every naturalist. Scarcely a single fact can be predicated in common of the males and hermaphrodites of certain cirripedes, when adult, and yet no one dreams of separating them. The naturalist includes as one species the several larval stages of the same individual, however much they may differ from each other and from the adult, as he likewise includes the so-called alternate generations of Steenstrup, which can only in a technical sense be considered as the same individual. He includes monsters, he includes varieties, not solely because they closely resemble the parent form, but because they are descended from it. He who believes that the cowslip is descended from the primrose, or conversely, ranks them together as a single species, and gives a single definition. As soon as three orchidean forms, Monocanthus, Myanthus, and Catasetum, which had previously been ranked as three distinct genera, were known to be sometimes produced on the same spike, they were immediately included as a single species. But it may be asked, what ought we to do, if it could be proved that one species of kangaroo had been produced, by a long course of modification, from a bear? Ought we to rank this one species with bears, and what should we do with the other species? The supposition is of course preposterous, and I might answer by the argumentum ad hominem, and ask what should be done if a perfect kangaroo were seen to come out of the womb of a bear. According to all analogy, it would be ranked with bears, but then assuredly all the other species of the kangaroo family would have to be classed under the bear genus. The whole case is preposterous, for where there has been close descent in common, there will certainly be close resemblance or affinity. As descent has universally been used in classing together the individuals of the same species, though the males and females and larvae are sometimes extremely different, and as it has been used in classing varieties which have undergone a certain, and sometimes a considerable amount of modification, may not this same element of descent have been unconsciously used in grouping species under genera, and genera under higher groups, though in these cases the modification has been greater in degree, and has taken a longer time to complete? I believe it has thus been unconsciously used, and only thus can I understand the several rules and guides which have been followed by our best systematists. We have no written pedigrees, we have to make out community of descent by resemblances of any kind. Therefore we choose those characters which, as far as we can judge, are the least likely to have been modified in relation to the conditions of life to which each species has been recently exposed. Rudimentary structures on this view are as good as, or even sometimes better than, other parts of the organization. We care not how trifling a character may be, let it be the mere inflection of the angle of the jaw, the manner in which an insect's wing is folded, whether the skin be covered by hair or feathers, if it prevail throughout many and different species, especially those having very different habits of life, it assumes high value, for we can account for its presence in so many forms with such different habits, only by its inheritance from a common parent. We may err in this respect in regard to single points of structure, but when several characters, let them be ever so trifling, occur together throughout a large group of beings having different habits, we may feel almost sure, on the theory of descent, that these characters have been inherited from a common ancestor. And we know that such correlated or aggregated characters have especial value in classification. We can understand why a species or a group of species may depart, in several of its most important characteristics, from its allies, and yet be safely classed with them. This may be safely done, and is often done, as long as a sufficient number of characters, let them be ever so unimportant, betrays the hidden bond of community of descent. Let two forms have not a single character in common, yet if these extreme forms are connected together by a chain of intermediate groups, we may at once infer their community of descent, and we put them all into the same class. As we find organs of high physiological importance, those which serve to preserve life under the most diverse conditions of existence are generally the most constant, we attach especial value to them, but if these same organs, in another group or section of a group, are found to differ much, we at once value them less in our classification. We shall hereafter, I think, clearly see why embryological characters are of such high classificatory importance. Geographical distribution may sometimes be brought usefully into play in classing large and widely distributed genera, because all the species of the same genus, inhabiting any distinct and isolated region, have in all probability descended from the same parents. We can understand, on these views, the very important distinction between real affinities and analogical or adaptive resemblances. Lamarck first called attention to this distinction, and he has been ably followed by Macleay and others. The resemblance, in the shape of the body and in the fin-like anterior limbs, between the dugong, which is a pachydermatous animal, and the whale, and between both these mammals and fishes, is analogical. Amongst insects there are innumerable instances, thus Linnaeus, misled by external appearances, actually classed an homopterous insect as a moth. We see something of the same kind even in our domestic varieties, as in the thickened stems of the common and Swedish turnip. The resemblance of the greyhound and racehorse is hardly more fanciful than the analogies which have been drawn by some authors between very distinct animals. On my view of characters being of real importance for classification only in so far as they reveal descent, we can clearly understand why analogical or adaptive character, although of the utmost importance to the welfare of the being, are almost valueless to the systematist. For animals, belonging to two most distinct lines of descent, may readily become adapted to similar conditions, and thus assume a close external resemblance, but such resemblances will not reveal, will rather tend to conceal their blood relationship to their proper lines of descent. We can also understand the apparent paradox, that the very same characters are analogical when one class or order is compared with another, but give true affinities when the members of the same class or order are compared one with another. Thus the shape of the body and fin-like limbs are only analogical when whales are compared with fishes, being adaptations in both classes for swimming through the water, but the shape of the body and fin-like limbs serve as characters exhibiting true affinity between the several members of the whale family, for these cetaceans agree in so many characters, great and small, that we cannot doubt that they have inherited their general shape of body and structure of limbs from a common ancestor. So it is with fishes. As members of distinct classes have often been adapted by successive slight modifications to live under nearly similar circumstances, to inhabit for instance the three elements of land, air, and water, we can perhaps understand how it is that a numerical parallelism has sometimes been observed between the subgroups in distinct classes. A naturalist, struck by a parallelism of this nature in any one class, by arbitrarily raising or sinking the value of the groups in other classes, and all our experience shows that this valuation has hitherto been arbitrary, could easily extend the parallelism over a wide range, and thus the septenary, quinary, quaternary, and ternary classifications have probably arisen. As the modified descendants of dominant species, belonging to the larger genera, tend to inherit the advantages, which made the groups to which they belong large and their parents dominant, they are almost sure to spread widely, and to seize on more and more places in the economy of nature. The larger and more dominant groups thus tend to go on increasing in size, and they consequently supplant many smaller and feebler groups. Thus we can account for the fact that all organisms, recent and extinct, are included under a few great orders, under still fewer classes, and all in one great natural system. As showing how few the higher groups are in number, and how widely spread they are throughout the world, the fact is striking that the discovery of Australia has not added a single insect belonging to a new order, and that in the vegetable kingdom, as I learn from Dr. Hooker, it has added only 2 or 3 orders of small size. In the chapter on geological succession I attempted to show, on the principle of each group having generally diverged much in character during the long-continued process of modification, how it is that the more ancient forms of life often present characters in some slight degree intermediate between existing groups. A few old and intermediate parent forms having occasionally transmitted to the present-day descendants but little modified, will give to us our so-called osculant or aberrant groups. The more aberrant any form is, the greater must be the number of connecting forms which on my theory have been exterminated and utterly lost. And we have some evidence of aberrant forms having suffered severely from extinction, for they are generally represented by extremely few species, and such species as do occur are generally very distinct from each other, which again implies extinction. The genera Ornithorhynchus and Lepidosiren, for example, would not have been less aberrant had each been represented by a dozen species instead of by a single one, but such richness in species, as I find after some investigation, does not commonly fall to the lot of aberrant genera. We can, I think, account for this fact only by looking at aberrant forms as failing groups conquered by more successful competitors, with a few members preserved by some unusual coincidence of favorable circumstances. Mr. Waterhouse has remarked that, when a member belonging to one group of animals exhibits an affinity to a quite distinct group, this affinity in most cases is general and not special. Thus, according to Mr. Waterhouse, of all rodents, the biscature is most nearly related to marsupials, but in the points in which it approaches this order, its relations are general, and not to any one marsupial species more than to another. As the points of affinity of the biscature to marsupials are believed to be real and not merely adaptive, they are due on my theory to inheritance in common. Therefore we must suppose either that all rodents, including the biscature, branched off from some very ancient marsupial, which will have had a character in some degree intermediate with respect to all existing marsupials, or that both rodents and marsupials branched off from a common progenitor, and that both groups have since undergone much modification in divergent directions. On either view we may suppose that the biscature has retained, by inheritance, more of the character of its ancient progenitor than have other rodents, and therefore it will not be specially related to any one existing marsupial, but indirectly to all or nearly all marsupials, from having partially retained the character of their common progenitor, or of an early member of the group. On the other hand, of all marsupials, as Mr. Waterhouse has remarked, the Phascolomys resembles most nearly, not any one species, but the general order of rodents. In this case, however, it may be strongly suspected that the resemblance is only analogical, owing to the Phascolomys having become adapted to habits like those of a rodent. The elder de Candolle has made nearly similar observations on the general nature of the affinities of distinct orders of plants. On the principle of the multiplication and gradual divergence in character of the species descended from a common parent, together with their retention by inheritance of some characters in common, we can understand the excessively complex and radiating affinities by which all the members of the same family or higher group are connected together. For the common parent of a whole family of species, now broken up by extinction into distinct groups and subgroups, will have transmitted some of its characters, modified in various ways and degrees, to all, and the several species will consequently be related to each other by circuitous lines of affinity of various lengths, as may be seen in the diagram so often referred to, mounting up through many predecessors. As it is difficult to show the blood relationship between the numerous kindred of any ancient and noble family, even by the aid of a genealogical tree, and almost impossible to do this without this aid, we can understand the extraordinary difficulty which naturalists have experienced in describing, without the aid of a diagram, the various affinities which they perceive between the many living and extinct members of the same great natural class. Extinction, as we have seen in the 4th chapter, has played an important part in defining and widening the intervals between the several groups in each class. We may thus account even for the distinctness of whole classes from each other, for instance, of birds from all other vertebrate animals, by the belief that many ancient forms of life have been utterly lost, through which the early progenitors of birds were formerly connected with the early progenitors of the other vertebrate classes. There has been less entire extinction of the forms of life which once connected fishes with batrachians. There has been still less in some other classes, as in that of the crustacea, for here the most wonderfully diverse forms are still tied together by a long, but broken, chain of affinities. Extinction has only separated groups, it has by no means made them, for if every form which has ever lived on this earth were suddenly to reappear, though it would be quite impossible to give definitions by which each group could be distinguished from other groups, as all would blend together by steps as fine as those between the finest existing varieties, nevertheless a natural classification, or at least a natural arrangement, would be possible. We shall see this by turning to the diagram. The letters A to L may represent 11 Silurian genera, some of which have produced large groups of modified descendants. Every intermediate link between these 11 genera and their primordial parent, and every intermediate link in each branch and sub-branch of their descendants, may be supposed to be still alive, and the links to be as fine as those between the finest varieties. In this case it would be quite impossible to give any definition by which the several members of the several groups could be distinguished from their more immediate parents, or these parents from their ancient and unknown progenitor. Yet the natural arrangement in the diagram would still hold good, and, on the principle of inheritance, all the forms descended from A, or from I, would have something in common. In a tree we can specify this or that branch, though at the actual fork the two unite and blend together. We could not, as I have said, define the several groups, but we could pick out types, or forms, representing most of the characters of each group, whether large or small, and thus give a general idea of the value of the differences between them. This is what we should be driven to, if we were ever to succeed in collecting all the forms in any class which have lived throughout all time and space. We shall certainly never succeed in making so perfect a collection. Nevertheless, in certain classes, we are tending in this direction, and Milne Edwards has lately insisted, in an able paper, on the high importance of looking to types, whether or not we can separate and define the groups to which such types belong. Finally, we have seen that natural selection, which results from the struggle for existence, and which almost inevitably induces extinction and divergence of character in the many descendants from one dominant parent species, explains that great and universal feature in the affinities of all organic beings, namely, their subordination in group under group. We use the element of descent in classing the individuals of both sexes and of all ages. Although having few characters in common, under one species, we use descent in classing acknowledged varieties, however different they may be from their parent, and I believe this element of descent is the hidden bond of connection which naturalists have sought under the term of the natural system. On this idea of the natural system being, in so far as it has been perfected, genealogical in its arrangement, with the grades of difference between the descendants from a common parent, expressed by the terms genera, families, orders, etc., we can understand the rules which we are compelled to follow in our classification. We can understand why we value certain resemblances far more than others, why we are permitted to use rudimentary and useless organs, or others of trifling physiological importance, why, in comparing one group with a distinct group, we summarily reject analogical or adaptive characters, and yet use these same characters within the limits of the same group. We can clearly see how it is that all living and extinct forms can be grouped together in one great system, and how the several members of each class are connected together by the most complex and radiating lines of affinities. We shall never, probably, disentangle the inextricable web of affinities between the members of any one class, but when we have a distinct object in view, and do not look to some unknown plan of creation, we may hope to make sure but slow progress. Morphology. We have seen that the members of the same class, independently of their habits of life, resemble each other in the general plan of their organization. This resemblance is often expressed by the term unity of type, or by saying that the several parts and organs in the different species of the class are homologous. The whole subject is included under the general name of morphology. This is the most interesting department of natural history, and may be said to be its very soul. What can be more curious than that the hand of a man, formed for grasping, that of a mole for digging, the leg of the horse, the paddle of the porpoise, and the wing of the bat, should all be constructed on the same pattern, and should include the same bones, in the same relative positions? Geoffrey St. Hilaire has insisted strongly on the high importance of relative connection in homologous organs. The parts may change to almost any extent in form and size, and yet they always remain connected together in the same order. We never find, for instance, the bones of the arm and forearm, or of the thigh and leg, transposed. Hence the same names can be given to the homologous bones in widely different animals. We see the same great law in the construction of the mouths of insects. What can be more different than the immensely long spiral proboscis of a sphinx moth, the curious folded one of a bee or bug, and the great jaws of a beetle? Yet all these organs, serving for such different purposes, are formed by infinitely numerous modifications of an upper lip, mandibles, and 2 pairs of maxillae. Analogous laws govern the construction of the mouths and limbs of crustaceans. So it is with the flowers of plants. Nothing can be more hopeless than to attempt to explain this similarity of pattern in members of the same class, by utility or by the doctrine of final causes. The hopelessness of the attempt has been expressly admitted by Owen in his most interesting work on the nature of limbs. On the ordinary view of the independent creation of each being, we can only say that so it is, that it has so pleased the Creator to construct each animal and plant. The explanation is manifest on the theory of the natural selection of successive slight modifications, each modification being profitable in some way to the modified form, but often affecting by correlation of growth other parts of the organization. In changes of this nature, there will be little or no tendency to modify the original pattern, or to transpose parts. The bones of a limb might be shortened and widened to any extent, and become gradually enveloped in thick membrane, so as to serve as a fin, or a webbed foot might have all its bones, or certain bones, lengthened to any extent, and the membrane connecting them increased to any extent, so as to serve as a wing. Yet in all this great amount of modification there will be no tendency to alter the framework of bones or the relative connection of the several parts. If we suppose that the ancient progenitor, the archetype as it may be called, of all mammals, had its limbs constructed on the existing general pattern, for whatever purpose they served, we can at once perceive the plain signification of the homologous construction of the limbs throughout the whole class. So with the mouths of insects, we have only to suppose that their common progenitor had an upper lip, mandibles, and 2 pair of maxillae, these parts being perhaps very simple in form, and then natural selection will account for the infinite diversity in structure and function of the mouths of insects. Nevertheless, it is conceivable that the general pattern of an organ might become so much obscured as to be finally lost, by the atrophy and ultimately by the complete abortion of certain parts, by the soldering together of other parts, and by the doubling or multiplication of others, variations which we know to be within the limits of possibility. In the paddles of the extinct gigantic sea lizards, and in the mouths of certain suctorial crustaceans, the general pattern seems to have been thus to a certain extent obscured. There is another and equally curious branch of the present subject, namely, the comparison not of the same part in different members of a class, but of the different parts or organs in the same individual. Most physiologists believe that the bones of the skull are homologous with, that is, correspond in number and in relative connection with, the elemental parts of a certain number of vertebrae. The anterior and posterior limbs in each member of the vertebrate and articulate classes are plainly homologous. We see the same law in comparing the wonderfully complex jaws and legs in crustaceans. It is familiar to almost every one that in a flower the relative position of the sepals, petals, stamens, and pistils, as well as their intimate structure, are intelligible on the view that they consist of metamorphosed leaves, arranged in a spire. In monstrous plants, we often get direct evidence of the possibility of one organ being transformed into another, and we can actually see in embryonic crustaceans and in many other animals, and in flowers, that organs, which when mature become extremely different, are at an early stage of growth exactly alike. How inexplicable are these facts on the ordinary view of creation? Why should the brain be enclosed in a box composed of such numerous and such extraordinarily shaped pieces of bone? As Owen has remarked, the benefit derived from the yielding of the separate pieces in the act of parturition of mammals will by no means explain the same construction in the skulls of birds. Why should similar bones have been created in the formation of the wing and leg of a bat, used as they are for such totally different purposes? Why should one crustacean, which has an extremely complex mouth formed of many parts, consequently always have fewer legs, or conversely, those with many legs have simpler mouths? Why should the sepals, petals, stamens, and pistils in any individual flower, though fitted for such widely different purposes, be all constructed on the same pattern? On the theory of natural selection, we can satisfactorily answer these questions. In the vertebrata, we see a series of internal vertebrae bearing certain processes and appendages. In the articulator, we see the body divided into a series of segments, bearing external appendages, and in flowering plants, we see a series of successive spiral whorls of leaves. An indefinite repetition of the same part or organ is the common characteristic, as Owen has observed, of all low or little modified forms. Therefore we may readily believe that the unknown progenitor of the vertebrata possessed many vertebrae, the unknown progenitor of the articulator, many segments, and the unknown progenitor of flowering plants, many spiral whorls of leaves. We have formerly seen that parts many times repeated are eminently liable to vary in number and structure. Consequently, it is quite probable that natural selection, during a long continued course of modification, should have seized on a certain number of the primordially similar elements, many times repeated, and have adapted them to the most diverse purposes. And as the whole amount of modification will have been effected by slight successive steps, we need not wonder at discovering in such parts or organs a certain degree of fundamental resemblance, retained by the strong principle of inheritance. In the great class of mollusks, though we can homologize the parts of one species with those of another and distinct species, we can indicate but few serial homologies, that is, we are seldom enabled to say that one part or organ is homologous with another in the same individual. And we can understand this fact, for in mollusks, even in the lowest members of the class, we do not find nearly so much indefinite repetition of any one part, as we find in the other great classes of the animal and vegetable kingdoms. Naturalists frequently speak of the skull as formed of metamorphosed vertebrae, the jaws of crabs as metamorphosed legs, the stamens and pistils of flowers as metamorphosed leaves, but it would in these cases probably be more correct, as Professor Huxley has remarked, to speak of both skull and vertebrae, both jaws and legs, etc., as having been metamorphosed, not one from the other, but from some common element. Naturalists, however, use such language only in a metaphorical sense. They are far from meaning that during a long course of descent, primordial organs of any kind, vertebrae in the one case and legs in the other, have actually been modified into skulls or jaws. Yet so strong is the appearance of a modification of this nature having occurred, that naturalists can hardly avoid employing language having this plain signification. On my view, these terms may be used literally, and the wonderful fact of the jaws, for instance, of a crab retaining numerous characters, which they would probably have retained through inheritance, if they had really been metamorphosed during a long course of descent from true legs, or from some simple appendage, is explained. Embryology. It has already been casually remarked that certain organs in the individual, which when mature become widely different and serve for different purposes, are in the embryo exactly alike. The embryos, also, of distinct animals within the same class are often strikingly similar. A better proof of this cannot be given than a circumstance mentioned by Agassiz, namely, that having forgotten to ticket the embryo of some vertebrate animal, he cannot now tell whether it be that of a mammal, bird, or reptile. The vermiform larvae of moths, flies, beetles, etc. resemble each other much more closely than do the mature insects, but in the case of larvae, the embryos are active, and have been adapted for special lines of life. A trace of the law of embryonic resemblance sometimes lasts till a rather late age. Thus birds of the same genus, and of closely allied genera, often resemble each other in their first and second plumage, as we see in the spotted feathers in the thrush group. In the cat tribe, most of the species are striped or spotted in lines, and stripes can be plainly distinguished in the whelp of the lion. We occasionally, though rarely, see something of this kind in plants. Thus the embryonic leaves of the ilex or firs, and the first leaves of the Philodinius acacias, are pinnate or divided like the ordinary leaves of the leguminosae. The points of structure, in which the embryos of widely different animals of the same class resemble each other, often have no direct relation to their conditions of existence. We cannot, for instance, suppose that in the embryos of the vertebrata the peculiar loop-like course of the arteries near the branchial slits are related to similar conditions, in the young mammal which is nourished in the womb of its mother, in the egg of the bird which is hatched in a nest, and in the spawn of a frog under water. We have no more reason to believe in such a relation than we have to believe that the same bones in the hand of a man, wing of a bat, and fin of a porpoise, are related to similar conditions of life. No one will suppose that the stripes on the whelp of a lion, or the spots on the young blackbird, are of any use to these animals, or are related to the conditions to which they are exposed. The case, however, is different when an animal during any part of its embryonic career is active and has to provide for itself. The period of activity may come on earlier or later in life, but whenever it comes on, the adaptation of the larva to its conditions of life is just as perfect and as beautiful as in the adult animal. From such special adaptations, the similarity of the larvae or active embryos of allied animals is sometimes much obscured, and cases could be given of the larvae of two species, or of two groups of species, differing quite as much, or even more, from each other than do their adult parents. In most cases, however, the larvae, though active, still obey more or less closely the law of common embryonic resemblance. Cirripedes afford a good instance of this. Even the illustrious Cuvier did not perceive that a barnacle was, as it certainly is, a crustacean, but a glance at the larva shows this to be the case in an unmistakable manner. So again the two main divisions of cirripedes, the pedunculated and sessile, which differ widely in external appearance, have larvae in all their several stages barely distinguishable. The embryo in the course of development generally rises in organization. I use this expression, though I am aware that it is hardly possible to define clearly what is meant by the organization being higher or lower. But no one probably will dispute that the butterfly is higher than the caterpillar. In some cases, however, the mature animal is generally considered as lower in the scale than the larva, as with certain parasitic crustaceans. To refer once again to cirripedes, the larvae in the first stage have 3 pairs of legs, a very simple single eye, and a probosciformed mouth, with which they feed largely, for they increase much in size. In the second stage, answering to the chrysalis stage of butterflies, they have 6 pairs of beautifully constructed natatory legs, a pair of magnificent compound eyes, and extremely complex antennae, but they have a closed and imperfect mouth and cannot feed. Their function at this stage is to search by their well-developed organs of sense, and to reach by their active powers of swimming, a proper place on which to become attached and to undergo their final metamorphosis. When this is completed they are fixed for life, their legs are now converted into prehensile organs, they again obtain a well-constructed mouth, but they have no antennae, and their 2 eyes are now reconverted into a minute, single, and very simple eye spot. In this last and complete state, cirripedes may be considered as either more highly or more lowly organized than they were in the larval condition. But in some genera the larvae become developed either into hermaphrodites having the ordinary structure, or into what I have called complemental males, and in the latter, the development has assuredly been retrograde, for the male is a mere sac, which lives for a short time, and is destitute of mouth, stomach, or other organ of importance, excepting for reproduction. We are so much accustomed to see differences in structure between the embryo and the adult, and likewise a close similarity in the embryos of widely different animals within the same class, that we might be led to look at these facts as necessarily contingent in some manner on growth. But there is no obvious reason why, for instance, the wing of a bat, or the fin of a porpoise, should not have been sketched out with all the parts in proper proportion, as soon as any structure became visible in the embryo. And in some whole groups of animals and in certain members of other groups, the embryo does not at any period differ widely from the adult. Thus Owen has remarked in regard to cuttlefish, there is no metamorphosis, the cephalopodic character is manifested long before the parts of the embryo are completed, and again in spiders, there is nothing worthy to be called a metamorphosis. The larvae of insects, whether adapted to the most diverse and active habits, or quite inactive, being fed by their parents or placed in the midst of proper nutriment, yet nearly all pass through a similar worm-like stage of development, but in some few cases, as in that of Aphis, if we look to the admirable drawings by Professor Huxley of the development of this insect, we see no trace of the vermiform stage. How, then, can we explain these several facts in embryology, namely the very general, but not universal difference in structure between the embryo and the adult, of parts in the same individual embryo, which ultimately become very unlike and serve for diverse purposes, being at this early period of growth alike, of embryos of different species within the same class, generally, but not universally, resembling each other, of the structure of the embryo not being closely related to its conditions of existence, except when the embryo becomes at any period of life active and has to provide for itself, of the embryo apparently having sometimes a higher organization than the mature animal, into which it is developed. I believe that all these facts can be explained, as follows, on the view of descent with modification. It is commonly assumed, perhaps from monstrosities often affecting the embryo at a very early period, that slight variations necessarily appear at an equally early period. But we have little evidence on this head. Indeed, the evidence rather points the other way, for it is notorious that breeders of cattle, horses, and various fancy animals cannot positively tell, until some time after the animal has been born, what its merits or form will ultimately turn out. We see this plainly in our own children. We cannot always tell whether the child will be tall or short, or what its precise features will be. The question is not at what period of life any variation has been caused, but at what period it is fully displayed. The cause may have acted, and I believe generally has acted, even before the embryo is formed, and the variation may be due to the male and female sexual elements having been affected by the conditions to which either parent, or their ancestors, have been exposed. Nevertheless, an effect thus caused at a very early period, even before the formation of the embryo, may appear late in life, as when an hereditary disease, which appears in old age alone, has been communicated to the offspring from the reproductive element of one parent. Or again, as when the horns of crossbred cattle have been affected by the shape of the horns of either parent. For the welfare of a very young animal, as long as it remains in its mother's womb, or in the egg, or as long as it is nourished and protected by its parent, it must be quite unimportant whether most of its characters are fully acquired a little earlier or later in life. It would not signify, for instance, to a bird which obtained its food best by having a long beak, whether or not it assumed a beak of this particular length, as long as it was fed by its parents. Hence, I conclude that it is quite possible that each of the many successive modifications, by which each species has acquired its present structure, may have supervened at a not very early period of life, and some direct evidence from our domestic animal supports this view. But in other cases it is quite possible that each successive modification, or most of them, may have appeared at an extremely early period. I have stated in the first chapter that there is some evidence to render it probable that at whatever age any variation first appears in the parent, it tends to reappear at a corresponding age in the offspring. Certain variations can only appear at corresponding ages, for instance, peculiarities in the caterpillar, cocoon, or imago states of the silk moth, or, again, in the horns of almost full-grown cattle. But further than this, variations which, for all that we can see, might have appeared earlier or later in life, tend to appear at a corresponding age in the offspring and parent. I am far from meaning that this is invariably the case, and I could give a good many cases of variations, taking the word in the largest sense, which have supervened at an earlier age in the child than in the parent. These two principles, if their truth be admitted, will, I believe, explain all the above specified leading facts in embryology. But first let us look at a few analogous cases in domestic varieties. Some authors who have written on dogs maintain that the greyhound and bulldog, though appearing so different, are really varieties most closely allied, and have probably descended from the same wild stock. Hence I was curious to see how far their puppies differed from each other. I was told by breeders that they differed just as much as their parents, and this, judging by the eye, seemed almost to be the case. But on actually measuring the old dogs and their 6-days-old puppies, I found that the puppies had not nearly acquired their full amount of proportional difference. So, again, I was told that the foals of cart and race horses differed as much as the full-grown animals, and this surprised me greatly, as I think it probable that the difference between these two breeds has been wholly caused by selection under domestication. But having had careful measurements made of the dam and of a 3-days-old colt of a race and heavy cart horse, I find that the colts have by no means acquired their full amount of proportional difference. As the evidence appears to me conclusive that the several domestic breeds of pigeon have descended from one wild species, I compared young pigeons of various breeds. Within 12 hours after being hatched, I carefully measured the proportions, but will not here give details of the beak, width of mouth, length of nostril and of eyelid, size of feet and length of leg, in the wild stock, in pouters, fantails, runts, barbs, dragons, carriers, and tumblers. Now some of these birds, when mature, differ so extraordinarily in length and form of beak, that they would, I cannot doubt, be ranked in distinct genera, had they been natural productions. But when the nestling birds of these several breeds were placed in a row, though most of them could be distinguished from each other, yet their proportional differences in the above specified several points were incomparably less than in the full-grown birds. Some characteristic points of difference, for instance, that of the width of mouth, could hardly be detected in the young. But there was one remarkable exception to this rule, for the young of the short-faced tumbler differed from the young of the wild rock pigeon and of the other breeds, in all its proportions, almost exactly as much as in the adult state. The two principles above given seem to me to explain these facts in regard to the later embryonic stages of our domestic varieties. Fanciers select their horses, dogs, and pigeons for breeding when they are nearly grown up. They are indifferent whether the desired qualities and structures have been acquired earlier or later in life, if the full-grown animal possesses them. And the cases just given, more especially that of pigeons, seem to show that the characteristic differences which give value to each breed, and which have been accumulated by man-selection, have not generally first appeared at an early period of life, and have been inherited by the offspring at a corresponding not early period. But the case of the short-faced tumbler, which when 12 hours old had acquired its proper proportions, proves that this is not the universal rule, for here the characteristic differences must either have appeared at an earlier period than usual, or, if not so, the differences must have been inherited, not at the corresponding, but at an earlier age. Now let us apply these facts and the above two principles, which latter, though not proved true, can be shown to be in some degree probable, to species in a state of nature. Let us take a genus of birds, descended on my theory from some one-parent species, and of which the several new species have become modified through natural selection in accordance with their diverse habits. Then, from the many slight successive steps of variation having supervened at a rather late age, and having been inherited at a corresponding age, the young of the new species of our supposed genus will manifestly tend to resemble each other much more closely than do the adults, just as we have seen in the case of pigeons. We may extend this view to whole families or even classes. The forelimbs, for instance, which served as legs in the parent species, may become, by a long course of modification, adapted in one descendant to act as hands, in another as paddles, in another as wings, and on the above two principles, namely of each successive modification supervening at a rather late age, and being inherited at a corresponding late age. The forelimbs in the embryos of the several descendants of the parent species will still resemble each other closely, for they will not have been modified. But in each individual new species, the embryonic forelimbs will differ greatly from the forelimbs in the mature animal, the limbs in the latter having undergone much modification at a rather late period of life, and having thus been converted into hands, or paddles, or wings. Whatever influence long-continued exercise or use on the one hand, and disuse on the other, may have in modifying an organ, such influence will mainly affect the mature animal, which has come to its full powers of activity and has to gain its own living, and the effects thus produced will be inherited at a corresponding mature age. Whereas the young will remain unmodified, or be modified in a lesser degree, by the effects of use and disuse. In certain cases the successive steps of variation might supervene, from causes of which we are wholly ignorant, at a very early period of life, or each step might be inherited at an earlier period than that at which it first appeared. In either case, as with the short-faced tumbler, the young or embryo would closely resemble the mature parent form. We have seen that this is the rule of development in certain whole groups of animals, as with cuttlefish and spiders, and with a few members of the great class of insects, as with aphids. With respect to the final cause of the young in these cases not undergoing any metamorphosis, or closely resembling their parents from their earliest age, we can see that this would result from the two following contingencies: firstly, from the young, during a course of modification carried on for many generations, having to provide for their own wants at a very early stage of development, and secondly, from their following exactly the same habits of life with their parents, for in this case, it would be indispensable for the existence of the species, that the child should be modified at a very early age in the same manner with its parents, in accordance with their similar habits. Some further explanation, however, of the embryo not undergoing any metamorphosis is perhaps requisite. If, on the other hand, it profited the young to follow habits of life in any degree different from those of their parent, and consequently to be constructed in a slightly different manner, then, on the principle of inheritance at corresponding ages, the active young or larvae might easily be rendered by natural selection different to any conceivable extent from their parents. Such differences might, also, become correlated with successive stages of development, so that the larvae, in the first stage, might differ greatly from the larvae in the second stage, as we have seen to be the case with cirripedes. The adult might become fitted for sites or habits, in which organs of locomotion or of the senses, etc., would be useless, and in this case the final metamorphosis would be said to be retrograde. As all the organic beings, extinct and recent, which have ever lived on this earth have to be classed together, and as all have been connected by the finest gradations, the best, or indeed, if our collections were nearly perfect, the only possible arrangement, would be genealogical. Descent being on my view the hidden bond of connection which naturalists have been seeking under the term of the natural system. On this view we can understand how it is that, in the eyes of most naturalists, the structure of the embryo is even more important for classification than that of the adult. For the embryo is the animal in its less modified state, and in so far it reveals the structure of its progenitor. In two groups of animal, however much they may at present differ from each other in structure and habits, if they pass through the same or similar embryonic stages, we may feel assured that they have both descended from the same or nearly similar parents, and are therefore in that degree closely related. Thus, community in embryonic structure reveals community of descent. It will reveal this community of descent, however much the structure of the adult may have been modified and obscured. We have seen, for instance, that cirripedes can at once be recognized by their larvae as belonging to the great class of crustaceans. As the embryonic state of each species and group of species partially shows us the structure of their less modified ancient progenitors, we can clearly see why ancient and extinct forms of life should resemble the embryos of their descendants, our existing species. Agassiz believes this to be a law of nature, but I am bound to confess that I only hope to see the law hereafter proved true. It can be proved true in those cases alone in which the ancient state, now supposed to be represented in many embryos, has not been obliterated, either by the successive variations in a long course of modification having supervened at a very early age, or by the variations having been inherited at an earlier period than that at which they first appeared. It should also be borne in mind that the supposed law of resemblance of ancient forms of life to the embryonic stages of recent forms may be true, but yet, owing to the geological record not extending far enough back in time, may remain for a long period, or forever, incapable of demonstration. Thus, as it seems to me, the leading facts in embryology, which are second in importance to none in natural history, are explained on the principle of slight modifications not appearing, in the many descendants from some one ancient progenitor, at a very early period in the life of each, though perhaps caused at the earliest, and being inherited at a corresponding not early period. Embryology rises greatly in interest when we thus look at the embryo as a picture, more or less obscured, of the common parent form of each great class of animals. Rudimentary, atrophied, or aborted organs. Organs or parts in this strange condition, bearing the stamp of inutility, are extremely common throughout nature. For instance, rudimentary mammae are very general in the males of mammals. I presume that the bastard wing in birds may be safely considered as a digit in a rudimentary state. In very many snakes one lobe of the lungs is rudimentary, in other snakes there are rudiments of the pelvis and hind limbs. Some of the cases of rudimentary organs are extremely curious, for instance, the presence of teeth in fetal whales, which when grown up have not a tooth in their heads, and the presence of teeth, which never cut through the gums, in the upper jaws of our unborn calves. It has even been stated on good authority that rudiments of teeth can be detected in the beaks of certain embryonic birds. Nothing can be plainer than that wings are formed for flight, yet in how many insects do we see wings so reduced in size as to be utterly incapable of flight, and not rarely lying under wing cases, firmly soldered together? The meaning of rudimentary organs is often quite unmistakable. For instance, there are beetles of the same genus, and even of the same species, resembling each other most closely in all respects, one of which will have full-sized wings, and another mere rudiments of membrane, and here it is impossible to doubt that the rudiments represent wings. Rudimentary organs sometimes retain their potentiality, and are merely not developed. This seems to be the case with the mammae of male mammals, for many instances are on record of these organs having become well developed in full-grown males, and having secreted milk. So again there are normally 4 developed and 2 rudimentary teats in the udders of the genus Bos, but in our domestic cows the 2 sometimes become developed and give milk. In individual plants of the same species the petals sometimes occur as mere rudiments, and sometimes in a well-developed state. In plants with separated sexes, the male flowers often have a rudiment of a pistil, and Kohlrotter found that by crossing such male plants with an hermaphrodite species, the rudiment of the pistil in the hybrid offspring was much increased in size, and this shows that the rudiment and the perfect pistil are essentially alike in nature. an organ serving for two purposes may become rudimentary or utterly aborted for one, even the more important purpose, and remain perfectly efficient for the other. Thus in plants, the office of the pistil is to allow the pollen tubes to reach the ovules protected in the ovarium at its base. The pistil consists of a stigma supported on the style, but in some compositae, the male florets, which of course cannot be fecundated, have a pistil, which is in a rudimentary state, for it is not crowned with a stigma, but the style remains well developed, and is clothed with hairs as in other compositae, for the purpose of brushing the pollen out of the surrounding anthers. Again, an organ may become rudimentary for its proper purpose, and be used for a distinct object. In certain fish the swimbladder seems to be rudimentary for its proper function of giving buoyancy, but has become converted into a nascent breathing organ or lung. Other similar instances could be given. Rudimentary organs in the individuals of the same species are very liable to vary in degree of development and in other respects. Moreover, in closely allied species, the degree to which the same organ has been rendered rudimentary occasionally differs much. This latter fact is well exemplified in the state of the wings of the female moths in certain groups. Rudimentary organs may be utterly aborted, and this implies that we find in an animal or plant no trace of an organ, which analogy would lead us to expect to find, and which is occasionally found in monstrous individuals of the species. Thus in the snapdragon, Antirrhinum, we generally do not find a rudiment of a fifth stamen, but this may sometimes be seen. In tracing the homologies of the same part in different members of a class, nothing is more common, or more necessary, than the use and discovery of rudiments. This is well shown in the drawings given by Owen of the bones of the leg of the horse, ox, and rhinoceros. It is an important fact that rudimentary organs, such as teeth in the upper jaws of whales and ruminants, can often be detected in the embryo, but afterwards wholly disappear. It is also, I believe, a universal rule, that a rudimentary part or organ is of greater size relatively to the adjoining parts in the embryo than in the adult, so that the organ at this early age is less rudimentary, or even cannot be said to be in any degree rudimentary. Hence, also, a rudimentary organ in the adult is often said to have retained its embryonic condition. I have now given the leading facts with respect to rudimentary organs. In reflecting on them, every one must be struck with astonishment, for the same reasoning power which tells us plainly that most parts and organs are exquisitely adapted for certain purposes, tells us with equal plainness that these rudimentary or atrophied organs are imperfect and useless. In works on natural history, rudimentary organs are generally said to have been created for the sake of symmetry, or in order to complete the scheme of nature, but this seems to me no explanation, merely a restatement of the fact. Would it be thought sufficient to say that because planets revolve in elliptic courses round the Sun, satellites follow the same course round the planets, for the sake of symmetry, and to complete the scheme of nature? An eminent physiologist accounts for the presence of rudimentary organs, by supposing that they serve to excrete matter in excess, or injurious to the system, but can we suppose that the minute papilla, which often represents the pistil in male flowers, and which is formed merely of cellular tissue, can thus act? Can we suppose that the formation of rudimentary teeth which are subsequently absorbed, can be of any service to the rapidly growing embryonic calf by the excretion of precious phosphate of lime? When a man's fingers have been amputated, imperfect nails sometimes appear on the stumps. I could as soon believe that these vestiges of nails have appeared, not from unknown laws of growth, but in order to excrete horny matter, as that the rudimentary nails on the fin of the manatee were formed for this purpose. On my view of descent with modification, the origin of rudimentary organs is simple. We have plenty of cases of rudimentary organs in our domestic productions, as the stump of a tail in tailless breeds, the vestige of an ear in earless breeds, the reappearance of minute dangling horns in hornless breeds of cattle, more especially, according to Youatt, in young animals, and the state of the whole flower in the cauliflower. We often see rudiments of various parts in monsters. But I doubt whether any of these cases throw light on the origin of rudimentary organs in a state of nature, further than by showing that rudiments can be produced, for I doubt whether species under nature ever undergo abrupt changes. I believe that disuse has been the main agency, that it has led in successive generations to the gradual reduction of various organs, until they have become rudimentary, as in the case of the eyes of animals inhabiting dark caverns, and of the wings of birds inhabiting oceanic islands, which have seldom been forced to take flight, and have ultimately lost the power of flying. Again, an organ useful under certain conditions might become injurious under others, as with the wings of beetles living on small and exposed islands, and in this case natural selection would continue slowly to reduce the organ until it was rendered harmless and rudimentary. Any change in function, which can be effected by insensibly small steps, is within the power of natural selection, so that an organ rendered, during changed habits of life, useless or injurious for one purpose, might easily be modified and used for another purpose. Or an organ might be retained for one alone of its former functions. An organ, when rendered useless, may well be variable, for its variations cannot be checked by natural selection. At whatever period of life disuse or selection reduces an organ, and this will generally be when the being has come to maturity and to its full powers of action, the principle of inheritance at corresponding ages will reproduce the organ in its reduced state at the same age, and consequently will seldom affect or reduce it in the embryo. Thus we can understand the greater relative size of rudimentary organs in the embryo, and their lesser relative size in the adult. But if each step of the process of reduction were to be inherited, not at the corresponding age, but at an extremely early period of life, as we have good reason to believe to be possible, the rudimentary part would tend to be wholly lost, and we should have a case of complete abortion. The principle, also, of economy, explained in a former chapter, by which the materials forming any part or structure, if not useful to the possessor, will be saved as far as is possible, will probably often come into play, and this will tend to cause the entire obliteration of a rudimentary organ. As the presence of rudimentary organs is thus due to the tendency in every part of the organization, which has long existed, to be inherited, we can understand, on the genealogical view of classification, how it is that systematists have found rudimentary parts as useful as, or even sometimes more useful than, parts of high physiological importance. Rudimentary organs may be compared with the letters in a word, still retained in the spelling, but become useless in the pronunciation, but which serve as a clue in seeking for its derivation. On the view of descent with modification, we may conclude that the existence of organs in a rudimentary, imperfect, and useless condition, or quite aborted, far from presenting a strange difficulty, as they assuredly do on the ordinary doctrine of creation, might even have been anticipated, and can be accounted for by the laws of inheritance. Summary. In this chapter 1 have attempted to show that the subordination of group to group in all organisms throughout all time, that the nature of the relationship, by which all living and extinct beings are united by complex, radiating, and circuitous lines of affinities into one grand system, the rules followed and the difficulties encountered by naturalists in their classifications, the value set upon characters, if constant and prevalent, whether of high vital importance, or of the most trifling importance, or, as in rudimentary organs, of no importance, the wide opposition in value between analogical or adaptive characters, and characters of true affinity, and other such rules, all naturally follow on the view of the common parentage of those forms which are considered by naturalists as allied, together with their modification through natural selection, with its contingencies of extinction and divergence of character. In considering this view of classification, it should be borne in mind that the element of descent has been universally used in ranking together the sexes, ages, and acknowledged varieties of the same species, however different they may be in structure. If we extend the use of this element of descent, the only certainly known cause of similarity in organic beings, we shall understand what is meant by the natural system. It is genealogical in its attempted arrangement, with the grades of acquired difference marked by the terms varieties, species, genera, families, orders, and classes. On this same view of descent with modification, all the great facts in morphology become intelligible, whether we look to the same pattern displayed in the homologous organs, to whatever purpose applied, of the different species of a class, or to the homologous parts constructed on the same pattern in each individual animal and plant. On the principle of successive slight variations, not necessarily or generally supervening at a very early period of life, and being inherited at a corresponding period, we can understand the great leading facts in embryology, namely, the resemblance in an individual embryo of the homologous parts, which when matured will become widely different from each other in structure and function, and the resemblance in different species of a class of the homologous parts or organs, though fitted in the adult members for purposes as different as possible. Larvae are active embryos, which have become specially modified in relation to their habits of life, through the principle of modifications being inherited at corresponding ages. On this same principle, and bearing in mind that when organs are reduced in size, either from disuse or selection, it will generally be at that period of life when the being has to provide for its own wants, and bearing in mind how strong is the principle of inheritance, the occurrence of rudimentary organs and their final abortion present to us no inexplicable difficulties. On the contrary, their presence might have been even anticipated. The importance of embryological characters and of rudimentary organs in classification is intelligible, on the view that an arrangement is only so far natural as it is genealogical. Finally, the several classes of facts which have been considered in this chapter seem to me to proclaim so plainly that the innumerable species, genera, and families of organic beings, with which this world is peopled, have all descended, each within its own class or group, from common parents, and have all been modified in the course of descent, that I should without hesitation adopt this view, even if it were unsupported by other facts or arguments. Chapter 14. Recapitulation and Conclusion. Recapitulation of the difficulties on the theory of natural selection. Recapitulation of the general and special circumstances in its favor. Causes of the general belief in the immutability of species. How far the theory of natural selection may be extended. Effects of its adoption on the study of natural history. Concluding remarks. As this whole volume is one long argument, it may be convenient to the reader to have the leading facts and inferences briefly recapitulated. That many and grave objections may be advanced against the theory of descent with modification through natural selection, I do not deny. I have endeavored to give to them their full force. Nothing at first can appear more difficult to believe than that the more complex organs and instincts should have been perfected, not by means superior to, though analogous with, human reason, but by the accumulation of innumerable slight variations, each good for the individual possessor. Nevertheless, this difficulty, though appearing to our imagination insuperably great, cannot be considered real if we admit the following propositions, namely, that gradations in the perfection of any organ or instinct, which we may consider, either do now exist or could have existed, each good of its kind, that all organs and instincts are, in ever so slight a degree, variable, and, lastly, that there is a struggle for existence leading to the preservation of each profitable deviation of structure or instinct. The truth of these propositions cannot, I think, be disputed. It is, no doubt, extremely difficult even to conjecture by what gradations many structures have been perfected, more especially amongst broken and failing groups of organic beings, but we see so many strange gradations in nature, as is proclaimed by the canon, natura non facit saltum, that we ought to be extremely cautious in saying that any organ or instinct, or any whole being, could not have arrived at its present state by many graduated steps. There are, it must be admitted, cases of special difficulty on the theory of natural selection, and one of the most curious of these is the existence of 2 or 3 defined castes of workers or sterile females in the same community of ants, but I have attempted to show how this difficulty can be mastered. With respect to the almost universal sterility of species when first crossed, which forms so remarkable a contrast with the almost universal fertility of varieties when crossed, I must refer the reader to the recapitulation of the facts given at the end of the 8th chapter, which seem to me conclusively to show that this sterility is no more a special endowment than is the incapacity of 2 trees to be grafted together, but that it is incidental on constitutional differences in the reproductive systems of the intercrossed species. We see the truth of this conclusion in the vast difference in the result, when the same 2 species are crossed reciprocally, that is, when one species is first used as the father and then as the mother. The fertility of varieties when intercrossed and of their mongrel offspring cannot be considered as universal, nor is their very general fertility surprising when we remember that it is not likely that either their constitutions or their reproductive systems should have been profoundly modified. Moreover, most of the varieties which have been experimentized on have been produced under domestication, and as domestication apparently tends to eliminate sterility, we ought not to expect it also to produce sterility. The sterility of hybrids is a very different case from that of first crosses, for their reproductive organs are more or less functionally impotent, whereas in first crosses the organs on both sides are in a perfect condition. As we continually see that organisms of all kinds are rendered in some degree sterile from their constitutions having been disturbed by slightly different and new conditions of life, we need not feel surprise at hybrids being in some degree sterile, for their constitutions can hardly fail to have been disturbed from being compounded of 2 distinct organizations. This parallelism is supported by another parallel, but directly opposite, class of facts, namely, that the vigor and fertility of all organic beings are increased by slight changes in their conditions of life, and that the offspring of slightly modified forms or varieties acquire from being crossed increased vigor and fertility. So that, on the one hand, considerable changes in the conditions of life and crosses between greatly modified forms lessen fertility, and on the other hand, lesser changes in the conditions of life and crosses between less modified forms increase fertility. Turning to geographical distribution, the difficulties encountered on the theory of descent with modification are grave enough. All the individuals of the same species, and all the species of the same genus, or even higher group, must have descended from common parents, and therefore, in however distant and isolated parts of the world they are now found, they must in the course of successive generations have passed from some one part to the others. We are often wholly unable even to conjecture how this could have been effected. Yet, as we have reason to believe that some species have retained the same specific form for very long periods, enormously long as measured by years, too much stress ought not to be laid on the occasional wide diffusion of the same species, for during very long periods of time there will always be a good chance for wide migration by many means. A broken or interrupted range may often be accounted for by the extinction of the species in the intermediate regions. It cannot be denied that we are as yet very ignorant of the full extent of the various climatal and geographical changes which have affected the Earth during modern periods, and such changes will obviously have greatly facilitated migration. As an example, I have attempted to show how potent has been the influence of the glacial period on the distribution both of the same and of representative species throughout the world. We are as yet profoundly ignorant of the many occasional means of transport. With respect to distinct species of the same genus inhabiting very distant and isolated regions, as the process of modification has necessarily been slow, all the means of migration will have been possible during a very long period, and consequently the difficulty of the wide diffusion of species of the same genus is in some degree lessened. As on the theory of natural selection an interminable number of intermediate forms must have existed, linking together all the species in each group by gradations as fine as our present varieties, it may be asked, why do we not see these linking forms all around us? Why are not all organic beings blended together in an inextricable chaos? With respect to existing forms, we should remember that we have no right to expect, excepting in rare cases, to discover directly connecting links between them, but only between each and some extinct and supplanted form. Even on a wide area, which has during a long period remained continuous, and of which the climate and other conditions of life change insensibly in going from a district occupied by one species into another district occupied by a closely allied species, we have no just right to expect often to find intermediate varieties in the intermediate zone. For we have reason to believe that only a few species are undergoing change at any one period, and all changes are slowly effected. I have also shown that the intermediate varieties which will at first probably exist in the intermediate zones, will be liable to be supplanted by the allied forms on either hand, and the latter, from existing in greater numbers, will generally be modified and improved at a quicker rate than the intermediate varieties, which exist in lesser numbers, so that the intermediate varieties will, in the long run, be supplanted and exterminated. On this doctrine of the extermination of an infinitude of connecting links, between the living and extinct inhabitants of the world, and at each successive period between the extinct and still older species, why is not every geological formation charged with such links? Why does not every collection of fossil remains afford plain evidence of the gradation and mutation of the forms of life? We meet with no such evidence, and this is the most obvious and forcible of the many objections which may be urged against my theory. Why, again, do whole groups of allied species appear, though certainly they often falsely appear, to have come in suddenly on the several geological stages? Why do we not find great piles of strata beneath the Silurian system, stored with the remains of the progenitors of the Silurian groups of fossils? For certainly on my theory such strata must somewhere have been deposited at these ancient and utterly unknown epochs in the world's history. I can answer these questions and grave objections only on the supposition that the geological record is far more imperfect than most geologists believe. It cannot be objected that there has not been time sufficient for any amount of organic change, for the lapse of time has been so great as to be utterly inappreciable by the human intellect. The number of specimens in all our museums is absolutely as nothing compared with the countless generations of countless species which certainly have existed. We should not be able to recognize a species as the parent of any one or more species if we were to examine them ever so closely, unless we likewise possessed many of the intermediate links between their past or parent and present states, and these many links we could hardly ever expect to discover, owing to the imperfection of the geological record. Numerous existing doubtful forms could be named which are probably varieties, but who will pretend that in future ages so many fossil links will be discovered that naturalists will be able to decide, on the common view, whether or not these doubtful forms are varieties? As long as most of the links between any two species are unknown, if any one link or intermediate variety be discovered, it will simply be classed as another and distinct species. Only a small portion of the world has been geologically explored. Only organic beings of certain classes can be preserved in a fossil condition, at least in any great number. Widely ranging species vary most, and varieties are often at first local, both causes rendering the discovery of intermediate links less likely. Local varieties will not spread into other and distant regions until they are considerably modified and improved, and when they do spread, if discovered in a geological formation, they will appear as if suddenly created there, and will be simply classed as new species. Most formations have been intermittent in their accumulation, and their duration, I am inclined to believe, has been shorter than the average duration of specific forms. Successive formations are separated from each other by enormous blank intervals of time, for fossiliferous formations, thick enough to resist future degradation, can be accumulated only where much sediment is deposited on the subsiding bed of the sea. During the alternate periods of elevation and of stationary level the record will be blank. During these latter periods there will probably be more variability in the forms of life, during periods of subsidence, more extinction. With respect to the absence of fossiliferous formations beneath the lowest Silurian strata, I can only recur to the hypothesis given in the 9th chapter. That the geological record is imperfect all will admit, but that it is imperfect to the degree which I require, few will be inclined to admit. If we look to long enough intervals of time, geology plainly declares that all species have changed, and they have changed in the manner which my theory requires, for they have changed slowly and in a graduated manner. We clearly see this in the fossil remains from consecutive formations invariably being much more closely related to each other than are the fossils from formations distant from each other in time. Such is the sum of the several chief objections and difficulties which may justly be urged against my theory, and I have now briefly recapitulated the answers and explanations which can be given to them. I have felt these difficulties far too heavily during many years to doubt their weight. But it deserves especial notice that the more important objections relate to questions on which we are confessedly ignorant, nor do we know how ignorant we are. We do not know all the possible transitional gradations between the simplest and the most perfect organs. It cannot be pretended that we know all the varied means of distribution during the long lapse of years, or that we know how imperfect the geological record is. Grave as these several difficulties are, in my judgment they do not overthrow the theory of descent with modification. Now let us turn to the other side of the argument. Under domestication we see much variability. This seems to be mainly due to the reproductive system being eminently susceptible to changes in the conditions of life, so that this system, when not rendered impotent, fails to reproduce offspring exactly like the parent form. Variability is governed by many complex laws, by correlation of growth, by use and disuse, and by the direct action of the physical conditions of life. There is much difficulty in ascertaining how much modification our domestic productions have undergone, but we may safely infer that the amount has been large, and that modifications can be inherited for long periods. As long as the conditions of life remain the same, we have reason to believe that a modification, which has already been inherited for many generations, may continue to be inherited for an almost infinite number of generations. On the other hand, we have evidence that variability, when it has once come into play, does not wholly cease, for new varieties are still occasionally produced by our most anciently domesticated productions. Man does not actually produce variability, he only unintentionally exposes organic beings to new conditions of life, and then nature acts on the organization, and causes variability. But man can and does select the variations given to him by nature, and thus accumulate them in any desired manner. He thus adapts animals and plants for his own benefit or pleasure. He may do this methodically, or he may do it unconsciously by preserving the individuals most useful to him at the time, without any thought of altering the breed. It is certain that he can largely influence the character of a breed by selecting, in each successive generation, individual differences so slight as to be quite inappreciable by an uneducated eye. This process of selection has been the great agency in the production of the most distinct and useful domestic breeds. That many of the breeds produced by man have to a large extent the character of natural species, is shown by the inextricable doubts whether very many of them are varieties or aboriginal species. There is no obvious reason why the principles which have acted so efficiently under domestication should not have acted under nature. In the preservation of favored individuals and races, during the constantly recurrent struggle for existence, we see the most powerful and ever-acting means of selection. The struggle for existence inevitably follows from the high geometrical ratio of increase which is common to all organic beings. This high rate of increase is proved by calculation, by the effects of a succession of peculiar seasons, and by the results of naturalization, as explained in the 3rd chapter. More individuals are born than can possibly survive. A grain in the balance will determine which individual shall live and which shall die, which variety or species shall increase in number, and which shall decrease, or finally become extinct. As the individuals of the same species come in all respects into the closest competition with each other, the struggle will generally be most severe between them. It will be almost equally severe between the varieties of the same species, and next in severity between the species of the same genus. But the struggle will often be very severe between beings most remote in the scale of nature. The slightest advantage in one being, at any age or during any season, over those with which it comes into competition, or better adaptation in however slight a degree to the surrounding physical conditions, will turn the balance. With animals having separated sexes, there will in most cases be a struggle between the males for possession of the females. The most vigorous individuals, or those which have most successfully struggled with their conditions of life, will generally leave most progeny. But success will often depend on having special weapons or means of defense, or on the charms of the males, and the slightest advantage will lead to victory. As geology plainly proclaims that each land has undergone great physical changes, we might have expected that organic beings would have varied under nature, in the same way as they generally have varied under the changed conditions of domestication. And if there be any variability under nature, it would be an unaccountable fact if natural selection had not come into play. It has often been asserted, but the assertion is quite incapable of proof, that the amount of variation under nature is a strictly limited quantity. Man, though acting on external characters alone and often capriciously, can produce within a short period a great result by adding up mere individual differences in his domestic productions, and every one admits that there are at least individual differences in species under nature. But, besides such differences, all naturalists have admitted the existence of varieties, which they think sufficiently distinct to be worthy of record in systematic works. No one can draw any clear distinction between individual differences and slight varieties, or between more plainly marked varieties and subspecies and species. Let it be observed how naturalists differ in the rank which they assign to the many representative forms in Europe and North America. If then we have under nature variability and a powerful agent always ready to act and select, why should we doubt that variations in any way useful to beings, under their excessively complex relations of life, would be preserved, accumulated, and inherited? Why, if man can by patience select variations most useful to himself, should nature fail in selecting variations useful, under changing conditions of life, to her living products? What limit can be put to this power, acting during long ages and rigidly scrutinizing the whole constitution, structure, and habits of each creature, favoring the good and rejecting the bad? I can see no limit to this power, in slowly and beautifully adapting each form to the most complex relations of life. The theory of natural selection, even if we looked no further than this, seems to me to be in itself probable. I have already recapitulated, as fairly as I could, the opposed difficulties and objections. Now let us turn to the special facts and arguments in favor of the theory. On the view that species are only strongly marked and permanent varieties, and that each species first existed as a variety, we can see why it is that no line of demarcation can be drawn between species, commonly supposed to have been produced by special acts of creation, and varieties which are acknowledged to have been produced by secondary laws. On this same view we can understand how it is that in each region where many species of a genus have been produced, and where they now flourish, these same species should present many varieties, for where the manufactory of species has been active, we might expect, as a general rule, to find it still in action, and this is the case if varieties be incipient species. Moreover, the species of the larger genera, which afford the greater number of varieties or incipient species, retain to a certain degree the character of varieties, for they differ from each other by a less amount of difference than do the species of smaller genera. The closely allied species also of the larger genera apparently have restricted ranges, and they are clustered in little groups round other species, in which respects they resemble varieties. These are strange relations on the view of each species having been independently created, but are intelligible if all species first existed as varieties. As each species tends by its geometrical ratio of reproduction to increase inordinately in number, and as the modified descendants of each species will be enabled to increase by so much the more as they become more diversified in habits and structure, so as to be enabled to seize on many and widely different places in the economy of nature, there will be a constant tendency in natural selection to preserve the most divergent offspring of any one species. Hence, during a long-continued course of modification, the slight differences, characteristic of varieties of the same species, tend to be augmented into the greater differences characteristic of species of the same genus. New and improved varieties will inevitably supplant and exterminate the older, less improved and intermediate varieties, and thus species are rendered to a large extent defined and distinct objects. Dominant species belonging to the larger groups tend to give birth to new and dominant forms, so that each large group tends to become still larger, and at the same time more divergent in character. But as all groups cannot thus succeed in increasing in size, for the world would not hold them, the more dominant groups beat the less dominant. This tendency in the large groups to go on increasing in size and diverging in character, together with the almost inevitable contingency of much extinction, explains the arrangement of all the forms of life, in groups subordinate to groups, all within a few great classes, which we now see everywhere around us, and which has prevailed throughout all time. This grand fact of the grouping of all organic beings seems to me utterly inexplicable on the theory of creation. As natural selection acts solely by accumulating slight, successive, favorable variations, it can produce no great or sudden modification, it can act only by very short and slow steps. Hence the canon of natura non facit saltum, which every fresh addition to our knowledge tends to make more strictly correct, is on this theory simply intelligible. We can plainly see why nature is prodigal in variety, though niggard in innovation. But why this should be a law of nature if each species has been independently created, no man can explain. Many other facts are, as it seems to me, explicable on this theory. How strange it is that a bird, under the form of woodpecker, should have been created to prey on insects on the ground, that upland geese, which never or rarely swim, should have been created with webbed feet, that a thrush should have been created to dive and feed on subaquatic insects, and that a petrel should have been created with habits and structure fitting it for the life of an auk or grebe. And so on in endless other cases. But on the view of each species constantly trying to increase in number, with natural selection always ready to adapt the slowly varying descendants of each to any unoccupied or ill-occupied place in nature, these facts cease to be strange, or perhaps might even have been anticipated. As natural selection acts by competition, it adapts the inhabitants of each country only in relation to the degree of perfection of their associates, so that we need feel no surprise at the inhabitants of any one country, although on the ordinary view supposed to have been specially created and adapted for that country, being beaten and supplanted by the naturalized productions from another land. Nor ought we to marvel if all the contrivances in nature be not, as far as we can judge, absolutely perfect, and if some of them be abhorrent to our ideas of fitness. We need not marvel at the sting of the bee causing the bee's own death, at drones being produced in such vast numbers for one single act, and being then slaughtered by their sterile sisters, at the astonishing waste of pollen by our fir trees, at the instinctive hatred of the queen bee for her own fertile daughters, at ichneumonidae feeding within the live bodies of caterpillars, and at other such cases. The wonder indeed is, on the theory of natural selection, that more cases of the want of absolute perfection have not been observed. The complex and little-known laws governing variation are the same, as far as we can see, with the laws which have governed the production of so-called specific forms. In both cases physical conditions seem to have produced but little direct effect, yet when varieties enter any zone, they occasionally assume some of the characters of the species proper to that zone. In both varieties and species, use and disuse seem to have produced some effect, for it is difficult to resist this conclusion when we look, for instance, at the logger-headed duck, which has wings incapable of flight, in nearly the same condition as in the domestic duck, or when we look at the burrowing tucutucu, which is occasionally blind, and then at certain moles, which are habitually blind and have their eyes covered with skin, or when we look at the blind animals inhabiting the dark caves of America and Europe. In both varieties and species, correlation of growth seems to have played a most important part, so that when one part has been modified, other parts are necessarily modified. In both varieties and species, reversions to long-lost characters occur. How inexplicable on the theory of creation is the occasional appearance of stripes on the shoulder and legs of the several species of the horse genus and in their hybrids. How simply is this fact explained if we believe that these species have descended from a striped progenitor, in the same manner as the several domestic breeds of pigeon have descended from the blue and barred rock pigeon? On the ordinary view of each species having been independently created, why should the specific characters, or those by which the species of the same genus differ from each other, be more variable than the generic characters in which they all agree? Why, for instance, should the color of a flower be more likely to vary in any one species of a genus, if the other species, supposed to have been created independently, have differently colored flowers, than if all the species of the genus have the same colored flowers? If species are only well-marked varieties, of which the characters have become in a high degree permanent, we can understand this fact, for they have already varied since they branched off from a common progenitor in certain characters, by which they have come to be specifically distinct from each other. And therefore these same characters would be more likely still to be variable than the generic characters which have been inherited without change for an enormous period. It is inexplicable on the theory of creation why a part developed in a very unusual manner in any one species of a genus, and therefore, as we may naturally infer, of great importance to the species, should be eminently liable to variation, but, on my view, this part has undergone, since the several species branched off from a common progenitor, an unusual amount of variability and modification, and therefore we might expect this part generally to be still variable. But a part may be developed in the most unusual manner, like the wing of a bat, and yet not be more variable than any other structure, if the part be common to many subordinate forms, that is, if it has been inherited for a very long period, for in this case it will have been rendered constant by long-continued natural selection. Glancing at instincts, marvelous as some are, they offer no greater difficulty than does corporeal structure on the theory of the natural selection of successive, slight, but profitable modifications. We can thus understand why nature moves by graduated steps in endowing different animals of the same class with their several instincts. I have attempted to show how much light the principle of gradation throws on the admirable architectural powers of the hive bee. Habit no doubt sometimes comes into play in modifying instincts, but it certainly is not indispensable, as we see, in the case of neuter insects, which leave no progeny to inherit the effects of long-continued habit. On the view of all the species of the same genus having descended from a common parent, and having inherited much in common, we can understand how it is that allied species, when placed under considerably different conditions of life, yet should follow nearly the same instincts, why the thrush of South America, for instance, lines her nest with mud like our British species. On the view of instincts having been slowly acquired through natural selection, we need not marvel at some instincts being apparently not perfect and liable to mistakes, and at many instincts causing other animals to suffer. If species be only well-marked and permanent varieties, we can at once see why their crossed offspring should follow the same complex laws in their degrees and kinds of resemblance to their parents, in being absorbed into each other by successive crosses, and in other such points, as do the crossed offspring of acknowledged varieties. On the other hand, these would be strange facts if species have been independently created, and varieties have been produced by secondary laws. If we admit that the geological record is imperfect in an extreme degree, then such facts as the record gives support the theory of descent with modification. New species have come on the stage slowly and at successive intervals, and the amount of change, after equal intervals of time, is widely different in different groups. The extinction of species and of whole groups of species, which has played so conspicuous a part in the history of the organic world, almost inevitably follows on the principle of natural selection, for old forms will be supplanted by new and improved forms. Neither single species nor groups of species reappear when the chain of ordinary generation has once been broken. The gradual diffusion of dominant forms, with the slow modification of their descendants, causes the forms of life, after long intervals of time, to appear as if they had changed simultaneously throughout the world. The fact of the fossil remains of each formation being in some degree intermediate in character between the fossils in the formations above and below is simply explained by their intermediate position in the chain of descent. The grand fact that all extinct organic beings belong to the same system with recent beings, falling either into the same or into intermediate groups, follows from the living and the extinct being the offspring of common parents. As the groups which have descended from an ancient progenitor have generally diverged in character, the progenitor with its early descendants will often be intermediate in character in comparison with its later descendants, and thus we can see why the more ancient a fossil is, the oftener it stands in some degree intermediate between existing and allied groups. Recent forms are generally looked at as being, in some vague sense, higher than ancient and extinct forms, and they are in so far higher as the later and more improved forms have conquered the older and less improved organic beings in the struggle for life. Lastly, the law of the long endurance of allied forms on the same continent, of marsupials in Australia, of Edentata in America, and other such cases, is intelligible, for within a confined country, the recent and the extinct will naturally be allied by descent. Looking to geographical distribution, if we admit that there has been during the long course of ages much migration from one part of the world to another, owing to former climatal and geographical changes and to the many occasional and unknown means of dispersal, then we can understand, on the theory of descent with modification, most of the great leading facts in distribution. We can see why there should be so striking a parallelism in the distribution of organic beings throughout space, and in their geological succession throughout time, for in both cases the beings have been connected by the bond of ordinary generation, and the means of modification have been the same. We see the full meaning of the wonderful fact, which must have struck every traveler, namely, that on the same continent, under the most diverse conditions, under heat and cold, on mountain and lowland, on deserts and marshes, most of the inhabitants within each great class are plainly related, for they will generally be descendants of the same progenitors and early colonists. On this same principle of former migration, combined in most cases with modification, we can understand, by the aid of the glacial period, the identity of some few plants, and the close alliance of many others, on the most distant mountains, under the most different climates, and likewise the close alliance of some of the inhabitants of the sea in the northern and southern temperate zones, though separated by the whole intertropical ocean. Although two areas may present the same physical conditions of life, we need feel no surprise at their inhabitants being widely different if they have been for a long period completely separated from each other, for as the relation of organism to organism is the most important of all relations, and as the two areas will have received colonists from some third source or from each other, at various periods and in different proportions, the course of modification in the two areas will inevitably be different. On this view of migration, with subsequent modification, we can see why oceanic islands should be inhabited by few species, but of these, that many should be peculiar. We can clearly see why those animals which cannot cross wide spaces of ocean, as frogs and terrestrial mammals, should not inhabit oceanic islands, and why, on the other hand, new and peculiar species of bats, which can traverse the ocean, should so often be found on islands far distant from any continent. Such facts as the presence of peculiar species of bats, and the absence of all other mammals, on oceanic islands, are utterly inexplicable on the theory of independent acts of creation. The existence of closely allied or representative species in any two areas, implies, on the theory of descent with modification, that the same parents formerly inhabited both areas, and we almost invariably find that wherever many closely allied species inhabit two areas, some identical species common to both still exist. Wherever many closely allied yet distinct species occur, many doubtful forms and varieties of the same species likewise occur. It is a rule of high generality that the inhabitants of each area are related to the inhabitants of the nearest source whence immigrants might have been derived. We see this in nearly all the plants and animals of the Galapagos archipelago, of Juan Fernandez, and of the other American islands being related in the most striking manner to the plants and animals of the neighboring American mainland, and those of the Cape de Verde archipelago and other African islands to the African mainland. It must be admitted that these facts receive no explanation on the theory of creation. The fact, as we have seen, that all past and present organic beings constitute one grand natural system, with group subordinate to group, and with extinct groups often falling in between recent groups, is intelligible on the theory of natural selection with its contingencies of extinction and divergence of character. On these same principles we see how it is, that the mutual affinities of the species and genera within each class are so complex and circuitous. We see why certain characters are far more serviceable than others for classification, why adaptive characters, though of paramount importance to the being, are of hardly any importance in classification, why characters derived from rudimentary parts, though of no service to the being, are often of high classificatory value, and why embryological characters are the most valuable of all. The real affinities of all organic beings are due to inheritance or community of descent. The natural system is a genealogical arrangement, in which we have to discover the lines of descent by the most permanent characters, however slight their vital importance may be. The framework of bones being the same in the hand of a man, wing of a bat, fin of the porpoise, and leg of the horse, the same number of vertebrae forming the neck of the giraffe and of the elephant, and innumerable other such facts, at once explain themselves on the theory of descent with slow and slight successive modifications. The similarity of pattern in the wing and leg of a bat, though used for such different purpose, in the jaws and legs of a crab, in the petals, stamens, and pistils of a flower, is likewise intelligible on the view of the gradual modification of parts or organs, which were alike in the early progenitor of each class. On the principle of successive variations not always supervening at an early age, and being inherited at a corresponding not early period of life, we can clearly see why the embryos of mammals, birds, reptiles, and fishes should be so closely alike, and should be so unlike the adult forms. We may cease marveling at the embryo of an air-breathing mammal or bird having branchial slits and arteries running in loops, like those in a fish which has to breathe the air dissolved in water, by the aid of well-developed branchiae. Disuse, aided sometimes by natural selection, will often tend to reduce an organ when it has become useless by changed habits or under changed conditions of life, and we can clearly understand on this view the meaning of rudimentary organs. But disuse and selection will generally act on each creature when it has come to maturity and has to play its full part in the struggle for existence, and will thus have little power of acting on an organ during early life, hence the organ will not be much reduced or rendered rudimentary at this early age. The calf, for instance, has inherited teeth, which never cut through the gums of the upper jaw, from an early progenitor having well-developed teeth, and we may believe that the teeth in the mature animal were reduced, during successive generations, by disuse or by the tongue and palate having been fitted by natural selection to browse without their aid, whereas in the calf, the teeth have been left untouched by selection or disuse, and on the principle of inheritance at corresponding ages, have been inherited from a remote period to the present day. On the view of each organic being and each separate organ having been specially created, how utterly inexplicable it is that parts, like the teeth in the embryonic calf or like the shriveled wings under the sodded wing covers of some beetles, should thus so frequently bear the plain stamp of inutility. Nature may be said to have taken pains to reveal, by rudimentary organs and by homologous structures, her scheme of modification, which it seems that we willfully will not understand. I have now recapitulated the chief facts and considerations which have thoroughly convinced me that species have changed, and are still slowly changing by the preservation and accumulation of successive slight favorable variations. Why, it may be asked, have all the most eminent living naturalists and geologists rejected this view of the mutability of species? It cannot be asserted that organic beings in a state of nature are subject to no variation. It cannot be proved that the amount of variation in the course of long ages is a limited quantity. No clear distinction has been, or can be, drawn between species and well-marked varieties. It cannot be maintained that species when intercrossed are invariably sterile, and varieties invariably fertile, or that sterility is a special endowment and sign of creation. The belief that species were immutable productions was almost unavoidable as long as the history of the world was thought to be of short duration, and now that we have acquired some idea of the lapse of time, we are too apt to assume, without proof, that the geological record is so perfect that it would have afforded us plain evidence of the mutation of species, if they had undergone mutation. But the chief cause of our natural unwillingness to admit that one species has given birth to other and distinct species, is that we are always slow in admitting any great change of which we do not see the intermediate steps. The difficulty is the same as that felt by so many geologists, when Lyell first insisted that long lines of inland cliffs had been formed, and great valleys excavated, by the slow action of the coast waves. The mind cannot possibly grasp the full meaning of the term of 100 million years, it cannot add up and perceive the full effects of many slight variations, accumulated during an almost infinite number of generations. Although I am fully convinced of the truth of the views given in this volume under the form of an abstract, I by no means expect to convince experienced naturalists whose minds are stocked with a multitude of facts all viewed, during a long course of years, from a point of view directly opposite to mine. It is so easy to hide our ignorance under such expressions as the plan of creation, unity of design, etc., and to think that we give an explanation when we only restate a fact. Anyone whose disposition leads him to attach more weight to unexplained difficulties than to the explanation of a certain number of facts will certainly reject my theory. A few naturalists, endowed with much flexibility of mind, and who have already begun to doubt on the immutability of species, may be influenced by this volume, but I look with confidence to the future, to young and rising naturalists, who will be able to view both sides of the question with impartiality. Whoever is led to believe that species are mutable will do good service by conscientiously expressing his conviction, for only thus can the load of prejudice by which this subject is overwhelmed be removed. Several eminent naturalists have of late published their belief that a multitude of reputed species in each genus are not real species, but that other species are real, that is, have been independently created. This seems to me a strange conclusion to arrive at. They admit that a multitude of forms, which till lately they themselves thought were special creations, and which are still thus looked at by the majority of naturalists, and which consequently have every external characteristic feature of true species, they admit that these have been produced by variation, but they refuse to extend the same view to other and very slightly different forms. Nevertheless, they do not pretend that they can define, or even conjecture, which are the created forms of life, and which are those produced by secondary laws. They admit variation as a vera causa in one case, they arbitrarily reject it in another, without assigning any distinction in the two cases. The day will come when this will be given as a curious illustration of the blindness of preconceived opinion. These authors seem no more startled at a miraculous act of creation than at an ordinary birth. But do they really believe that at innumerable periods in the Earth's history certain elemental atoms have been commanded suddenly to flash into living tissues? Do they believe that at each supposed act of creation one individual or many were produced? Were all the infinitely numerous kinds of animals and plants created as eggs or seed, or as full-grown? And in the case of mammals, were they created bearing the false marks of nourishment from the mother's womb? Although naturalists very properly demand a full explanation of every difficulty from those who believe in the mutability of species, on their own side they ignore the whole subject of the first appearance of species in what they consider reverent silence. It may be asked how far I extend the doctrine of the modification of species. The question is difficult to answer, because the more distinct the forms are which we may consider, by so much the arguments fall away in force. But some arguments of the greatest weight extend very far. All the members of whole classes can be connected together by chains of affinities, and all can be classified on the same principle, in groups subordinate to groups. Fossil remains sometimes tend to fill up very wide intervals between existing orders. Organs in a rudimentary condition plainly show that an early progenitor had the organ in a fully developed state, and this in some instances necessarily implies an enormous amount of modification in the descendants. Throughout whole classes various structures are formed on the same pattern, and at an embryonic age the species closely resemble each other. Therefore I cannot doubt that the theory of descent with modification embraces all the members of the same class. I believe that animals have descended from at most only 4 or 5 progenitors, and plants from an equal or lesser number. Analogy would lead me one step further, namely, to the belief that all animals and plants have descended from some one prototype. But analogy may be a deceitful guide. Nevertheless, all living things have much in common, in their chemical composition, their germinal vesicles, their cellular structure, and their laws of growth and reproduction. We see this even in so trifling a circumstance as that the same poison often similarly affects plants and animals, or that the poison secreted by the gallfly produces monstrous growths on the wild rose or oak tree. Therefore I should infer from analogy that probably all the organic beings which have ever lived on this earth have descended from some one primordial form, into which life was first breathed. When the views entertained in this volume on the origin of species, or when analogous views are generally admitted, we can dimly foresee that there will be a considerable revolution in natural history. Systematists will be able to pursue their labors as at present, but they will not be incessantly haunted by the shadowy doubt whether this or that form be in essence a species. This I feel sure, and I speak after experience, will be no slight relief. The endless disputes whether or not some 50 species of British brambles are true species will cease. Systematists will have only to decide, not that this will be easy, whether any form be sufficiently constant and distinct from other forms, to be capable of definition, and if definable, whether the differences be sufficiently important to deserve a specific name. This latter point will become a far more essential consideration than it is at present, for differences, however slight, between any two forms, if not blended by intermediate gradations, are looked at by most naturalists as sufficient to raise both forms to the rank of species. Hereafter we shall be compelled to acknowledge that the only distinction between species and well-marked varieties is, that the latter are known, or believed, to be connected at the present day by intermediate gradations, whereas species were formerly thus connected. Hence, without quite rejecting the consideration of the present existence of intermediate gradations between any two forms, we shall be led to weigh more carefully and to value higher the actual amount of difference between them. It is quite possible that forms now generally acknowledged to be merely varieties may hereafter be thought worthy of specific names, as with the primrose and cowslip, and in this case scientific and common language will come into accordance. In short, we shall have to treat species in the same manner as those naturalists treat genera, who admit that genera are merely artificial combinations made for convenience. This may not be a cheering prospect, but we shall at least be freed from the vain search for the undiscovered and undiscoverable essence of the term species. The other and more general departments of natural history will rise greatly in interest. The terms used by naturalists of affinity, relationship, community of type, paternity, morphology, adaptive characters, rudimentary and aborted organs, etc., will cease to be metaphorical, and will have a plain signification. When we no longer look at an organic being as a savage looks at a ship, as at something wholly beyond his comprehension, when we regard every production of nature as one which has had a history, when we contemplate every complex structure and instinct as the summing up of many contrivances, each useful to the possessor, nearly in the same way as when we look at any great mechanical invention as the summing up of the labor, the experience, the reason, and even the blunders of numerous workmen. When we thus view each organic being, how far more interesting, I speak from experience, will the study of natural history become? A grand and almost untrodden field of inquiry will be opened, on the causes and laws of variation, on correlation of growth, on the effects of use and disuse, on the direct action of external conditions, and so forth. The study of domestic productions will rise immensely in value. A new variety raised by man will be a far more important and interesting subject for study than one more species added to the infinitude of already recorded species. Our classifications will come to be, as far as they can be so made, genealogies, and will then truly give what may be called the plan of creation. The rules for classifying will no doubt become simpler when we have a definite object in view. We possess no pedigrees or armorial bearings, and we have to discover and trace the many diverging lines of descent in our natural genealogies, by characters of any kind which have long been inherited. Rudimentary organs will speak infallibly with respect to the nature of long-lost structures. Species and groups of species, which are called aberrant, and which may fancifully be called living fossils, will aid us in forming a picture of the ancient forms of life. Embryology will reveal to us the structure, in some degree obscured, of the prototypes of each great class. When we can feel assured that all the individuals of the same species, and all the closely allied species of most genera, have within a not very remote period descended from one parent, and have migrated from some one birthplace, and when we better know the many means of migration, then, by the light which geology now throws, and will continue to throw, on former changes of climate and of the level of the land, we shall surely be enabled to trace in an admirable manner the former migrations of the inhabitants of the whole world. Even at present, by comparing the differences of the inhabitants of the sea on the opposite sides of a continent, and the nature of the various inhabitants of that continent in relation to their apparent means of immigration, some light can be thrown on ancient geography. The noble science of geology loses glory from the extreme imperfection of the record. The crust of the earth with its embedded remains must not be looked at as a well-filled museum, but as a poor collection made at hazard and at rare intervals. The accumulation of each great fossiliferous formation will be recognized as having depended on an unusual concurrence of circumstances, and the blank intervals between the successive stages as having been of vast duration. But we shall be able to gauge with some security the duration of these intervals by a comparison of the preceding and succeeding organic forms. We must be cautious in attempting to correlate as strictly contemporaneous two formations, which include few identical species, by the general succession of their forms of life. As species are produced and exterminated by slowly acting and still existing causes, and not by miraculous acts of creation and by catastrophes, and as the most important of all causes of organic change is one which is almost independent of altered and perhaps suddenly altered physical conditions, namely, the mutual relation of organism to organism, the improvement of one being entailing the improvement or the extermination of others, it follows that the amount of organic change in the fossils of consecutive formations probably serves as a fair measure of the lapse of actual time. A number of species, however, keeping in a body might remain for a long period unchanged, whilst within this same period, several of these species, by migrating into new countries and coming into competition with foreign associates, might become modified, so that we must not overrate the accuracy of organic change as a measure of time. During early periods of the Earth's history, when the forms of life were probably fewer and simpler, the rate of change was probably slower, and at the first dawn of life, when very few forms of the simplest structure existed, the rate of change may have been slow in an extreme degree. The whole history of the world, as at present known, although of a length quite incomprehensible by us, will hereafter be recognized as a mere fragment of time, compared with the ages which have elapsed since the first creature, the progenitor of innumerable extinct and living descendants, was created. In the distant future I see open fields for far more important researches. Psychology will be based on a new foundation, that of the necessary acquirement of each mental power and capacity by gradation. Light will be thrown on the origin of man and his history. Authors of the highest eminence seem to be fully satisfied with the view that each species has been independently created. To my mind it accords better with what we know of the laws impressed on matter by the Creator, that the production and extinction of the past and present inhabitants of the world should have been due to secondary causes, like those determining the birth and death of the individual. When I view all beings not as special creations, but as the lineal descendants of some few beings which lived long before the first bed of the Silurian system was deposited, they seem to me to become ennobled. Judging from the past, we may safely infer that not one living species will transmit its unaltered likeness to a distant futurity. And of the species now living very few will transmit progeny of any kind to a far distant futurity, for the manner in which all organic beings are grouped shows that the greater number of species of each genus, and all the species of many genera, have left no descendants, but have become utterly extinct. We can so far take a prophetic glance into futurity as to foretell that it will be the common and wideless-bred species, belonging to the larger and dominant groups, which will ultimately prevail and procreate new and dominant species. As all the living forms of life are the lineal descendants of those which lived long before the Silurian epoch, we may feel certain that the ordinary succession by generation has never once been broken, and that no cataclysm has desolated the whole world. Hence we may look with some confidence to a secure future of equally inappreciable length. And as natural selection works solely by and for the good of each being, all corporeal and mental endowments will tend to progress towards perfection. It is interesting to contemplate an entangled bank, clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other, and dependent on each other in so complex a manner, have all been produced by laws acting around us. These laws, taken in the largest sense, being growth with reproduction, inheritance which is almost implied by reproduction, variability from the indirect and direct action of the external conditions of life, and from use and disuse, a ratio of increase so high as to lead to a struggle for life, and as a consequence to natural selection, entailing divergence of character and the extinction of less improved forms. Thus, from the war of nature, from famine and death, the most exalted object which we are capable of conceiving, namely, the production of the higher animals, directly follows. There is grandeur in this view of life, with its several powers, having been originally breathed into a few forms or into one, and that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning endless forms most beautiful and most wonderful have been, and are being, evolved.